Hello and welcome back. I'm glad you're here. Maybe you've had a long day, one of those days where the world felt a bit too loud, too fast, too much. Or perhaps you're just settling in for the night, looking for something to occupy your mind gently as you drift towards sleep. Either way, you're in the right place. Tonight, we're going on a journey together. Not a hurried one, but a slow walk through some of the most profound discoveries humanity has ever made. We're talking about the moments when everything changed, when someone looked at the world just a little differently and suddenly reality itself shifted. These aren't just facts to memorize for a test, they're invitations to see the universe and yourself in a new light. We'll explore 100 of these discoveries, from the nature of time itself to the invisible forces that hold atoms together. Some will feel familiar, like old friends you haven't thought about in years. Others might be entirely new, strange and beautiful in ways that make you pause and wonder. And that's exactly the point, to wonder gently as you let the day fall away. Before we begin, if you're enjoying these journeys into the cosmos, a like or a comment helps others find their way here too. And if you subscribe, you'll have a library of nights like this waiting for you whenever you need them. But no pressure. You're here now, and that's what matters. So find a comfortable position, let your breathing slow, and whenever you're ready, let's begin. We discovered that time itself can slow down and speed up depending on how fast you're moving or how strong gravity is around you. For most of human history, time seemed like the one thing we could count on. Empires rose and fell, stars were born and died, but time just flowed, steady and unchanging, like a river carrying everything along at the same pace. The second you experienced was the same second I experienced, was the same second someone on the other side of the planet experienced. It was the metronome of the universe, keeping everything in sync. And then came Albert Einstein. In the early 1900s, Einstein proposed something that seemed almost absurd. Time isn't the same for everyone. If you're moving very fast, say close to the speed of light, time actually slows down for you compared to someone standing still. And if you're near something with intense gravity, like a black hole, time stretches and warps, moving slower for you than for someone farther away. It wasn't that our clocks were broken or that we were measuring wrong. Time itself, the fabric of reality, was flexible. This idea, called relativity, suggested that time isn't a fixed river at all. It's more like a sheet of fabric that can bend and stretch and twist depending on how fast you're moving through space and how strong the gravity around you is. Imagine two twins. One stays on Earth, the other travels on a spaceship at nearly the speed of light. When the traveling twin returns, they've aged only a few years, while their sibling has grown old. It sounds like science fiction, but it's been proven again and again with atomic clocks and GPS satellites. Time isn't universal, it's personal, relative, woven into the very structure of space-time. It's enough to make your head spin if you think about it too hard. But there's something oddly comforting in it, too. Time isn't this rigid, unyielding thing we're trapped in. It's flexible, negotiable in a sense. Maybe that's why the universe feels less like a machine and more like something alive, something that breathes and shifts, and maybe, just maybe, that's a gentler way to move through the world, knowing that even time itself can bend. In 1953, We cracked the double helix structure of DNA and found the instruction manual for all known life written in just 4 chemical letters. If you've ever wondered what makes you, well, you, what determines the color of your eyes, the shape of your nose, the way your brain processes these very words, the answer is written in a language older than any civilization. It's written in your cells, in a molecule called DNA, and it uses an alphabet of just 4 letters, A, T, G, and C. For a long time, scientists knew that something in our cells carried hereditary information, the blueprint that gets passed from parent to child, but they didn't know what it looked like or how it worked. Then, in 1953, 2 researchers named James Watson and Francis Crick, building on the work of Rosalind Franklin and others, discovered the structure of DNA, a double helix, 2 spiraling strands twisted around each other like a ladder that's been wrung out. Each rung of that ladder is made of pairs of those 4 chemical letters: adenine, thymine, guanine, and cytosine. And the order of those letters is what makes all the difference. The sequence ATGCGA might code for one part of a protein, while GCTAAT codes for something entirely different. It's a bit like how the same 26 letters can create Shakespeare or a grocery list, depending on the order. But in DNA, the stakes are higher. The sequence determines whether you're a human, a butterfly, a blade of grass, or a bacterium. What's astonishing is that all life on Earth uses the same 4-letter code: a tree and a whale. And you, all of us reading from the same chemical alphabet, just with different sentences. The difference between you and a chimpanzee is less than 2% of your DNA. The difference between you and a butterfly is more, but still, at the most fundamental level, we're all variations on a theme, all chapters in the same book written in the same language. And that language has been copied, letter by letter, generation after generation, for billions of years. Every time a cell divides, it makes a copy of its DNA. Most of the time, it's perfect. Sometimes there are mistakes, mutations, and those mistakes are what drive evolution, creating the incredible diversity of life we see today. In a sense, you are a living library, carrying within you the accumulated edits and revisions of 4 billion years of life on Earth. And tonight, as you rest, billions of your cells are quietly reading that book, translating those letters into the proteins that keep you alive, keep your heart beating, keep your breath flowing in and out, gentle and steady. We learned that the universe is not only expanding, but accelerating outward, pushed by a mysterious force we call dark energy that makes up 68% of everything. Imagine you're watching fireworks explode in the night sky. The sparks fly outward in all directions, slowing down as gravity pulls them back toward the ground. That's what most scientists thought the universe was doing after the Big Bang. Expanding, yes, but slowing down over time, gravity gradually pulling everything back together, or at least slowing the expansion to a crawl. But in 1998, 2 teams of astronomers were studying distant supernovae, exploding stars that serve as cosmic mile markers. They expected to find that the universe's expansion was slowing. Instead, they found the opposite. The universe wasn't just expanding, it was speeding up. Galaxies were accelerating away from each other, as if something was pushing them apart. This discovery was so shocking, so contrary to everything predicted, that it won the Nobel Prize, because it meant there was something out there, some kind of energy that we hadn't accounted for. They called it dark energy, not because it's literally dark, but because we have no idea what it is. It doesn't emit light. It doesn't interact with matter in any way we can directly detect. But its effect is undeniable. It makes up about 68% of the universe, and it's pushing everything apart. Think about that for a moment. More than 2/3 of everything that exists is something we can't see, can't touch, can't even really understand. It's like discovering that most of a painting is invisible, or that most of a symphony is played in frequencies we can't hear. The universe is far stranger than we imagined. And what does it mean for the future? If dark energy continues to push galaxies apart at an accelerating rate, the universe will expand forever, faster and faster, until galaxies are so far apart that their light can never reach each other. In the distant future, trillions upon trillions of years from now, stars in other galaxies will wink out of view, one by one, until each galaxy is alone in the darkness, an island in an ever-expanding sea of nothing. But that's not tonight. Tonight the stars are still visible. The universe is still full of light and wonder. And maybe there's something oddly peaceful in knowing that even the cosmos doesn't have all the answers yet. Maybe the universe, like you, is still figuring things out. And maybe that's okay. Galileo turned his telescope to the sky in 1609 and discovered that Earth wasn't the center of everything. We orbit the sun, not the other way around. There's a certain comfort in thinking you're at the center of things. For thousands of years, that's exactly what humanity believed. The Earth was fixed, unmoving, and everything else, the sun, the moon, the planets, the stars, revolved around us. It made sense. After all, when you stand on the ground, you don't feel like you're moving. The sun appears to rise and set. The stars wheel overhead. It looked, for all the world, like we were the stage and everything else was the performance. Then came Galileo Galilei, an Italian astronomer with a curious mind and a newly improved telescope. In 1609, he turned that telescope toward the heavens and saw things no one had seen before. He saw mountains on the moon, proving it wasn't a perfect, smooth sphere. He saw 4 moons orbiting Jupiter, proving that not everything circles the Earth. And he saw phases of Venus, proving that Venus orbits the sun, not us. These observations supported an idea that had been around for a while, proposed by Nicolaus Copernicus decades earlier. The Earth isn't the center. We're just one planet among several, all orbiting the sun. It was called heliocentrism, sun at the center, and it was revolutionary and dangerous. The Catholic Church, which held that Earth was the center of God's creation, was not pleased. Galileo was tried, found guilty of heresy, and spent the rest of his life under house arrest. But the truth doesn't go away just because it's inconvenient. Other astronomers confirmed Galileo's observations. The heliocentric model explained the movements of the planets far better than the old Earth-centered view. Slowly, reluctantly, humanity had to accept a humbling fact. We are not the center of the universe. We're passengers on a rocky planet orbiting an ordinary star in the outer arm of an ordinary galaxy. And yet, there's a strange beauty in that too. Maybe being at the center would have been a burden. Maybe it's freeing to know that the universe doesn't revolve around us, that we're part of something much larger and older and grander than ourselves. Maybe it lets us relax a little, stop trying to be the center of everything, and just exist here and now on this small, lovely world spinning through space. And maybe that's enough. The discovery of penicillin in 1928 happened by accident when Alexander Fleming noticed mold-killing bacteria in a petri dish he forgot to clean. Some of the greatest discoveries in history happened because someone forgot to clean up. Alexander Fleming was a Scottish bacteriologist working in a cluttered London laboratory. One day in September 1928, he returned from a vacation to find that one of his petri dishes, which he'd been using to grow bacteria, had been contaminated with mold. Most scientists would have cursed their bad luck, tossed it in the trash, and started over. But Fleming noticed something strange. Around the mold, the bacteria had died. A clear ring surrounded the fuzzy growth where no bacteria could survive. The mold was producing something that killed the bacteria. He isolated the substance and named it penicillin, after the mold species Penicillium notatum. At the time, Fleming didn't fully realize what he'd stumbled upon. It took more than a decade, and the work of scientists like Howard Florey and Ernst Boris Chain during World War II, to develop penicillin into a practical medicine. But once they did, it changed everything. Before penicillin, a simple infection could kill you. A cut that got infected, a bout of pneumonia, a case of strep throat, these were potentially fatal. Soldiers died not just from their wounds, but from the infections that followed. Penicillin and the antibiotics that followed have saved hundreds of millions of lives. They turned infections from death sentences into minor inconveniences. Surgeries became safer. Diseases like tuberculosis and syphilis became treatable. It's hard to overstate how much this one accidental discovery reshaped human life. And it all came from a forgotten petri dish and a scientist who paid attention to something unexpected. There's a lesson in that, perhaps. Sometimes the most important things come not from careful planning, but from curiosity, from noticing the small anomalies, the things that don't fit. Sometimes the universe leaves clues in the mess, and all we have to do is stop and look. We discovered that atoms aren't the smallest things. They're made of even tinier particles like electrons, protons, and neutrons, which are themselves made of quarks. The word atom comes from the Greek word atomos, meaning indivisible. The ancient Greeks thought atoms were the smallest possible pieces of matter, the fundamental building blocks that couldn't be broken down any further. And for a long time, that idea held. Atoms were solid, indivisible little spheres, the Lego bricks of reality. But in the late 1800s and early 1900s, scientists began to discover that atoms weren't indivisible at all. They had structure. In 1897, J.J. Thomson discovered the electron, a tiny particle with a negative charge. It became clear that atoms contained these electrons somehow. Then Ernest Rutherford and others discovered the nucleus, a dense core at the center of the atom containing positively charged protons and neutral neutrons. The atom wasn't a solid sphere. It was mostly empty space, with electrons orbiting a tiny nucleus, like planets around a sun. But it didn't stop there. In the mid-20th century, physicists using massive particle accelerators discovered that even protons and neutrons have internal structure. They're made of smaller particles called quarks, held together by particles called gluons. And quarks, as far as we know, are fundamental. They don't seem to be made of anything smaller, though we can't be entirely sure. We've also found other fundamental particles, like neutrinos and muons, that don't fit neatly into the atom model, but are essential to understanding the universe. It's a bit like opening a Russian nesting doll and finding that each doll contains another, smaller one. And just when you think you've reached the smallest, you find there's one more, and maybe even one more after that. The deeper we look, the stranger it gets. At the quantum level, particles don't even behave like solid objects. They're more like waves, or probabilities, or little knots of energy vibrating in fields. It's almost as if reality itself is less like a machine made of parts and more like a symphony of vibrations, patterns of energy dancing through space. And all of this, these quarks and electrons, these fields and forces, all of it makes up you, your body, the device you're holding or lying near, the air around you, the bed beneath you. It's all made of these impossibly small, incredibly strange particles. You are, in a very real sense, a collection of quantum events happening in concert, a temporary pattern in the universe's endless dance. And somehow, miraculously, that pattern thinks and feels and wonders about its own existence. Isn't that something? Charles Darwin's theory of evolution by natural selection showed that all life on Earth shares common ancestors going back billions of years. There's a tree growing somewhere in your ancestry, not a family tree, a real tree. Maybe it's an oak or a pine or a fern, it doesn't really matter. Go back far enough, trace your lineage through millions of generations, and you'll find that you and that tree share a common ancestor. You're cousins, separated by about 1 billion years. That's what Charles Darwin's theory of evolution revealed. In 1859, after years of studying finches on the Galapagos Islands, fossils, and domestic animals, Darwin published On the Origin of Species. His central idea was natural selection. Living things produce more offspring than can survive. Those with traits better suited to their environment are more likely to survive and reproduce, passing those traits to the next generation. Over time, populations change, adapt, split into new species, and if you trace it all back, every living thing on Earth descended from a common ancestor that lived billions of years ago. It's a humbling thought. You're not separate from nature, you are nature. The same processes that shaped the wings of a butterfly shaped your hands. The same forces that produced the eyes of a deep-sea fish produced your eyes. Evolution doesn't have a plan or a goal. It's just what happens when life reproduces imperfectly in a changing world. Mistakes in copying DNA, mutations, occasionally produce something new. Usually, those mutations are neutral or harmful, but sometimes, by chance, they're beneficial and they stick around. Over millions of years, those small changes add up. A population of fish living in a shallow pool might gradually develop better vision. If some members of that population get cut off in a cave, their descendants might lose their eyes entirely over generations because vision is useless in total. Darkness and costs energy to maintain. Meanwhile, their cousins in the sunlight might develop bright colors to attract mates. Same starting point, different environments, different outcomes. And here you are, the product of nearly 4 billion years of this process. Every single one of your ancestors, stretching back to the first self-replicating molecule, successfully survived long enough to reproduce. Not one broke the chain. You are the result of an unbroken line of survival, adaptation, and reproduction that reaches back to the very beginning of life itself. That's your inheritance, not just from your parents or grandparents, but from every creature that ever lived. You carry traces of them in your DNA, in the structure of your cells, in the way your body develops from a single fertilized egg. Isaac Newton discovered that the same force pulling an apple to the ground also keeps the moon orbiting Earth and planets circling the sun. The story goes that Isaac Newton was sitting under an apple tree when a fruit fell and bonked him on the head, and suddenly he understood gravity. That's probably not how it happened. Newton himself never mentioned being hit. But there's a truth in the legend. Newton did wonder why apples fall down rather than up or sideways. And that simple question led to one of the most profound realizations in the history of science. Before Newton, people thought the heavens and the earth operated under different rules. Earthly objects fell because it was their nature to seek the ground. Celestial objects like the moon and planets moved in perfect circles, or so they thought, because that's what heavenly bodies did. It was all very neat and separate. Newton unified it. He realized that the same force pulling the apple down is also pulling on the moon. The moon doesn't fall to Earth because it's moving sideways fast enough that it keeps missing. It's in a constant state of falling around the Earth, held in orbit by gravity. The planets orbit the sun for the same reason. And this force, gravity, acts between any two objects with mass, anywhere in the universe. It's universal. He even worked out the math. Newton's law of universal gravitation states that every object attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. It's beautifully simple and staggeringly powerful. With this one equation, you can predict the orbits of planets, the tides of the ocean, the trajectory of a thrown ball, the motion of galaxies. For the first time, the heavens and the earth were subject to the same laws. There was no separation, no special rules for the divine realm above. The universe operated on principles that could be understood, calculated, predicted. It was a radical act of intellectual unification, and it worked. Newton's laws held up for more than 2 centuries, until Einstein came along and showed that gravity isn't exactly a force, but a curvature of space-time. Even then, Newton's equations are accurate enough for almost everything we encounter in daily life. There's something quietly astonishing about this. The force that keeps your feet on the ground, that makes a pen fall when you drop it, is the same force that holds the solar system together, that sculpts galaxies, that shape the universe itself. Everything is connected, governed by the same rules, playing the same game. And maybe there's comfort in that, in knowing that the universe, for all its vastness and complexity, is fundamentally comprehensible, orderly, woven from the same threads all the way down. We discovered that light behaves as both a wave and a particle at the same time, depending on how you observe it. Light is strange. For a long time, scientists argued about what it was. Isaac Newton thought light was made of particles, tiny bullets of light shooting through space. Others, like Christian Huygens, thought light was a wave, like ripples on a pond. For centuries, these two camps debated. Then, in the early 1800s, experiments seemed to settle it. Thomas Young's famous double-slit experiment showed that light creates interference patterns, bright and dark bands, just like waves do. When two waves overlap, they can reinforce each other, creating brightness, or cancel each other out, creating darkness. Light did this, so it must be a wave. Case closed. Except it wasn't. In the early 1900s, new experiments revealed something puzzling. When light hits certain metals, it knocks electrons loose. This is called the photoelectric effect, and the details didn't match wave theory. If light were a wave, the energy should depend on the wave's intensity, its brightness. But instead, it depended on the wave's frequency, its color. Blue light could knock electrons loose, but no amount of red light could, no matter how bright. It was as if light came in discrete packets of energy. Albert Einstein explained it by proposing that light is made of particles, now called photons, each carrying a specific amount of energy. The Nobel Prize he won wasn't for relativity. It was for this explanation of the photoelectric effect. Light was particles, after all. So which is it, wave or particle? The uncomfortable, beautiful answer is both. Light behaves like a wave in some experiments and like a particle in others. This isn't because we're confused or our instruments are faulty. It's because light genuinely has both natures. Quantum mechanics calls this wave-particle duality, and it applies not just to light, but to electrons and even whole atoms. Here's the truly weird part. Which nature light exhibits depends on how you observe it. If you set up an experiment to detect particles, you'll see particles. If you set up an experiment to detect waves, you'll see waves. It's as if reality itself is undecided until you look, as if the act of observation plays a role in what's real. This isn't mysticism, it's physics, confirmed in countless experiments. And it hints at something profound. The universe at its most fundamental level doesn't deal in certainties. It deals in probabilities, in potentials, in things that hover between states until something, an interaction, a measurement, forces a decision. Maybe that's unsettling, or maybe it's liberating. Maybe the universe is more fluid, more open than we ever imagined. Maybe reality is less like a clockwork machine and more like a conversation, shaped by its participants, never fully settled, always becoming. The Big Bang Theory revealed that the entire universe began as an infinitely hot, dense point about 13.8 billion years ago. Imagine everything, every star, every galaxy, every atom in your body, every thought you've ever had, compressed into a single point, smaller than the period at the end of this sentence. Not just the matter, but space itself and time, all wound up so tight that the concepts of where and when don't even apply. That's where the universe began, or at least that's as close as we can get to describing it. About 13.8 billion years ago, this point began to expand, not into empty space. There was no space yet. Space itself was expanding, unfurling, stretching out in all directions at once. In the first fractions of a second, the universe grew from smaller than an atom to the size of a grapefruit, then larger, cooling as it went. Particles formed, quarks and electrons and photons, all in a hot, dense soup. As it cooled further, quarks combined into protons and neutrons. After about 380,000 years, things had cooled enough for atoms to form, and light could finally travel freely. That light, stretched and cooled by billions of years of expansion, is still around today as the cosmic microwave background radiation, a faint glow filling all of space, the oldest light in the universe. This is the Big Bang Theory, and it's our best explanation for how the universe began. It's not an explosion in space, it's the expansion of space itself. Every point in the universe is expanding away from every other point, like dots drawn on a balloon that's being inflated. The farther apart two points are, the faster they're moving apart. Galaxies billions of light years away are receding from us faster than the speed of light, not because they're moving through space that fast, but because the space between us is growing. It sounds wild, almost unbelievable, but the evidence is overwhelming. The universe is expanding. We can see it in the way distant galaxies are moving away from us. The cosmic microwave background matches predictions perfectly. The proportions of hydrogen and helium in the universe match what the Big Bang Theory predicts. Everything points to a universe that had a beginning, a moment when time itself started ticking. And that raises questions, doesn't it? What came before? Was there a before? What caused the Big Bang? We don't know. Maybe the question doesn't even make sense. Asking what came before time is like asking what's north of the North Pole. Or maybe there are answers we haven't found yet, deeper layers of reality waiting to be uncovered. For now, though, here we are, 13.8 billion years downstream from that first moment, riding the expansion of space-time itself. You are, in a very real sense, a piece of the universe contemplating its own origins. And tonight, as you settle into rest, the universe continues to expand around you. Galaxies drifting apart, space stretching, time flowing onward into an open and uncertain future. And somehow, in the middle of all that vastness, here you are, warm and breathing and aware. And that, perhaps, is the greatest mystery of all. We discovered radioactivity when Henri Becquerel left uranium salts on a photographic plate and found they exposed the film without any light. Sometimes the most important discoveries happen when you're not even looking. Henri Becquerel was a French physicist studying phosphorescence in 1896. The way some materials glow after being exposed to light. He was working with uranium salts, and his plan was to leave them in sunlight, then place them on wrapped photographic plates to see if they'd expose the film. But Paris had cloudy weather that week. Becquerel tucked his uranium samples and photographic plates into a drawer to wait for better conditions. Days passed. Finally, perhaps out of curiosity or impatience, he developed the plates anyway, expecting to find nothing or at most a faint image. Instead, he found a strong, clear exposure. The uranium had affected the photographic plate without any exposure to light at all. Something was coming out of the uranium itself, some kind of invisible ray that could penetrate paper and expose film. Becquerel had discovered radioactivity, though he didn't call it that yet. The term came later, coined by Marie Curie, who would go on to isolate radioactive elements like polonium and radium, and would win Nobel Prizes for her work. What Becquerel had stumbled upon was the fact that some atomic nuclei are unstable. They spontaneously break apart, releasing energy in the form of particles and radiation. This process happens naturally in elements like uranium, radium, and many others. It's happening all around you, all the time, in the rocks beneath your feet, in the walls of your home, even in your own body. Bananas contain trace amounts of radioactive potassium. You are, very slightly, radioactive yourself. Radioactivity opened up entirely new fields of science. It gave us insights into the structure of atoms, showed us that atoms could transform from one element to another, and revealed that the Earth was far older than anyone had imagined. By measuring the decay of radioactive elements in rocks, scientists could determine ages in the millions and billions of years, pushing Earth's age from thousands of years, as many once believed, to its true age of 4.54 billion years. Radioactivity also gave us tools. Medical imaging techniques like PET scans, cancer treatments using radiation therapy, and methods for dating ancient artifacts and fossils. But it also revealed new dangers. The very properties that make radioactive materials useful also make them hazardous. Marie Curie herself died from a plastic anemia, likely caused by prolonged exposure to radiation. The atomic bombs that ended World War II released radioactive fallout that would linger for generations. It's a reminder, perhaps, that every discovery is a door that swings both ways. Knowledge is neutral. It's what we do with it that matters. And sometimes, the universe reveals its secrets, not when we're actively seeking them, but when we're patient enough to look at what's been sitting in the drawer all along, quiet and persistent, waiting to be noticed. The periodic table organized by Dmitri Mendeleev in 1869 didn't just catalog elements, it predicted elements that hadn't been discovered yet. Imagine trying to organize a library when you only have half the books, and you're not sure which half you're missing. That was the challenge facing chemists in the mid-1800s. They knew about dozens of elements, substances that couldn't be broken down into simpler components, but there seemed to be no rhyme or reason to their properties. Some were metals, some gases, some reactive, some inert. It was a chaotic jumble. Then came Dmitri Mendeleev, a Russian chemist with a gift for seeing patterns. In 1869, he arranged the known elements by atomic weight and noticed something remarkable. Properties repeated at regular intervals. If you lined them up just right, elements with similar characteristics fell into columns. Metals here, gases there, reactive elements in this group, inert ones in that group. It was like finding a hidden melody in noise. But Mendeleev did something even more audacious. When the pattern didn't quite fit, when there was a gap where an element should be but wasn't known, he left a blank space and predicted what that missing element would be like. He said there should be an element between calcium and titanium with specific properties. Its atomic weight, its density, how it would react with other elements. He called it Eka boron, Eka meaning one in Sanskrit, indicating it was one place below boron in his table. And then years later, scientists discovered those missing elements. Gallium, scandium, germanium. They fit perfectly into Mendeleev's gaps, with properties almost exactly as he'd predicted. It was as if he'd found a map of reality itself, a blueprint showing not just what existed, but what must exist to make the pattern complete. The periodic table has been refined since Mendeleev's time. We now organize elements by atomic number, the number of protons, rather than atomic weight. And we've added entire rows for elements he couldn't have known about. But the fundamental insight remains. The elements aren't random. They follow a pattern, a structure, because they're built from the same basic parts, protons, neutrons, and electrons, just in different quantities and arrangements. There's something deeply satisfying about the periodic table. It's proof that beneath the complexity of the world, there are simple, elegant rules. The same element that makes up a diamond is what's in your pencil lead. Both are carbon, just arranged differently. The sodium in your table salt is a metal so reactive it bursts into flame when it touches water, yet combined with chlorine, a toxic gas, it becomes something you sprinkle on your food. Chemistry is just atoms finding new partners, dancing into new configurations, creating the vast diversity of matter from a palette of about 100 elements. And every single one of those elements, heavier than hydrogen, was forged in the heart of a star or in the explosion of a supernova. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was cooked up in stellar furnaces billions of years ago and scattered into space, eventually coalescing into the planet you're lying on and the body you inhabit. You are, quite literally, made of stardust, organized according to the periodic table's elegant logic. And tonight, as you rest, those elements continue their ancient dance, building and breaking bonds, keeping you alive, keeping you here. We discovered that continental drift is real. The ground beneath your feet is riding on massive tectonic plates that float on molten rock. The ground feels solid, doesn't it? Stable, permanent, unchanging. The continents have always been where they are, right? Mountains have always stood in their places. Oceans have always filled their basins. The earth, whatever else might change, surely stays put, except it doesn't. In 1912, a German meteorologist named Alfred Wegener proposed something radical: the continents move. He noticed that the coastlines of South America and Africa looked like puzzle pieces that could fit together. He found similar fossils of ancient plants and animals on continents now separated by thousands of miles of ocean. He found evidence of ancient glaciers in tropical regions and tropical plants in polar areas. His explanation: the continents were once joined together in a single supercontinent. He called it Pangaea. And over millions of years, they drifted apart. Most scientists dismissed the idea. It seemed absurd. How could entire continents move? What force could possibly push them around? Wegener couldn't answer that, and without a mechanism, his theory was mostly ignored. He died in 1930 on an expedition to Greenland, his ideas largely rejected. But evidence kept accumulating. In the 1960s, scientists mapping the ocean floor discovered something extraordinary: underwater mountain ranges, called mid-ocean ridges, where new crust was constantly being formed. Molten rock from deep within the earth was rising up, cooling, and spreading outward, pushing the continents along like cargo on conveyor belts. Other boundaries, old crust was sinking back down into the Earth's interior, recycled into the mantle. The continents weren't plowing through the ocean floor. They were riding on massive plates of crust that floated on the semi-molten rock beneath. This was plate tectonics, and it explained everything. Earthquakes happen where plates grind against each other. Volcanoes form where one plate dives beneath another, melting and rising as magma. Mountain ranges are built where plates collide and crumple upward. The Atlantic Ocean is slowly growing wider, about an inch a year, as new crust forms at the mid-Atlantic ridge. Meanwhile, the Pacific is shrinking as its edges are consumed in subduction zones. The ground beneath you is moving right now. You can't feel it. It's far too slow, about as fast as your fingernails grow. But over millions of years, it adds up. 200 million years ago, all the continents were clustered together. 50 million years from now, Africa will have collided with Europe, closing the Mediterranean Sea. Australia will bump into Asia. The Earth you're lying on is temporary, a snapshot in an endless process of assembly and dispersal. And it's not just Earth. Venus has volcanism but no plate tectonics. Its crust is a single stagnant lid. Mars once had plate tectonics, maybe, but its interior cooled and the process stopped. Plate tectonics might be rare, special, maybe even essential for life. It recycles nutrients, regulates climate, creates diverse environments. Without it, Earth might be a lifeless desert like Mars, or a hellish hothouse like Venus. So as you lie still tonight, know that you're not still at all. You're riding a raft of rock through a slow-motion ocean of molten earth, drifting at the stately pace of geological time, part of a cycle that's been reshaping the planet for billions of years and will continue long after humanity is gone. The ground is solid enough to hold you, but fluid enough to move mountains. And maybe that's a metaphor for something. Maybe solidity and change aren't opposites after all. Maybe everything is both, always, depending on the time scale you're watching. The discovery of the cosmic microwave background radiation in 1964 gave us a baby picture of the universe just 380,000 years after the Big Bang. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey, trying to eliminate background noise from a sensitive antenna. They were preparing to observe radio signals from space. But no matter what they did, they couldn't get rid of a persistent hiss. It was faint, uniform, coming from every direction in the sky equally. They even wondered if pigeon droppings inside the antenna might be the cause. They cleaned it out meticulously, but the noise remained. What they'd stumbled upon wasn't noise at all. It was the afterglow of the Big Bang itself. When the universe was very young, about 380,000 years after its birth, it was a hot, dense fog of ionized particles and photons. Light couldn't travel far before being absorbed and re-emitted. But as the universe expanded and cooled, protons and electrons combined to form neutral hydrogen atoms, and suddenly light could travel freely. That moment is called recombination, and the light released then has been traveling through space ever since, stretched and cooled by the expansion of the universe from visible light to microwaves. That's what Penzias and Wilson detected, the cosmic microwave background, or CMB, a faint glow at a temperature of about 2.7 degrees above absolute zero, filling all of space. It's the oldest light in the universe, a snapshot of what things looked like when the universe was just a baby. They won the Nobel Prize for their discovery, an accidental find that turned out to be one of the most important confirmations of the Big Bang theory. Since then, we've mapped the CMB in exquisite detail with satellites like COBE, WMAP, and Planck. And it's not perfectly uniform. There are tiny fluctuations, regions slightly warmer or cooler by a few millionths of a degree. Those tiny ripples were the seeds of everything, the slight overdensities where gravity would pull matter together to form the first stars, the first galaxies, eventually planets and people. You can trace your existence back to those tiny temperature variations in the infant universe. Looking at the CMB is like looking at a sonogram of the cosmos. We're seeing the universe before stars existed, before galaxies formed, when everything was simpler and the future was still wide open. It's humbling and awe-inspiring to think that we can observe something so ancient, so fundamental. That faint microwave hiss detected by accident is a message from the dawn of time, still echoing through space, whispering the story of where everything came from. And every moment as you go about your life, that ancient light is passing through you. Photons that began their journey before the Earth existed, before the sun ignited, before our galaxy took shape. They're streaming through your body right now, silent and invisible, carrying information about the universe's earliest moments. You're immersed in the glow of creation itself, a gentle radiation bath that's been traveling for 13.8 billion years just to arrive here. Now, with you. We discovered that all matter is made of atoms around 1808, when John Dalton proposed that elements consist of indivisible particles. For much of history, people wondered what would happen if you kept cutting something in half. Take a piece of gold, cut it in half, cut it again and again. Could you keep going forever, or would you eventually reach a point where you couldn't cut any more, where you'd arrived at the smallest possible piece of gold? The ancient Greeks debated this. Some, like Democritus, argued for atomism, the idea that matter is made of tiny, indivisible particles called atoms, from atomos, meaning uncuttable. Others, like Aristotle, disagreed, believing matter was continuous and infinitely divisible. Aristotle's view dominated for centuries, partly because he was Aristotle and partly because there was no way to test the idea. Atoms, if they existed, were far too small to see. Then in the early 1800s, an English chemist named John Dalton began thinking carefully about how elements combine to form compounds. He noticed that when elements react, they do so in specific whole number ratios. Water, for instance, is always made of hydrogen and oxygen in a 2.1 ratio by number of atoms. Carbon dioxide is always carbon and oxygen in a 1.2 ratio. This made sense if matter was made of discrete particles that combined in specific ways, but not if matter was infinitely divisible. Dalton proposed atomic theory. All matter is made of atoms, indivisible particles that define each element. All atoms of a given element are identical. Different elements have different kinds of atoms. Compounds are formed when atoms of different elements combine in fixed ratios. Chemical reactions involve rearranging atoms, but the atoms themselves don't change. It was a beautiful, simple idea, and it explained so much. Why elements have distinct properties, why compounds have fixed compositions, why mass is conserved in chemical reactions. Atoms are just rearranging, not being created or destroyed. Dalton's theory wasn't perfect. We now know atoms are divisible and that atoms of the same element can vary slightly, isotopes. But the core insight was revolutionary. Matter has a granular structure. There is a smallest piece, and that idea, once accepted, changed everything. It gave chemists a framework for understanding reactions. It led to the discovery of new elements. It allowed scientists to calculate atomic weights and eventually to determine the structure of molecules. The periodic table makes sense because elements are different types of atoms with different numbers of protons. Today we know atoms are mostly empty space, a tiny nucleus surrounded by a cloud of electrons. We know they can be split in nuclear reactions, releasing enormous energy. We know they behave in strange, quantum ways, existing in superpositions and entanglements. But Dalton's fundamental insight remains. Matter is made of discrete units, not a continuous blob. The universe is quantized, granular, made of distinct pieces that combine and recombine in endless variety. And every object around you, the pillow under your head, the air in your lungs, the screen you're reading this on, is a temporary assembly of atoms, borrowed from the universe and destined to be returned, recycled into new forms. Atoms from Caesar's dying breath are in the air you're breathing now. Atoms from ancient oceans are in your tears. You're not a separate thing made of separate stuff. You're a pattern of atoms that the universe is trying out for a while. And when you're done, those atoms will go on to form other patterns, other lives, other stories. Nothing is permanent, but nothing is truly lost either. Everything just changes form, endlessly, beautifully, according to rules we're still learning to read. The Higgs boson, discovered in 2012, explains why particles have mass. It's a field that pervades all of space. Imagine walking through an empty room. Easy, right? Now imagine walking through the same room, but it's filled waist deep with water. Harder. The water resists your movement, slows you down. You have to push through it. Now imagine the room is filled with thick honey. Even harder. The honey clings to you, drags at you, makes every step an effort. That's a bit like what the Higgs field does, except instead of a room, it's all of space, and instead of slowing you down, it gives particles mass. In the 1960s, physicists had a problem. According to their best theories, all fundamental particles should be massless, zipping around at the speed of light. But clearly, many particles, electrons, quarks, W and Z bosons, have mass. They don't move at light speed. Something was giving them mass, but what? Peter Higgs and others proposed a solution. There's a field permeating all of space, now called the Higgs field. Particles interact with this field as they move through it, and that interaction gives them mass. Particles that interact strongly with the Higgs field, like the top quark, have a lot of mass. Particles that barely interact, like the electron, have little mass. And particles that don't interact at all, like the photon, remain massless and travel at light speed. It's not that the Higgs field slows particles down in the usual sense. It's more that it makes them resistant to acceleration, which is what mass is. The field gives them inertia. Without the Higgs field, electrons would be massless and couldn't be captured by atomic nuclei. Atoms wouldn't form. There would be no chemistry, no molecules, no life. The Higgs field is, in a very real sense, what makes the material world possible. But for decades, this was just a theory. The Higgs field, if it existed, should produce a corresponding particle, the Higgs boson. And finding it required building the largest, most complex machine ever constructed, the Large Hadron Collider at CERN in Switzerland, a ring 17 miles around where protons are accelerated to nearly the speed of light and smashed together. In 2012, after years of operation and analyzing trillions of collisions, physicists announced they'd found it. The Higgs boson exists. The field is real. The mechanism works. Peter Higgs won the Nobel Prize, almost 50 years after predicting the particle's existence. It's a strange thing to think about. Right now, as you lie there, you're immersed in the Higgs field. It's passing through you, interacting with the particles that make up your body, giving them the mass that allows them to stick together, allows you to exist as a coherent material being. Without it, you wouldn't be matter at all. You'd be radiation, pure energy dispersing at the speed of light. And the universe is filled with these invisible fields: the electromagnetic field, the electron field, the quark field, and more. Reality isn't made of particles, exactly. It's made of fields, and particles are just excitations in those fields, little ripples, temporary disturbances. You're not a collection of objects. You're a pattern of vibrations in quantum fields that have been humming since the Big Bang. And the Higgs field, that omnipresent invisible honey, is what lets those vibrations slow down enough to dance together, to form the atoms and molecules and cells and thoughts that make up everything you know. We discovered that energy and mass are interchangeable, captured in Einstein's famous equation ERA-mc2. There's an equation so famous that even people who've never studied physics know it. EA-mc2. Energy equals mass times the speed of light squared. It's elegant, simple, just 5 symbols. And it's one of the most profound statements about the nature of reality ever written. What it says is this: energy and mass are not separate things. They're the same thing in different forms. Mass is just concentrated energy. Energy is mass that's been set free. And the conversion factor, C2, the speed of light squared, is enormous. The speed of light is about 300 million meters per second, so when you square it, you get 90 quadrillion. That means a tiny amount of mass contains a staggering amount of energy. To give you a sense of scale, if you could convert just 1 gram of matter, about the mass of a paperclip, entirely into energy, it would release about 90 trillion joules. That's roughly the energy of 21,000 tons of TNT, the explosive force of the bomb dropped on Hiroshima. All that energy, locked up in something smaller than your fingertip. Of course, completely converting mass to energy is extraordinarily difficult. But we can do it in small ways. In nuclear reactions, whether in the sun or in a nuclear power plant, or in a bomb, a tiny fraction of mass is converted to energy when atomic nuclei split or fuse. The mass of the products is slightly less than the mass of the reactants, and that missing mass has been transformed into energy: heat, light, radiation. This is how the sun shines. Every second, the sun fuses about 600 million tons of hydrogen into helium. In the process, about 4 million tons of mass are converted into pure energy, radiated out into space as light and heat. That lost mass is what makes the sun shine, what warms the earth, what makes life possible. You are powered ultimately by the sun's conversion of mass into energy, sustained by Einstein's equation playing out in the core of a star 93 million miles away. Einstein derived this equation from special relativity, his theory of space and time. It emerged naturally from the math, an unexpected consequence of the fact that the speed of light is constant for all observers. He published it in 1905 in a short 3-page paper as a sort of addendum to his relativity paper. He probably didn't realize how revolutionary it would be. ERA-mc2 changed our understanding of the universe. It told us that mass and energy are conserved together, not separately. It explained where stars get their energy. It made nuclear power and nuclear weapons possible. It revealed that matter is just another form of energy, that the seemingly solid world around you is, at a fundamental level, congealed light, frozen energy shaped into atoms and molecules and living things. And it means that nothing is truly solid. Everything is energy, temporarily locked into patterns we call matter, held together by forces, stable for a while, but ultimately impermanent. The atoms in your body were once energy in the Big Bang, condensed into matter as the universe cooled, forged into heavier elements in dying stars, scattered and reformed into planets and people. And someday, in the unimaginably distant future, they might become energy again, released as the universe expands and cools toward heat death. But for now, here, tonight, that energy is you, thinking, feeling, breathing, resting, and that's beautiful. The electron was discovered in 1897 by J.J. Thomson, revealing that atoms have an internal structure with negatively charged particles. For a long time, atoms were thought to be indivisible. the name itself means uncuttable. But in the late 1800s, scientists studying electricity began to suspect atoms might have parts. When they passed electric current through gases at low pressure, they saw glowing beams, cathode rays, streaming from one electrode to another. But what were these rays made of? J.J. Thomson, working at Cambridge University, set out to find out. In 1897, he conducted a series of experiments with cathode rays. He showed that the rays could be bent by electric and magnetic fields, which meant they were made of charged particles. He measured how much they bent and calculated the ratio of the particle's charge to its mass. And he discovered something astonishing. These particles were nearly 2,000 times lighter than a hydrogen atom, the lightest known atom. These particles, later called electrons, were pieces of atoms. Atoms weren't indivisible after all. They had internal structure, and these electrons were negatively charged, which meant atoms must also contain something positive to balance them out. Thomson proposed the plum pudding model. Atoms were spheres of positive charge with electrons embedded in them like raisins in a pudding. That model didn't last long. Ernest Rutherford's experiments in 1911 showed that most of an atom is empty space, with a tiny, dense, positively charged nucleus at the center and electrons orbiting around it. But Thomson's discovery of the electron was the crack that broke open the atom, the first glimpse into the hidden architecture of matter. Electrons are everywhere. They're responsible for electricity. An electric current is just electrons moving through a conductor. They're responsible for chemistry. Chemical bonds form when atoms share or transfer electrons. They're responsible for light. Electrons jumping between energy levels in atoms emit or absorb photons. Magnetism, conductivity, color, the structure of molecules, all of it comes down to how electrons behave. And electrons are strange. They're fundamental particles as far as we know, with no internal structure. They have both wave and particle properties. They can exist in superpositions, in multiple states at once until observed. They obey the Pauli exclusion principle, which says no two electrons can be in the same quantum state, and that's why matter is solid, why you don't fall through your chair, why atoms don't collapse. It's electrons pushing back against each other through quantum rules that give matter its structure and stability. Your body contains about 1028 electrons, 10,000 trillion. They're flowing through your neurons right now, carrying signals that create your thoughts. They're holding your molecules together, defining your shape, your substance, and they're identical, every single one. An electron in your body is indistinguishable from an electron in a distant star. They're perfect copies, timeless and universal. The same today as they were at the dawn of the universe. There's something quietly profound in that. At the most fundamental level, we're all made of the same stuff. Not just the same types of particles, but literally interchangeable, identical pieces of reality. The boundaries between you and the world are arbitrary, temporary. You're not separate from the cosmos. You're a brief arrangement of its most basic components. And when you're gone, those components will remain unchanged and unchanging, ready to build new patterns, new worlds, new minds, to wonder about it all. We discovered that viruses exist and cause diseases, changing medicine forever and explaining epidemics that had mystified humanity for millennia. For most of human history, disease was a mystery wrapped in fear. Plagues would sweep through cities, killing thousands, and no one knew why. Some blamed bad air, others divine punishment, others the alignment of planets. People tried everything: bloodletting, herbs, prayers, but mostly they just suffered and died, helpless against invisible enemies. Then, in the late 1800s, scientists like Louis Pasteur and Robert Koch developed germ theory, the revolutionary idea that many diseases are caused by microscopic organisms, bacteria. Suddenly, epidemics made sense. Cholera came from contaminated water. Tuberculosis was spread through the air. You could see these bacteria under a microscope, culture them in labs, study them. But some diseases didn't fit. They passed through filters fine enough to catch all known bacteria. They couldn't be seen under ordinary microscopes. They couldn't be grown in the nutrient broths that bacteria thrived in. Whatever caused these diseases was smaller, stranger than bacteria. In 1892, Russian scientist Dmitry Ivanovsky was studying tobacco mosaic disease, which stunted tobacco plants. He filtered sap from infected plants through the fine porcelain filter that should have removed all bacteria, but the filtered sap still caused disease. Something was passing through. A few years later, Dutch scientist Martinus Beijerinck repeated the experiment and concluded that the infectious agent was not a bacterium, but something fundamentally different, a contagious living fluid. He called it a virus, from the Latin word for poison. Over the next decades, scientists discovered that viruses were behind many diseases: influenza, polio, rabies, smallpox, the common cold. But it wasn't until the 1930s, with the invention of the electron microscope, that anyone actually saw a virus. They were astonishingly small, some only 20 nanometers across, hundreds of times smaller than bacteria. And they were strange. Viruses aren't quite alive. They can't reproduce on their own, can't metabolize, can't maintain homeostasis. They're just genetic material, DNA or RNA, wrapped in a protein coat. They hijack living cells, injecting their genetic code and forcing the cell to make copies of the virus. The cell becomes a virus factory, churning out new viruses until it bursts, releasing them to infect more cells. It's simple, brutal, effective. Viruses have shaped human history in ways we're only beginning to fully appreciate. The Black Death, which killed a third of Europe's population, was likely caused by bacteria, but viruses have caused their own catastrophes. The 1918 flu pandemic killed 50 to 100 million people worldwide. Smallpox killed hundreds of millions over centuries before being eradicated through vaccination, one of humanity's greatest achievements. HIV has killed more than 35 million people since the 1980s, though modern treatments have turned it from a death sentence to a manageable chronic condition. And then, of course, more recently, the world was reshaped by SARS-CoV-2, the virus behind COVID-19. It reminded us that even with all our technology, we're still vulnerable to these tiny, non-living packages of genetic code that can spread across the globe in weeks. But viruses aren't just enemies. They've played a crucial role in evolution. Much of our genome, perhaps as much as 8%, consists of ancient viral DNA that got incorporated into our ancestors' genomes millions of years ago. Some of those viral genes now serve useful functions. Viruses may have been key players in the early evolution of life, shuffling genetic material between organisms, driving innovation and diversity. The discovery of X-rays in 1895 let us see inside living bodies for the first time without surgery. Wilhelm Röntgen was experimenting with cathode rays in his laboratory in Würzburg, Germany, in November 1895. He was working with a vacuum tube covered in black cardboard to block the light, studying the glow of the cathode rays. But across the room, a screen coated with barium platinocyanide began to glow. Even though the tube was completely covered, something invisible was escaping the tube and making the screen fluoresce. Röntgen was puzzled and intrigued. He spent weeks investigating this mysterious radiation. He found it could pass through wood, paper, and even human flesh, but was partially blocked by denser materials like bone and metal. He took a photographic plate, placed his wife's hand over it, and exposed it to the rays. When he developed the plate, there was an image of the bones in her hand, along with the ring on her finger, floating like ghosts against the shadow of her flesh. It was the first X-ray image ever taken, and it changed medicine forever. Röntgen called them X-rays because he didn't know what they were. X for unknown. We now know they're a form of electromagnetic radiation, like light or radio waves, but with much higher energy and shorter wavelengths. That high energy lets them pass through soft tissue, but get absorbed by denser materials like bones, which is why bones show up clearly on X-ray images. The medical applications were immediately obvious. For the first time, doctors could see inside a living patient without cutting them open. Broken bones could be diagnosed and set more accurately. Bullets and foreign objects could be located. Lung diseases could be detected. Surgery became safer because surgeons knew exactly where to cut. Within a year of Röntgen's discovery, X-ray machines were being used in hospitals around the world. Röntgen won the first Nobel Prize in Physics in 1901 for his discovery. He refused to patent the X-ray or the equipment used to produce it, believing that scientific discoveries should benefit everyone. His discovery has since saved countless lives. Of course, we've learned that X-rays come with risks. They're ionizing radiation, energetic enough to knock electrons out of atoms, which can damage DNA and increase cancer risk. Early radiologists, not knowing the dangers, suffered terrible injuries from prolonged exposure. Today, X-ray machines are carefully calibrated to use the minimum dose necessary, and the benefits for diagnosing injuries and diseases far outweigh the small risks. And X-rays have given us so much more than medical imaging. They've let us study the structure of crystals, leading to discoveries about DNA's double helix and the atomic structure of proteins. X-ray astronomy reveals the universe's most violent phenomena: black holes, neutron stars, supernovae. We've learned to see with light our eyes can't perceive, expanding our vision far beyond the narrow sliver of the electromagnetic spectrum we evolved to detect. There's a metaphor in there, maybe. Sometimes the most important things are invisible. Sometimes you need to look at the world in a different way, through X-rays or radio waves or infrared, to see what's really there. The visible world is just one layer of reality, one frequency band in an infinite symphony. And maybe the same is true for ideas, for understanding, for wisdom. Sometimes you need to shift your perspective, look from a different angle, shine a different kind of light, to see the truth that was hidden all along, waiting patiently to be discovered. We discovered that the speed of light is constant for all observers, no matter how fast they're moving, about 186,282 miles per second. Imagine you're on a train moving at 60 miles per hour, and you throw a ball forward at 20 miles per hour. To someone standing on the platform watching you pass, the ball appears to be moving at 80 miles per hour. Your speed plus the ball's speed. That's how velocities add up in our everyday experience. It's intuitive, obvious, the way the world works, except when it comes to light. In the late 1800s, physicists believed light traveled through a medium called the luminiferous ether, an invisible substance that filled all of space. If that were true, then someone moving through the ether should measure different speeds of light depending on their direction of motion. Faster when moving toward the light source, slower when moving away, just like that ball on the train. In 1887, Albert Michelson and Edward Morley set up an incredibly precise experiment to detect Earth's motion through this ether. They measured the speed of light in perpendicular directions, expecting to find a difference as Earth moved through the ether. But they found nothing, no difference at all. Light traveled at the same speed in every direction, regardless of Earth's motion. It was baffling. Scientists tried to explain it away. Maybe Earth dragged the ether along with it. Maybe the apparatus contracted in the direction of motion just enough to hide the effect. But the simplest explanation, the one that turned out to be right, was also the most radical. There is no ether. Light doesn't need a medium, and its speed is constant for all observers, regardless of how they're moving. This was one of the key insights that led Einstein to develop special relativity in 1905. The speed of light, about 186,282 miles per second, or 299,792,458 meters per second, is the same for everyone, everywhere, always. If you're standing still and measure a beam of light, you'll get that speed. If you're in a spaceship traveling at 99% the speed of light and measure a beam of light passing you, you'll still get the same speed. The light doesn't appear to be moving just 1% faster than you. It appears to be moving at full light speed. This seems impossible. It violates our intuition, but it's true, confirmed by countless experiments, and it has profound consequences. If the speed of light is constant, then something else has to give. And what gives is space and time themselves. They're not fixed and absolute. They're flexible, relative, different for different observers. Time slows down for objects moving at high speeds. Distances contract. Simultaneity, the idea that two events happen at the same time, becomes relative. What's simultaneous for you might not be for someone moving at a different speed. The speed of light becomes a cosmic speed limit. Nothing with mass can reach it, much less exceed it. As you accelerate closer to light speed, you get heavier, from the perspective of a stationary observer, requiring more and more energy to go faster. To actually reach light speed would require infinite energy, which is impossible. Only massless particles, like photons, can travel at light speed, and they do so effortlessly, eternally, never experiencing time at all from their own perspective. It's a strange universe we live in, one where the rules change depending on how fast you're going, where time and space bend and stretch to preserve the constancy of light. But in a way, it's elegant. Light speed isn't just a speed. It's woven into the fabric of space-time itself, a fundamental constant that governs causality, the flow of information, the structure of reality. It's the universe's way of keeping things consistent, of preventing paradoxes, of maintaining order in a relativistic cosmos. Quantum entanglement shows that two particles can be connected in such a way that measuring one instantly affects the other, even across the universe. Imagine you have a pair of magic coins. You put one in a box and send it to your friend on the other side of the world. You keep the other. When you flip your coin and it comes up heads, your friend's coin, flipped at the exact same moment, always comes up tails. Every single time. Instantly, regardless of the distance. Not because of any signal passing between the coins, but because they're connected in some deeper, fundamental way. That's a rough analogy for quantum entanglement, one of the strangest phenomena in physics. When two particles interact in certain ways, they can become entangled. Their quantum states become linked, so that measuring a property of one particle, like its spin or polarization, instantly determines the corresponding property of the other, no matter how far apart they are. If one particle is measured and found to be spinning up, the other will be spinning down. It's not that one particle sends a signal to the other. It's that they're not really separate particles anymore, not in the way we usually think about separate things. They're parts of a single quantum system described by one wave function. Albert Einstein hated this idea. He called it spooky action at a distance, and was convinced it meant quantum mechanics was incomplete, that there must be hidden variables we weren't accounting for. In 1935, he and two colleagues, Boris Podolsky and Nathan Rosen, published a thought experiment, now called the EPR paradox, arguing that entanglement was absurd and that quantum mechanics must be missing something. But Einstein was wrong. Starting in the 1960s, physicist John Bell developed a theorem showing how to test whether hidden variables could explain quantum correlations. And when experiments were finally performed in the 1970s and 80s, they confirmed that quantum entanglement is real. The correlations between entangled particles are stronger than any theory of local hidden variables can explain. The particles really are connected in a way that transcends space. This doesn't mean information travels faster than light. You can't use entanglement to send messages. When you measure one particle, you see a random result. It's only when you compare your results with measurements on the other particle that you see the correlation. But the fact remains, measuring one particle affects the state of its partner instantly, even if that partner is on the other side of the universe. Entanglement is now being harnessed for quantum technologies. Quantum computers use entangled qubits to perform calculations impossible for classical computers. Quantum cryptography uses entanglement to create unbreakable codes. Any attempt to intercept the message would disturb the entangled particles and reveal the eavesdropping. Quantum teleportation, not like Star Trek but still remarkable, uses entanglement to transfer quantum states from one particle to another at a distance. But beyond the applications, entanglement challenges our intuitions about reality. It suggests that the universe is not made of separate, independent pieces, but is fundamentally interconnected. Particles that have interacted remain linked, woven into the same quantum tapestry. In a sense, everything that has ever interacted is still entangled, to some tiny degree. The universe is not a collection of isolated objects. It's a unified whole, a seamless web of correlations extending across space and time. Maybe that's comforting. Maybe it means we're never truly alone, never truly separate. The boundaries between things, between you and the world, are not as solid as they seem. At the quantum level, everything is connected, entangled in the dance of existence. And maybe, just maybe, that connectedness extends beyond particles and fields. Maybe we're all part of something larger, harder to define, impossible to prove, but beautiful to contemplate as you drift towards sleep, feeling the invisible threads that tie you to the cosmos humming quietly in the darkness. We discovered that cells are the basic units of life, and all living things are made of one or more cells. There's a hidden world inside you, a bustling city of trillions of tiny rooms, each one alive in its own way. You can't see them with your naked eye, but they're there, cells, the fundamental units of life, working together to keep you breathing, thinking, moving, being. For most of history, no one knew cells existed. Life seemed to be made of flesh, blood, bone, continuous substances, not discrete units. Then, in the 1660s, Robert Hooke looked at a thin slice of cork under a microscope and saw a honeycomb pattern of small compartments. He called them cells because they reminded him of the small rooms monks lived in. What he was actually seeing were the dead cell walls of plant tissue, but the name stuck. Over the next 2 centuries, better microscopes revealed that all living things are made of cells. Animals, plants, fungi, bacteria, all built from these tiny, membrane-bound units. In the 1830s, Matthias Schleiden and Theodor Schwann formalized cell theory. All organisms are composed of one or more cells. The cell is the basic unit of life, and all cells come from pre-existing cells. It was a unifying principle, like the periodic table or evolution. Life, in all its diversity, is built from the same basic building block. A bacterium is a single cell. You are about 37 trillion cells, working in exquisite coordination. Each cell is a self-contained world, with a membrane defining its boundary, a nucleus, in most cells, containing genetic instructions, and organelles carrying out specialized functions. Mitochondria producing energy, ribosomes assembling proteins, lysosomes breaking down waste. What's astonishing is how much happens inside a single cell. It's not just a bag of chemicals. It's a factory, a library, a power plant, a transportation network, all rolled into one microscopic package. At any given moment, thousands of chemical reactions are occurring, carefully regulated by enzymes and signaling molecules. DNA is being transcribed into RNA. RNA is being translated into proteins. Proteins are folding into precise three-dimensional shapes and carrying out their functions, all in a dance so intricate and well choreographed that even a single misstep can cause disease. And cells communicate. They send chemical signals to each other, coordinate their activities, divide labor. Cells in your pancreas sense rising blood sugar and release insulin. Cells in your immune system patrol for invaders and remember past infections. Neurons in your brain fire in patterns that create thoughts, memories, emotions, perhaps even the sense of self. The feeling that you are a unified consciousness rather than a colony of trillions of semi-independent units. Because that's what you are, really. You're not a single thing. You're a superorganism, a community of cells that have agreed, in an evolutionary sense, to cooperate, to specialize, to sacrifice their individual interests for the good of the whole. Most of your cells will never reproduce. They exist to serve the collective, you, and when you die, they die with you, their lineage ending. Only a few cells, egg or sperm, have a chance to continue into the next generation, and even that view is incomplete. Many of the cells in your body aren't even human. You're home to trillions of bacteria, mostly in your gut, forming a microbiome essential to your health. They help digest food, produce vitamins, train your immune system, maybe even influence your mood and behavior. You're not an individual, you're an ecosystem, a walking coral reef of cooperating organisms. The discovery of antibiotics revolutionized medicine and turned infections that were once death sentences into treatable conditions. There's a scene that played out countless times throughout history. A child cuts their hand on a rusty nail. The wound gets infected. Fever sets in. The infection spreads. Within days, the child is dead, and there's nothing anyone can do about it. A simple cut, a common bacteria, and a life over before it began. That was the reality for most of human existence. Infections killed indiscriminately. Pneumonia, tuberculosis, sepsis, syphilis. These were among the leading causes of death. Childbirth was dangerous partly because of infections. Surgery was a last resort because even if the operation was successful, post-operative infections often killed the patient anyway. Soldiers in wars died more often from infected wounds than from the wounds themselves. Then came antibiotics, and everything changed. We've already talked about how Alexander Fleming discovered penicillin in 1928, noticing that mold killed bacteria in a petri dish. But it took more than a decade to turn that observation into a usable medicine. During World War II, Howard Florey and Ernst Boris Chain developed methods to purify and mass-produce penicillin. The first patient treated with purified penicillin in 1941 was a British policeman with a severe infection. He improved dramatically, but they ran out of penicillin and he died. But subsequent patients with more ample supplies were cured of infections that would have killed them just years earlier. By the end of World War II, penicillin was being mass-produced. Soldiers who would have died from infected wounds survived. Surgical procedures became far safer. Diseases like strep throat, scarlet fever, and bacterial meningitis became treatable. Life expectancy increased dramatically, not just because of antibiotics, but they were a major factor. Penicillin was just the first. Scientists discovered or synthesized dozens of other antibiotics: streptomycin for tuberculosis, tetracycline for a wide range of infections, vancomycin for resistant strains. Each one worked slightly differently, targeting different aspects of bacterial biology. Some interfered with cell wall synthesis, some disrupted protein production, some damaged bacterial DNA. For a while, it seemed like we'd conquered infectious disease. New antibiotics kept being discovered, and bacteria, though they evolved resistance, were always overcome by the next generation of drugs. But that golden age is ending. Antibiotic resistance is rising faster than new antibiotics are being developed. Bacteria like MRSA, methicillin-resistant Staphylococcus aureus, are resistant to multiple drugs. Some infections are becoming untreatable again, and we're facing the possibility of a post-antibiotic era where common surgeries become risky once more. It's a reminder that evolution never stops. Bacteria reproduce rapidly and mutate constantly. When we use antibiotics, we create selective pressure. Bacteria with resistance genes survive and reproduce, passing those genes on. Overuse and misuse of antibiotics in medicine and especially in agriculture, where they're often used to promote growth in livestock, have accelerated this process. But for now, Antibiotics still work for most infections. They're still saving lives every day, and they're a testament to the power of scientific observation, of following unexpected findings wherever they lead, of translating basic research into practical application. Fleming's moldy petri dish led to one of the greatest medical advances in history, and millions of people alive today owe their existence to that discovery. We discovered that planets orbit other stars, exoplanets, with the first confirmed detection in 1992. For thousands of years, humans looked at the stars and wondered, are we alone? Do other worlds exist beyond our solar system? Are there planets orbiting those distant suns? And if so, what are they like? These questions were unanswerable for most of history. The stars were too far away, the planets too dim. Even the largest telescopes couldn't resolve enough detail to see a planet orbiting another star. Planets don't produce their own light. They shine only by reflecting their star's light. And they're so much dimmer and so close to their bright parent stars that detecting them seemed impossible. But in 1992, astronomers Alexander Wolszczan and Dale Frail announced the first confirmed detection of planets outside our solar system. Surprisingly, these weren't orbiting a normal star, but a pulsar, a rapidly spinning neutron star. They detected the planets by measuring tiny variations in the pulsar's radio pulses, variations caused by the gravitational tug of orbiting planets. It was an indirect detection, not a direct image, but it was proof. Other solar systems existed. Then in 1995, Michel Mayor and Didier Queloz discovered the first planet orbiting a Sun-like star, 51 Pegasi b. It was a hot Jupiter, a gas giant planet orbiting incredibly close to its star, completing an orbit in just 4 days. This was shocking. In our solar system, rocky planets are close to the Sun and gas giants are far out. But 51 Pegasi b defied those expectations. It suggested that solar systems could be far more diverse than we'd imagined. Since then, the floodgates have opened. Using increasingly sophisticated techniques, watching for the tiny wobble a planet causes in its star, measuring the dimming when a planet passes in front of its star, even occasionally taking direct images, astronomers have discovered thousands of exoplanets. The Kepler Space Telescope alone found more than 2,600 confirmed planets. We now know that planets are common. Most stars have planets. There are likely more planets in the Milky Way than there are stars. Hundreds of billions of worlds. And they're incredibly diverse. There are super-Earths, rocky planets larger than Earth but smaller than Neptune. There are hot Jupiters orbiting so close to their stars that their atmospheres are being stripped away. There are planets orbiting binary star systems, where 2 suns rise and set. There are rogue planets drifting through interstellar space, untethered to any star. There are planets in the habitable zone, the region where temperatures might allow liquid water to exist on the surface. Some of these planets might harbor life. We don't know yet. We haven't detected any definitive biosignatures, chemical signs of life in a planet's atmosphere. But the search is on. New telescopes, like the James Webb Space Telescope, can analyze the atmospheres of exoplanets, looking for oxygen, methane, and other gases that might indicate biological activity. Within the next few decades, we might answer one of humanity's oldest questions. Are we alone? Even if we find that most planets are barren, the discovery of exoplanets has transformed our perspective. Earth isn't special in the sense of being the only planet, or even the only rocky planet in a habitable zone. we're one world among countless others, a single experiment in a universe running trillions of experiments simultaneously. And that's both humbling and exhilarating. Somewhere out there, maybe, on a planet orbiting a star you can't even see with the naked eye, someone or something might be looking back, wondering if they're alone, asking the same questions you're asking, feeling the same wonder you feel when you look up at the night sky. Or maybe not. Maybe we're the only ones asking these questions, the universe's only way of knowing itself. Either way, the cosmos is vaster and stranger than we ever dreamed, full of worlds beyond imagining, and we're just beginning to explore them, one distant pixel at a time. The structure of space-time can ripple, creating gravitational waves that travel across the cosmos at light speed. Imagine space-time as a vast, invisible fabric stretching across the universe. Now imagine dropping a stone into a still pond, ripples spread outward from the point of impact, waves moving across the water's surface. Gravitational waves are like those ripples, but they're ripples in space-time itself, created by some of the most violent events in the cosmos: colliding black holes, merging neutron stars, exploding supernovae. Einstein predicted gravitational waves in 1916 as a consequence of his general theory of relativity. If gravity is the curvature of space-time caused by mass and energy, then accelerating masses should create waves in that curvature, much like accelerating electric charges create electromagnetic waves. But Einstein himself doubted we'd ever detect them. The waves are incredibly weak. Even from cosmic cataclysms, they stretch and compress space by an amount far smaller than an atomic nucleus. For a century, physicists tried to detect gravitational waves. They built increasingly sensitive instruments, but the signals remained frustratingly out of reach. Then on September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected a signal. Two black holes, each about 30 times the mass of the Sun, had spiraled into each other 1.3 billion light-years away. In the final fraction of a second before they merged, they released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that moment. That wave propagated outward at the speed of light, spreading across the universe. When it reached Earth, it stretched and compressed space by about 1,000th the diameter of a proton. But LIGO was sensitive enough to detect it. The two LIGO detectors, one in Louisiana and one in Washington state, both saw the same signal milliseconds apart. It was the first direct detection of gravitational waves, confirmation of Einstein's prediction, and the beginning of a new era in astronomy. Since then, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events, mostly colliding black holes, but also merging neutron stars. That last category is especially exciting because neutron star mergers produce both gravitational waves and light, allowing astronomers to observe the same event in multiple ways. In 2017, LIGO detected gravitational waves from merging neutron stars, and within seconds, telescopes around the world were pointed at the source, observing the explosion in visible light, X-rays, gamma rays, and radio waves. It was a watershed moment, multi-messenger astronomy, using different types of signals to study cosmic events. Gravitational waves give us a new way to observe the universe. Light can be blocked or scattered, but gravitational waves pass through everything unimpeded. They carry information from the hearts of black holes, from the moments after the Big Bang, from regions of space-time we can't observe any other way. It's like gaining a new sense, like being born deaf and suddenly hearing sound for the first time. And it's profound on a deeper level too. Gravitational waves are proof that space-time is a real, physical thing, not just a mathematical abstraction. It can ripple, stretch, compress. When a gravitational wave passes through you, and they do all the time, though far too weakly to notice, you're literally being stretched and compressed, along with the space around you. The distance between atoms in your body changes infinitesimally as the wave passes. You're always moving through space-time, but space-time itself is moving too, vibrating with the echoes of cosmic collisions, humming with the reverberations of the universe's most energetic events. It's a strange and beautiful thought. You're not in space exactly. You're made of space, woven into it, and it's woven into you. And as you lie there, peaceful and still, space-time ripples gently around you, carrying messages from distant corners of the cosmos, whispering secrets about black holes and neutron stars and the fundamental nature of gravity itself. And maybe in some small way, you're listening. We discovered photosynthesis, the process by which plants convert sunlight, water, and carbon dioxide into sugar and oxygen. Take a deep breath. Hold it for a moment. Now exhale. That oxygen you just breathed in, the oxygen that's keeping you alive right now, was made by plants. Or more precisely, it was made by photosynthesis, one of the most important chemical processes on Earth. For billions of years, Earth's atmosphere had very little oxygen. The early Earth was a place you couldn't breathe, a world of nitrogen, carbon dioxide, methane, and water vapor. Then around 2.4 billion years ago, something remarkable happened. Cyanobacteria, simple single-celled organisms, evolved the ability to use sunlight to split water molecules, releasing oxygen as a waste product. At first, that oxygen was absorbed by rocks and dissolved in the oceans, causing the Great Oxidation Event. Iron in the oceans rusted, forming the vast iron ore deposits we mine today. Eventually, the oceans and rocks were saturated, and oxygen began accumulating in the atmosphere. It was an environmental catastrophe for the anaerobic organisms that dominated the Earth at the time. Oxygen was toxic to them, but it was also an opportunity. Oxygen-breathing organisms evolved, and they could extract far more energy from food than their anaerobic ancestors. Complex life became possible. Today, photosynthesis is carried out by plants, algae, and cyanobacteria. It's an elegant process. Chlorophyll, the green pigment in plant cells, absorbs light, mostly red and blue wavelengths, reflecting green, which is why plants look green. That light energy is used to split water molecules into hydrogen and oxygen. The oxygen is released into the air. The hydrogen is combined with carbon dioxide from the air to produce glucose, a simple sugar that the plant uses for energy and to build more complex molecules like cellulose and starch. The chemical equation is simple. Carbon dioxide plus water with sunlight and chlorophyll yields glucose and oxygen, but the actual process is staggeringly complex, involving dozens of steps, multiple protein complexes embedded in cell membranes, and electron transport chains that would make an electrical engineer envious. Photosynthesis is the foundation of almost all life on Earth. Plants use it to grow. Herbivores eat the plants, absorbing the stored energy. Carnivores eat the herbivores. Even decomposers, breaking down dead matter, are ultimately feeding on energy that came from the sun and was captured by photosynthesis. There are a few ecosystems, deep-sea hydrothermal vents for example, that don't rely on sunlight, but they're the exception. The vast majority of life on Earth is solar-powered, either directly or indirectly. And it's not just energy. Photosynthesis pulls carbon dioxide out of the atmosphere and locks it in organic matter. Over geological time, some of that carbon gets buried and turns into coal, oil, and natural gas, fossil fuels, which are essentially stored sunlight from millions of years ago. When we burn them, we're releasing that ancient carbon back into the atmosphere, disrupting the balance that photosynthesis maintains. Plants and algae produce about 330 billion tons of oxygen every year through photosynthesis. That might sound like a lot, but it's actually in balance with consumption. Animals, bacteria, and other processes use up about the same amount. If photosynthesis stopped tomorrow, we'd run out of breathable oxygen in a few thousand years. Not immediately, but inevitably. So as you breathe in and out, slow and steady, settling into sleep, remember that every breath connects you to the green world, to the trees outside your window, the grass in the park, the algae in the ocean, the microscopic cyanobacteria floating in lakes and seas. They're quietly, constantly splitting water and assembling sugar, powered by sunlight, producing the oxygen you need to live. You and the plants are partners in an ancient exchange. They give you oxygen. You give them carbon dioxide. It's a collaboration billions of years old, a cycle that connects all aerobic life. A reminder that you're not separate from nature, but embedded in it, dependent on it, part of a system so vast and intricate that it sustains an entire living planet. And tonight, as you rest, that cycle continues, breath by breath, the rhythm of life itself. The discovery of electricity's connection to magnetism in the 1820s unified two forces and paved the way for modern technology. For a long time, electricity and magnetism seemed like separate phenomena. Electricity was lightning, sparks from rubbing amber, the shock you got from certain fish. Magnetism was lodestones attracting iron, compass needles pointing north. They were curiosities, interesting but seemingly unrelated. Then, in 1820, Danish physicist Hans Christian Ørsted was giving a lecture on electricity. During a demonstration, he placed a compass near a wire carrying electric current. The compass needle deflected, moving away from north to point perpendicular to the wire. Ørsted realized something profound. Electric current creates magnetism. It was a revelation. Within weeks, other scientists were building on the discovery. André-Marie Ampère showed that parallel wires carrying current in the same direction attract each other, while wires carrying current in opposite directions repel. Michael Faraday discovered electromagnetic induction, that moving a magnet near a wire induces an electric current in the wire. This was the key to generators and motors, devices that convert motion into electricity and electricity into motion. In the 1860s, James Clerk Maxwell unified it all mathematically. He showed that electricity and magnetism aren't separate forces. They're different aspects of a single force. Electromagnetism. His equations, now called Maxwell's equations, describe how electric and magnetic fields interact and propagate. And they predicted something startling. Oscillating electric and magnetic fields should create waves that travel through space at a specific speed. When Maxwell calculated that speed, it turned out to be the speed of light. Light, Maxwell realized, is an electromagnetic wave. Visible light, radio waves, X-rays, infrared, ultraviolet, all of them are electromagnetic radiation, differing only in wavelength and frequency. It was one of the great unifications in physics, showing that seemingly different phenomena, electricity, magnetism, and light, are all manifestations of the same underlying force. This discovery transformed the world. Understanding electromagnetism led to electric power generation and distribution. Faraday's discovery of induction made possible the electric motors that run everything from fans to trains, and the generators that produce the electricity powering your lights, your devices, your life. Maxwell's equations enabled radio communication, Marconi's wireless telegraph, modern cell phones, Wi-Fi, GPS, all depend on electromagnetic waves carrying information through space. It's hard to overstate how much of modern life depends on electromagnetism. The device you're using to read this, the light that might be on in your room, the electricity running through your walls, the radio waves connecting you to the world, all of it is electromagnetism at work. And it goes deeper. Electromagnetism is one of the 4 fundamental forces of nature, along with gravity, the strong nuclear force, and the weak nuclear force. It's what holds atoms together. Electrons are bound to nuclei by electromagnetic attraction. It's responsible for chemistry. Chemical bonds are electromagnetic interactions between atoms. It's why matter is solid, why you don't fall through your chair, why surfaces feel hard. When you touch something, you're not actually touching it. The electrons in your skin and the electrons in the object are repelling each other electromagnetically. And that repulsion is what you feel as touch. You're not separate from the electromagnetic universe. You're part of it, woven into it, shaped by it. And as you drift towards sleep, maybe that's oddly comforting. You're connected through invisible fields and forces to everything around you, part of a vast, interconnected web of energy and matter, all dancing to the elegant mathematics discovered by Maxwell and the experimentalists who came before him. And maybe that's enough to be here, now, part of the pattern riding the waves. We learned that most of the universe's matter is invisible, dark matter that doesn't emit light, but shapes galaxies with its gravity. Look up at the night sky on a clear, moonless night. You see stars, hundreds, maybe thousands, if you're far from city lights. Each star is a sun, a massive ball of fusing hydrogen. Collect all those stars together, all 100 billion or so in the Milky Way, and you have a galaxy. It's an almost incomprehensible amount of matter, so much light, so much mass. But here's the strange thing. All those stars, all that shining matter, all the gas and dust and planets, everything we can see, makes up only about 15% of the matter in the galaxy. The rest, about 85%, is invisible. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all. We call it dark matter, not because it's dark like a shadow, but because it's invisible, and we know it's there because of its gravity. In the 1930s, astronomer Fritz Zwicky was studying the Coma Cluster, a group of galaxies. He measured how fast individual galaxies were moving within the cluster and calculated how much mass would be needed to keep them gravitationally bound. The number was staggering, far more mass than could be accounted for by the visible galaxies. He proposed that most of the cluster's mass was dark matter, unseen but necessary to explain the motion. Most astronomers ignored him. It seemed too strange. But in the 1970s, Vera Rubin studied the rotation of spiral galaxies and found the same problem. Stars at the edges of galaxies were moving just as fast as stars near the center. According to Newtonian physics, they should be moving slower. The farther from the center, the weaker the gravity, so the slower the orbit. But they weren't. Something with mass, something invisible, was spread throughout the galaxy, providing extra gravity to speed up those outer stars. Since then, evidence for dark matter has accumulated. Gravitational lensing, the bending of light around massive objects, shows that there's more mass in galaxy clusters than we can see. The cosmic microwave background's temperature fluctuations match predictions that include dark matter. Computer simulations of galaxy formation only work if they include dark matter. The case is overwhelming. Most of the matter in the universe is something we've never directly detected. What is it? We don't know. It's not made of atoms. If it were, we'd see it interacting with light. The best guess is that it's made of exotic particles that interact only through gravity, and perhaps the weak nuclear force. Physicists have built detectors deep underground, shielded from cosmic rays, hoping to catch a dark matter particle interacting with ordinary matter. So far, nothing definitive. Dark matter remains stubbornly elusive, but its effects are undeniable. Dark matter shaped the universe. In the early universe, slight overdensities in dark matter grew through gravity, pulling in ordinary matter, forming the seeds of galaxies. Without dark matter, galaxies wouldn't have formed the way they did. Structures in the universe would be much smaller. Stars, planets, life, all might not exist. So here you are, lying on a planet orbiting a star in a galaxy, held together by invisible matter that you can't see, can't touch, can't directly detect, but which is far more abundant than the familiar matter you're made of. More than 4/5 of the matter in the universe is unknown to us. We're like people living in a forest who can see the leaves and branches, but not the roots that anchor everything. It's humbling. The universe is stranger and more mysterious than we imagined. And maybe that's okay. Maybe not knowing, not understanding everything, leaves room for wonder. Maybe the darkness isn't something to fear, but something to be curious about. A reminder that there's always more to discover, always deeper layers to reality, waiting patiently for someone clever enough, patient enough, to uncover them. And tonight, as you rest, dark matter is all around you, invisible and silent, holding galaxies together, shaping the cosmos, a hidden foundation for everything you see and everything you are. The theory of plate tectonics explained earthquakes, volcanoes, and mountain formation as the result of Earth's shifting crustal plates. We touched on continental drift earlier, but it's worth diving deeper into plate tectonics because it's one of the most complete and elegant theories in all of Earth science. It explains so much. Why earthquakes happen where they do, why volcanoes form rings around the Pacific Ocean, why mountain ranges rise, why certain regions are rich in specific minerals. It's a unifying framework, the geology equivalent of evolution in biology or relativity in physics. The Earth's outer shell, the lithosphere, is broken into about a dozen major plates and several smaller ones. These plates are 50 to 100 miles thick, including both the crust and the uppermost part of the mantle. They float on the asthenosphere, a layer of partially molten, ductile rock that flows very slowly over geological time. The plates move, driven by heat from Earth's interior. Hot rock rises in the mantle, cools near the surface, then sinks back down, creating convection currents that drag the plates along. At some boundaries, plates pull apart. Magma rises to fill the gap, creating new crust. These are divergent boundaries, like the Mid-Atlantic Ridge, where new seafloor is constantly being formed and the Atlantic Ocean widens. At other boundaries, plates collide. If both are continental plates, they crumple upward, forming mountain ranges. The Himalayas, for instance, are the result of the Indian plate crashing into the Eurasian plate. If one plate is oceanic and the other continental, the denser oceanic plate dives beneath the continental plate in a process called subduction. The descending plate melts, and the molten rock rises to form volcanoes. This is why the western coast of South America, where the Nazca Plate subducts beneath the South American plate, is so volcanically active. At transform boundaries, plates slide past each other horizontally. The friction is immense. The plates lock together, building stress over decades or centuries. Eventually, the stress exceeds the friction, and the plates suddenly slip, an earthquake. The San Andreas Fault in California is a transform boundary where the Pacific Plate and North American Plate grind past each other, causing the earthquakes that periodically shake the region. Plate tectonics also explains the distribution of fossils. Identical fossils appear on continents now separated by oceans because those continents were once joined. It explains why certain rock formations and mountain ranges line up across ocean basins. It explains the ages of ocean floor, youngest at mid-ocean ridges, oldest near continents, and nowhere older than about 200 million years because old seafloor gets recycled through subduction. The theory took decades to be accepted. Alfred Wegener proposed continental drift in 1912, but most scientists rejected it because he couldn't explain what force moved continents. It wasn't until the 1960s, with the discovery of seafloor spreading and the mapping of magnetic stripes on the ocean floor, which recorded reversals in Earth's magnetic field and proved new crust was forming at mid-ocean ridges, that the pieces fell into place. Plate tectonics became the unifying theory of geology. And it's ongoing. Right now, as you lie still, the ground beneath you is moving. The plates are shifting, mountains are rising, ocean floors are spreading. In 50 million years, the continents will be in different positions. Africa will have collided with Europe, closing the Mediterranean. Australia will have merged with Asia. California, west of the San Andreas Fault, will have slid northward. The Earth is restless, always changing, never still. This dynamism might be essential for life. Plate tectonics recycles carbon, pulling carbon dioxide out of the atmosphere when rocks weather and pushing it back out through volcanoes. This carbon cycle regulates Earth's climate over geological time, keeping it relatively stable despite the sun's increasing brightness. Without plate tectonics, Earth might have become a lifeless desert like Mars or a runaway greenhouse like Venus. So as you rest on this active, dynamic planet, appreciate that you're not on a static ball of rock, but on a living world, geologically speaking. One that breathes and shifts and renews itself. One that's been doing so for billions of years and will continue long after humanity is gone. The ground is solid enough to hold you, but fluid enough to move mountains. patient enough to build continents over eons, violent enough to shake cities in seconds. And somehow, in the middle of all that dynamism, life flourishes, clinging to the surface of a restless world, adapting to changes, thriving in the spaces between catastrophes. And that perhaps is the real miracle. We discovered that living organisms pass traits to offspring through genes, the units of heredity identified by Gregor Mendel in the 1860s. Why do children look like their parents? Why does a golden retriever always have golden retriever puppies, never beagles or poodles? For most of history, inheritance was mysterious. People noticed family resemblances, but the mechanism was unknown. Some thought traits blended like paints mixing. A tall parent and a short parent would produce medium-height children. Others thought environmental influences during pregnancy shaped offspring. Then came Gregor Mendel, an Augustinian friar working in a monastery garden in what's now the Czech Republic. Between 1856 and 1863, he conducted meticulous experiments with pea plants, carefully crossbreeding varieties with different traits, tall versus short, green seeds versus yellow seeds, smooth pods versus wrinkled pods. He kept detailed records of thousands of plants across multiple generations. What he discovered was revolutionary. Traits didn't blend. They were inherited as discrete units. We now call them genes, that could be dominant or recessive. A tall plant crossed with a short plant didn't produce medium plants. It produced tall plants because tallness was dominant. But those tall plants carried a hidden factor for shortness. When those plants were bred together, about 3/4 of their offspring were tall and 1/4 were short. The recessive trait reappeared, proving it hadn't been lost or blended away. Mendel worked out the mathematical ratios, showing that inheritance followed predictable patterns. Each parent contributes one copy of each gene, and offspring inherit one copy from each parent. If you have 2 copies of the dominant form, you show the dominant trait. If you have 1 dominant and 1 recessive, you still show the dominant trait. Only with 2 recessive copies does the recessive trait appear. He published his findings in 1866 in a relatively obscure journal. Almost no one paid attention. It wasn't until 1900, 16 years after Mendel's death, that 3 different scientists independently rediscovered his work and realized its significance. Suddenly, inheritance made sense. Darwin's theory of evolution by natural selection had lacked a mechanism for how traits were passed down and how variation was maintained. Mendel provided that mechanism. We now know that genes are stretches of DNA that code for proteins or regulate other genes. You have about 20,000 to 25,000 genes spread across 23 pairs of chromosomes. Each gene can have different versions, alleles, and which alleles you inherit determines many of your traits. Eye color, blood type, whether you can roll your tongue, whether you'll develop certain genetic diseases, all governed by genes. But it's more complex than Mendel could have known. Most traits aren't controlled by a single gene, but by many genes working together, plus environmental influences. Height, for instance, is influenced by hundreds of genes, plus nutrition during development. Intelligence, personality, susceptibility to diseases, all involve complex interactions between multiple genes and environment. And some genes don't follow Mendel's simple dominant recessive pattern. Some show incomplete dominance, where heterozygotes show a blend. Some genes are linked, inherited together because they're close on the same chromosome. Still, Mendel's fundamental insight holds. Heredity is particulate, not blending. Information passes from parent to offspring in discrete units that don't mix or disappear. Each of your cells contains a complete copy of your genome, about 3 billion DNA base pairs, arranged into genes that encode the instructions for building and running a human body. Half of those instructions came from your mother, half from your father, and you're a unique combination that's never existed before and never will again. And when those genes are expressed, when DNA is transcribed into RNA and translated into proteins, those proteins fold into specific shapes and carry out specific functions, building your body, maintaining your cells, giving you your traits. You are, in a very real sense, the physical manifestation of your genes interacting with your environment. Not determined by your genes, there's no gene for who you are, but shaped by them, constrained by them, enabled by them. The discovery of thermodynamics laws showed that energy can neither be created nor destroyed, only transformed. There's a certain economy to the universe. Nothing is truly created. Nothing is truly destroyed. Everything just changes form. This is the essence of the first law of thermodynamics, and it's one of the most fundamental principles in all of physics. The story begins with steam engines. In the early 1800s, during the Industrial Revolution, engineers were building machines that converted heat into mechanical work, pumping water, powering factories, driving locomotives. But the process was inefficient. Most of the heat was wasted. Engineers wanted to understand why and how to improve efficiency. Scientists studying these questions, people like Sadi Carnot, James Joule, and Rudolf Clausius, gradually worked out the principles of thermodynamics, the science of heat and energy. The first law emerged from their work: energy is conserved. In any process, the total amount of energy remains constant. Energy can change from one form to another: heat to motion, chemical energy to electrical energy, potential energy to kinetic energy. But the total never changes. This might seem obvious now, but it was a profound realization. It meant perpetual motion machines, devices that could run forever without any input of energy, were impossible. It meant that energy had to come from somewhere. When coal burns, releasing heat, that energy was stored in the chemical bonds of the coal molecules, which ultimately came from sunlight captured by ancient plants through photosynthesis. Nothing was being created. Energy was just being converted from one form to another. The second law of thermodynamics is even more profound, and in some ways, sadder. It says that in any energy transformation, some energy becomes unavailable to do work. Entropy, a measure of disorder or randomness, always increases in a closed system. Heat flows from hot to cold, never the reverse unless you put in work. Concentrated, organized energy inevitably disperses and becomes less useful. This is why engines can never be 100% efficient. Some of the heat energy always escapes without doing useful work. It's why your body produces waste heat. You're not a perfect converter of chemical energy to mechanical energy and thought. It's why the universe is gradually running down, heading toward a state called heat death, where all energy is evenly distributed, no gradients exist, and nothing interesting can happen anymore. But that's trillions upon trillions of years in the future. For now, there are still hot stars and cold space, still energy flowing from one place to another, still stars forming and galaxies colliding and life evolving. Entropy increases, yes, but locally, temporarily, order can emerge. Life itself is an example. You're an incredibly organized, low entropy system, maintaining your structure by consuming food and releasing heat, exporting entropy to your surroundings. The third law of thermodynamics says that as temperature approaches absolute zero, entropy approaches a minimum value. It's a statement about the limits of coldness, about the impossibility of reaching absolute zero in a finite number of steps. There's always a little bit of thermal motion, a little bit of uncertainty, even at the coldest possible temperatures. Together, these laws govern everything that involves energy, which is to say, everything: chemistry, biology, engineering, cosmology. All of it operates within the constraints of thermodynamics. You can't win, energy is conserved. You can't break even, entropy increases. And you can't quit the game. You can't reach absolute zero. But within those constraints, the universe is incredibly creative. Stars fuse hydrogen into helium, releasing energy that warms planets. Plants capture that energy and store it in sugars. Animals eat the plants and use that energy to move, to think, to live. Eventually, that energy dissipates as heat, entropy increases, and the cycle continues. Nothing is lost, just transformed endlessly, beautifully, following rules that were worked out by people trying to build better engines. So as you lie there, warm and comfortable, know that the heat you're feeling is energy. Energy that came from the food you ate, which came from plants or animals, which ultimately came from the sun, which got it from nuclear fusion, which converted mass into energy, according to EMC2. And that warmth is radiating away, spreading out into the cooler air around you, increasing the entropy of the universe by an infinitesimal amount. You're part of the flow, part of the great cosmic process of energy transformation that's been running since the Big Bang and will continue until the last star burns out. And maybe there's comfort in that, in being part of something so vast and ancient, in following rules so fundamental they govern everything from stars to cells to your own beating heart. You're temporary, yes, but you're also part of something eternal, something that never ends, only changes form. And tonight, that's enough. We found that the brain generates electricity and that neurons communicate through electrical and chemical signals. You're thinking right now. You're processing these words, making sense of them, perhaps visualizing the concepts they describe. And all of that, every thought, every memory, every sensation, is happening because of electricity. Your brain is about 3 pounds of tissue, wrinkled and pinkish gray, floating in protective fluid inside your skull. It contains about 86 billion neurons, each one a specialized cell capable of generating and transmitting electrical signals. These neurons form trillions of connections, synapses, creating a network so complex that we're only beginning to understand how it works. For a long time, people didn't know what the brain did. Ancient Egyptians thought it was useless and threw it away during mummification, preserving the heart instead. Aristotle thought the brain was a cooling organ for the blood. It wasn't until the 1600s that scientists began to suspect the brain was the seat of thought and sensation. In the 1780s, Luigi Galvani discovered that frog legs twitched when touched with metal electrodes, suggesting that nerves used electricity. But it wasn't until the 1900s that scientists really understood how neurons work. A neuron at rest maintains an electrical charge across its membrane, negative inside, positive outside. When stimulated, ion channels in the membrane open, allowing charged particles, mostly sodium and potassium ions, to flow in and out. This changes the voltage, creating a wave of electrical depolarization that travels down the neuron's axon at speeds up to 250 miles per hour. When this electrical signal reaches the end of the axon, something interesting happens. The signal can't jump directly to the next neuron. Instead, the electrical signal triggers the release of neurotransmitters, chemical messengers that float across the tiny gap between neurons, the synapse. These neurotransmitters bind to receptors on the next neuron, either exciting it, making it more likely to fire, or inhibiting it, making it less likely to fire. This combination of electrical and chemical signaling is how your brain works. Patterns of neurons firing in concert create thoughts, memories, emotions. When you remember something, neurons that fired together when the memory was formed fire together again. When you learn something new, the connections between neurons strengthen. When you see something, neurons in your visual cortex fire in patterns that represent shapes, colors, motion. When you feel happy or sad, different neurotransmitters, dopamine, serotonin, norepinephrine, modulate neural activity in specific brain regions. Your consciousness, the feeling of being you, of having experiences, of existing, emerges somehow from this vast orchestra of electrical and chemical signals. We don't fully understand how. It's one of the deepest mysteries in neuroscience. How does the firing of neurons give rise to subjective experience? How does the physical activity in your brain become the mental sensation of seeing red, or feeling pain, or falling in love? We don't have complete answers yet, but we know that your brain is constantly active, even when you're at rest, even when you're asleep. Right now, neurons in your visual cortex are processing these words. Neurons in your language centers are interpreting their meaning. Neurons in your prefrontal cortex are perhaps thinking about what it means, making connections, wondering about the implications. Neurons in your hippocampus might be encoding this moment into memory, storing it for future recall. And as you drift towards sleep, your brain doesn't shut down. It shifts modes. Different patterns of neural activity emerge. Your brain consolidates memories, transferring them from short-term to long-term storage. It performs maintenance tasks, clearing out metabolic waste that accumulated during the day. It might generate dreams, strange narratives woven from fragments of memory and imagination, serving purposes we're still trying to understand. All of it, every thought you've ever had, every sensation, every emotion, every dream, is electricity and chemistry, patterns of signals flowing through a network of cells. It's reductive, perhaps, to say that you are your brain, that consciousness is just neurons firing. But it's also awe-inspiring, the fact that matter can organize itself into a structure capable of thought, of self-awareness, of pondering its own existence. That's remarkable. You're not just in the universe. You're a way the universe has found to know itself. And tonight, as your brain shifts into its sleeping rhythms, it continues its quiet work, maintaining you, sustaining you, preparing you for tomorrow. And maybe that's the most profound thing of all, that this 3-pound lump of tissue, running on electricity and chemistry, somehow gives rise to everything you are. the discovery of stem cells revealed that some cells can develop into any type of tissue in the body. Every cell in your body came from a single cell, the fertilized egg that formed when sperm met egg. That one cell divided into two, those two into four, and so on, creating trillions of cells. But here's the amazing part. Those cells didn't all become the same thing. Some became skin cells, some became neurons, some became muscle, bone, blood, liver, kidney. More than 200 different cell types, all from the same starting point. How does that happen? How does a cell decide what to become? The answer lies in stem cells, cells that have the remarkable ability to differentiate into specialized cell types. The fertilized egg is totipotent, meaning it can become any cell type in the body, plus the cells that form the placenta. As it divides, its daughter cells become pluripotent. They can still become any cell type in the body, but not placental cells. These are embryonic stem cells, and they exist only in the very early embryo. As development continues, cells become more specialized. They become multipotent, able to differentiate into several related cell types, but not all types. A blood stem cell can become any kind of blood cell, red blood cells, white blood cells, platelets, but it can't become a neuron or a muscle cell. A neural stem cell can become neurons or glial cells, but not blood or liver cells. Stem cells were first discovered in the 1960s, when researchers found that bone marrow contained cells that could regenerate blood. This led to bone marrow transplants, which are essentially stem cell transplants, replacing a patient's diseased blood stem cells with healthy ones. It saved countless lives, particularly for people with leukemia and other blood disorders. In 1998, scientists isolated human embryonic stem cells for the first time, and the potential seemed limitless. If you could coax these cells to become any tissue type, you could potentially repair damaged organs, replace lost neurons in Parkinson's or Alzheimer's patients, grow new heart tissue after a heart attack, even create entire organs for transplant. But embryonic stem cells came with ethical concerns. They're derived from embryos, which raises questions about the moral status of early human life. Then, in 2006, Japanese scientist Shinya Yamanaka discovered something remarkable. You could take adult cells, say skin cells, and reprogram them back into a pluripotent state by introducing just 4 specific genes. These induced pluripotent stem cells, or iPSCs, could do everything embryonic stem cells could do, but without the ethical baggage. Yamanaka won the Nobel Prize for this discovery, and it's revolutionized regenerative medicine. Researchers can now take a patient's own cells, reprogram them into stem cells, differentiate them into whatever cell type is needed, and transplant them back without risk of immune rejection. Clinical trials are underway for treating everything from spinal cord injuries to macular degeneration to heart disease. We're also learning that adults retain some stem cells throughout life. Your skin constantly regenerates from stem cells in the basal layer. Your intestinal lining replaces itself every few days, grown from stem cells in intestinal crypts. Even your brain contains neural stem cells in certain regions, generating new neurons throughout life, contrary to the old belief that you're born with all the neurons you'll ever have. This ongoing regeneration is part of why you persist, why you remain recognizably you, even though most of your cells are regularly replaced. The atoms in your body cycle through every few years. The molecules are constantly being broken down and rebuilt. Even your cells are temporary, dying and being replaced. But the pattern persists. The structure maintains itself. You're like a river. The water is always different, but the river remains, a stable pattern in a constant flow. And stem cells are key to that maintenance. They're your body's repair kit, the reserve force that steps in when tissue is damaged, the source of renewal that keeps you alive and functioning. Right now, as you rest, stem cells in your bone marrow are producing new blood cells. Stem cells in your skin are generating new cells to replace ones that were shed. If you have a cut or bruise, stem cells are migrating to the site, differentiating into the cell types needed for repair. You're not a static thing. You're a process, a constant becoming, a pattern that maintains itself through endless turnover and renewal. And stem cells, these remarkable, versatile, adaptable cells, are part of what makes that possible. They're potential incarnate, cells that haven't decided what to be yet, waiting for signals that will guide them down one developmental path or another. And in that flexibility, that openness to possibility, maybe there's a lesson. Maybe we're all like stem cells in a sense, not fixed, not determined, but capable of becoming different things depending on the signals we receive, the environment we're in, the choices we make. And maybe that's hopeful. Maybe it means we're never too old, never too set in our ways, never completely finished becoming who we are. There's always potential, always the possibility of renewal, always another chapter to write. We learned that light from distant galaxies is stretched to redder wavelengths because those galaxies are moving away from us. Imagine an ambulance driving toward you with its siren blaring. The pitch sounds high, the waves compressed as the ambulance approaches. Then it passes, and the pitch drops. The sound waves stretched as the ambulance recedes. This is the Doppler effect, and it works for any wave, sound, light, water ripples. In the 1920s, astronomer Edwin Hubble was studying distant galaxies, analyzing the light they emitted. He noticed something peculiar: the spectral lines, specific wavelengths of light emitted by elements like hydrogen, were shifted toward the red end of the spectrum. This redshift meant the galaxies were moving away from Earth. But here's the remarkable part. The farther away a galaxy was, the more its light was redshifted, meaning it was moving away faster. Hubble discovered a relationship, now called Hubble's law, between a galaxy's distance and its recession velocity. The universe wasn't static, it was expanding. Every galaxy was moving away from every other galaxy, like dots on an inflating balloon. This was revolutionary. It meant the universe had a history, a beginning. If galaxies are moving apart now, they must have been closer together in the past. Trace it back far enough, and you arrive at a moment when everything was in the same place, the Big Bang. Redshift became one of the most important tools in astronomy. By measuring how much a galaxy's light is redshifted, astronomers can determine how fast it's moving away. And because the expansion of space itself is causing the motion, redshift also tells us about the structure and evolution of the universe. Light from the most distant galaxies we can see has been traveling for more than 13 billion years. During that time, the universe has been expanding, stretching the wavelengths of light. Some of this light started in the ultraviolet range, but has been stretched all the way into the infrared by the time it reaches us. The cosmic microwave background, the afterglow of the Big Bang, was once visible light, hot and bright. Now, after 13.8 billion years of expansion, it's been stretched into microwaves, cooled to just 2.7 degrees above absolute zero. Redshift also revealed something unexpected. In the 1990s, astronomers studying distant supernovae found that the universe's expansion is accelerating. Distant supernovae were fainter than expected, meaning they were farther away than they should be if the expansion were constant or slowing. Something, dark energy, is pushing the expansion to speed up. The more distant a galaxy, the faster it's receding. Not just because it started with more velocity, but because space itself is expanding faster. This accelerating expansion means that the most distant galaxies we can see today will eventually disappear from view. In trillions of years, as the expansion continues, galaxies will be so far apart that their light can't reach each other. Future astronomers in distant galaxies will look at the sky and see only their own galaxy, isolated in a dark, empty universe, with no evidence of the billions of other galaxies that once filled the cosmos. The discovery of natural selection's mechanism showed that evolution doesn't need a guiding hand. It emerges from survival and reproduction. Evolution is often misunderstood as a process with a goal, a direction, a purpose. People imagine it as a ladder with simple organisms at the bottom and humans at the top, as if everything has been striving to become us. But that's not how it works. Evolution has no goal. It's not trying to create anything. It's simply what happens when living things reproduce imperfectly in a world with limited resources. Charles Darwin realized this in the mid-1800s. He'd spent years studying geology, collecting specimens on the HMS Beagle's voyage around the world, thinking deeply about the patterns he'd observed. Finches on the Galapagos Islands had different beak shapes depending on which island they lived on and what food was available. Fossils showed extinct creatures that resembled modern ones, but were different. Domestic animals, dogs, pigeons, cattle, had been shaped by artificial selection, with humans breeding for desired traits. Darwin put it together. If humans could shape animals through selective breeding, couldn't nature do the same thing? Organisms produce more offspring than can survive. Those offspring vary. Some are slightly faster or stronger or better camouflaged. In the struggle for existence, those with advantageous variations are more likely to survive and reproduce, passing those variations to their offspring. Over many generations, this process, natural selection, could shape populations, creating adaptation without any conscious design. It was a radical idea. It meant life's diversity arose not from separate acts of creation, but from descent with modification from common ancestors. It meant humans were part of nature, not separate from it. We evolved from earlier primates, who evolved from earlier mammals, tracing back through countless forms to the first living cell. Darwin waited more than 20 years to publish his theory, knowing it would be controversial. He finally did so in 1859, in On the Origin of Species, only because another naturalist, Alfred Russel Wallace, had independently arrived at the same idea. The book caused a sensation. Some embraced it immediately. Others rejected it on religious grounds. But the evidence was overwhelming, and over time, evolution by natural selection became the foundation of biology. Natural selection is elegant in its simplicity. It requires only 3 things: variation, individuals differ; inheritance, offspring resemble parents; and differential survival, some individuals leave more offspring than others. That's it. Given those conditions, populations will evolve, adapting to their environment without any need for design or direction. And it's not just a historical process. Evolution is happening right now, all around you. Bacteria evolve resistance to antibiotics. Insects evolve resistance to pesticides. Viruses evolve to evade immune systems. Cancer cells evolve within your body, becoming resistant to treatments. Urban animals evolve behaviors adapted to city life. Evolution doesn't stop. It's ongoing, relentless, indifferent. But it's not progress. Evolution doesn't make organisms better in any absolute sense. It makes them better suited to their current environment. If the environment changes, what was advantageous might become detrimental. There's no pinnacle of evolution, no ultimate form. Bacteria are just as evolved as humans. They've been adapting to their environments for the same amount of time, and they're extraordinarily successful. And evolution isn't just competition. Cooperation can be advantageous too. Cells cooperated to form multicellular organisms. Organisms cooperate in symbiotic relationships. Social animals cooperate to raise young, defend territory, find food. Even altruism can evolve if it helps relatives survive, because relatives share genes. Natural selection acts on genes, not just individuals, and genes that promote their own survival. Even through the survival of others carrying copies of themselves will spread. We discovered that the sun produces energy through nuclear fusion, converting hydrogen into helium and releasing tremendous energy. The sun has been shining for 4.6 billion years. Every day, without fail, it rises and sets, or rather, Earth rotates, and the sun appears to rise and set, warming the planet, powering photosynthesis, driving weather, making life possible. For most of history, no one knew how. What could possibly burn for billions of years without running out of fuel? Some thought the sun was made of burning coal, but calculation showed that wouldn't work. The sun would burn out in a few thousand years. Others proposed that the sun was contracting, with gravitational potential energy converting to heat. That gave millions of years, but geologists were finding evidence that Earth was billions of years old, and the sun had to be at least as old. The answer came from nuclear physics. In the 1920s and 30s, scientists realized that atomic nuclei could fuse together, combining lighter elements into heavier ones and releasing energy in the process. In the 1930s, Hans Bethe worked out the details of how this happens in the sun. Deep in the sun's core, the temperature is about 15 million degrees Celsius, and the pressure is immense. Under these conditions, hydrogen nuclei, protons, overcome their electromagnetic repulsion, like charges repel, and fuse together. 4 hydrogen nuclei eventually combine to form one helium nucleus. The helium nucleus has slightly less mass than the 4 hydrogens did. That missing mass is converted to energy according to Einstein's EMC2. The amount of mass lost is tiny, less than 1% of the original mass. But because C2, the speed of light squared, is such a huge number, even a tiny amount of mass converts to enormous energy. The sun fuses about 600 million tons of hydrogen into helium every second, losing about 4 million tons of mass in the process. That mass becomes energy, the light and heat that radiate outward, taking about 100,000 years to work their way from the core to the surface, then just 8 minutes to travel through space to Earth. This process can continue for about 10 billion years before the sun runs out of hydrogen in its core. We're about halfway through. The sun is middle-aged, stable, reliable. When the hydrogen is depleted, the core will contract and heat up, allowing helium fusion to begin, creating carbon and oxygen. The outer layers will expand, and the sun will become a red giant, eventually swallowing Mercury and Venus, and possibly Earth. But that's billions of years away. For now, the sun is steady, fusing hydrogen, shining. Nuclear fusion is the power source of the universe. Every star shines through fusion. The heavier elements, carbon, nitrogen, oxygen, iron, gold, everything except hydrogen and helium, were forged in the cores of stars through fusion reactions, then scattered into space when those stars exploded as supernovae. You are made of stardust, literally, atoms forged in stellar furnaces billions of years ago. We've tried to harness fusion here on Earth. If we could create controlled fusion reactions, we'd have nearly limitless clean energy. Hydrogen from seawater, no radioactive waste. Unlike fission, no greenhouse gases, no risk of meltdown. But it's extraordinarily difficult. We can create fusion in hydrogen bombs, but that's uncontrolled. Controlled fusion requires containing plasma at temperatures of tens of millions of degrees, which melts any physical container. Scientists use powerful magnetic fields to confine the plasma, but achieving net positive energy, getting more energy out than you put in to sustain the reaction, has proven elusive. We're getting closer, though. Recent experiments have achieved significant milestones, and fusion power might become practical within decades. But for now, we rely on the sun's fusion indirectly. Solar panels capture sunlight directly. Fossil fuels are stored sunlight from millions of years ago. Wind and hydroelectric power are driven by solar heating. Almost all the energy we use ultimately comes from the sun, from fusion reactions in its core, from the conversion of mass into energy, from Einstein's equation playing out on a stellar scale. The germ theory of disease proved that microscopic organisms cause many illnesses, revolutionizing medicine and sanitation. For most of human history, disease was a terrifying mystery. Plagues swept through cities without warning. People died from infections, fevers, mysterious illnesses that had no obvious cause. Various theories tried to explain it: miasma, bad air, imbalance of bodily humors, divine punishment, astrological influences. None of them really worked. Then in the mid-1800s, Louis Pasteur and Robert Koch developed germ theory, the idea that many diseases are caused by microorganisms, germs, too small to see without a microscope. Pasteur showed that fermentation and spoilage were caused by microorganisms, not spontaneous generation. Koch identified specific bacteria that caused specific diseases: anthrax, tuberculosis, cholera, fulfilling what became known as Koch's postulates for proving a microbe causes a disease. It was revolutionary. Suddenly, disease made sense. Cholera spread through contaminated water. Tuberculosis spread through the air. Wound infections were caused by bacteria entering the body. And if you knew the cause, you could prevent or treat the disease. This led to enormous public health improvements. Cities built sewage systems to separate drinking water from waste. Hospitals adopted antiseptic practices, sterilizing instruments, washing hands, cleaning wounds, dramatically reducing infections. Vaccines were developed to prevent diseases like smallpox, rabies, and polio. Antibiotics, once discovered, provided treatments for bacterial infections. Life expectancy soared. In the mid-1800s, life expectancy at birth was around 40 years in many countries. By the mid-1900s, it had nearly doubled, largely due to reductions in infectious disease deaths. Childhood diseases that once killed millions became preventable or treatable. Surgeries became safe. Childbirth became far less dangerous. But germ theory was controversial at first. Many doctors resisted the idea. Ignaz Semmelweis, a Hungarian physician, discovered in the 1840s that doctors should wash their hands between patients, especially after performing autopsies and before delivering babies. Maternal mortality dropped dramatically in wards where doctors washed their hands. But his colleagues mocked him, offended by the suggestion that they were causing infections. Semmelweis was eventually committed to an asylum, where he died, ironically from an infected wound. It took decades for germ theory to be fully accepted, but once it was, medicine was transformed. Understanding that diseases have specific causes, bacteria, viruses, fungi, parasites, allowed for targeted treatments and preventions. We learned how diseases spread and how to interrupt transmission. We developed vaccines, antibiotics, antivirals, antifungals. Of course, the story doesn't end there. Microorganisms evolve, developing resistance to our treatments. New diseases emerge: HIV, Ebola, COVID-19. Old diseases that we thought were under control, like tuberculosis and measles, resurge when vaccination rates drop. The battle between humans and pathogens is ongoing, an evolutionary arms race with no final victory for either side. But we're better equipped than our ancestors. We understand the enemy. We can see bacteria and viruses under microscopes, sequence their genomes, study their weaknesses, develop countermeasures. We can track disease outbreaks in real time, predict their spread, coordinate global responses. Germ theory gave us the framework to fight back. And it's worth remembering, as you lie there in relative health, that your body is constantly fighting off infections. Your immune system is a marvel, an army of specialized cells patrolling your body, identifying and destroying invaders, remembering past infections so it can respond faster next time. Most of the time, you don't even notice. Millions of potential infections are stopped before they start, handled quietly and efficiently by immune cells you never think about. You're also host to trillions of harmless or beneficial microorganisms, your microbiome, especially in your gut. Most microbes aren't pathogens. Most are neutral or helpful, aiding digestion, producing vitamins, training your immune system, even influencing your mood. Germ theory taught us to fear microbes, but we've since learned that we need them, that we're healthier with them than without them, that we're not really individuals but ecosystems. We found that the universe has a shape and structure, with galaxies organized into clusters, superclusters, and vast cosmic filaments. When you look up at the night sky, the stars seem randomly scattered, sprinkled across the darkness without pattern or order. But zoom out, way out, and a structure emerges. The universe is not a uniform distribution of matter. It's organized into a vast cosmic web, a network of filaments and clusters separated by enormous voids. Galaxies aren't evenly spread through space. They cluster together, drawn by mutual gravity. Our Milky Way is part of the Local Group, a cluster of about 80 galaxies, including Andromeda, and a bunch of smaller dwarf galaxies. The Local Group, in turn, is part of the Virgo supercluster, a collection of thousands of galaxies spanning about 110 million light-years. But even superclusters aren't the largest structures. They're organized along filaments, vast threads of galaxies stretching across hundreds of millions of light years. Between the filaments are voids, immense regions of nearly empty space, sometimes 300 million light-years across with very few galaxies. This structure, the cosmic web, emerged from tiny density fluctuations in the early universe. In the cosmic microwave background, we see those fluctuations as slight temperature variations. Regions that were slightly denser had slightly stronger gravity, attracting more matter. Over billions of years, those small overdensities grew, pulling in surrounding matter, forming the first galaxies, then clusters, then superclusters, then filaments. Dark matter played a crucial role. It doesn't interact with light, so it can clump together without radiation pressure, pushing it apart. Dark matter formed the scaffolding of the cosmic web first, and ordinary matter followed, falling into the dark matter's gravitational wells, forming stars and galaxies where the dark matter was most concentrated. Mapping this structure took decades. Astronomers had to measure the distances to millions of galaxies, plotting them in 3 dimensions. Early surveys revealed that galaxies weren't randomly distributed. They formed patterns, walls, and sheets surrounding voids. In 1989, astronomers discovered the Great Wall, a sheet of galaxies about 500 million light-years long. As surveys became more extensive, the full cosmic web came into focus. Computer simulations, based on our understanding of gravity and dark matter, reproduced the observed structure beautifully. The universe looks like a foam or a sponge, dense filaments surrounding empty voids with clusters at the intersections of filaments. And it's not static. The structure is evolving. Gravity pulls clusters together along the filaments. Eventually, over trillions of years, galaxy clusters will merge into larger clusters. But the accelerating expansion of the universe, driven by dark energy, will eventually halt this process. Clusters will become isolated, separated by ever-growing expanses of empty space as the universe expands faster than gravity can pull things together. But that's far in the future. For now, we can observe this magnificent structure, the result of 13.8 billion years of gravitational evolution. And we're part of it. A tiny speck on a planet orbiting a star in a galaxy, in a cluster, in a supercluster, in a filament, in the cosmic web. Our address is incredibly long and incredibly specific. There's something humbling and awe-inspiring about that. The universe is vast beyond comprehension, and yet it's organized, structured, shaped by forces we can understand. Gravity, acting over eons, has sculpted the cosmos into this web of light and darkness, matter and void. And we're here on a small world, looking out and trying to make sense of it all, mapping the universe's structure, tracing its evolution, understanding our place in the grand scheme. The discovery of enzymes revealed that living cells use protein catalysts to speed up chemical reactions that would otherwise take years. Your body is a chemical factory. Every moment, thousands of chemical reactions are occurring in your cells, breaking down food, building proteins, copying DNA, generating energy, neutralizing toxins. Without help, these reactions would happen incredibly slowly. Some would take years or even centuries, but in your cells, they happen in fractions of a second. The secret is enzymes, proteins that act as catalysts, speeding up reactions without being consumed in the process. Each enzyme is specialized, folding into a specific 3-dimensional shape, that creates an active site, a pocket or groove where substrates, the molecules the enzyme acts on, can bind. When a substrate binds, the enzyme stabilizes the transition state, lowering the activation energy needed for the reaction to proceed. The reaction happens, products are released, and the enzyme is ready to work again. Enzymes are astoundingly efficient. A single enzyme molecule might catalyze thousands or even millions of reactions per second, and they're specific. Each enzyme typically catalyzes only one type of reaction, or even just one reaction with one specific substrate. This specificity allows cells to control biochemical pathways with precision, turning reactions on or off, speeding them up or slowing them down, responding to changing conditions. The discovery of enzymes began in the 1800s when scientists studying digestion realized that something in gastric juices was breaking down food. In 1897, Eduard Buchner showed that cell-free extracts from yeast could ferment sugar, proving that living cells weren't necessary. The chemical machinery could work in isolation. He called the active agents enzymes, from the Greek words meaning in yeast. Over the next century, thousands of enzymes were discovered and characterized. We now know that almost every biochemical reaction in living organisms is catalyzed by an enzyme. Digestion relies on enzymes like amylase, lipase, and protease to break down carbohydrates, fats, and proteins. DNA replication depends on enzymes like DNA polymerase. Energy production in mitochondria involves dozens of enzymes in the electron transport chain and the citric acid cycle. Enzymes are also tools in industry and medicine. Laundry detergents contain enzymes that break down stains. Cheese making uses enzymes to curdle milk. DNA sequencing and genetic engineering rely on restriction enzymes that cut DNA at specific sequences. Medical treatments use enzymes. For example, tissue plasminogen activator, TPA, dissolves blood clots in stroke patients. But enzymes can also malfunction. Genetic mutations can produce defective enzymes, causing metabolic disorders. Phenylketonuria, for instance, is caused by a defective enzyme that can't break down the amino acid phenylalanine, leading to toxic buildup. Many diseases involve enzyme dysfunction. Alzheimer's involves abnormal proteins that resist breakdown by enzymes. Gaucher disease results from a deficiency in an enzyme that breaks down a fatty substance. Enzymes are also targets for drugs. Many medications work by inhibiting specific enzymes. Aspirin inhibits enzymes that produce inflammation-causing molecules. HIV drugs inhibit enzymes the virus needs to replicate. Cholesterol-lowering statins inhibit an enzyme involved in cholesterol synthesis. What's remarkable is how enzymes achieve their catalytic power. They don't just speed up reactions, they guide them, bringing reactants together in the right orientation, straining bonds, stabilizing intermediates. It's chemistry with a choreographer, reactions performed with elegance and precision that human chemists can barely match even with sophisticated laboratory equipment. And it all happens because of shape. Enzymes are proteins, chains of amino acids folded into intricate three-dimensional structures. The sequence of amino acids determines how the protein folds, and the folded shape determines function. Change even a single amino acid and the enzyme might not work. The right shape is everything. We learned that Earth has a magnetic field generated by currents in its liquid iron core, which protects us from solar radiation. There's an invisible shield surrounding Earth protecting you right now from a stream of charged particles that would otherwise strip away the atmosphere and make the surface uninhabitable. You can't see it or feel it, but it's there. Earth's magnetic field, a bubble of magnetism extending tens of thousands of miles into space. For centuries, sailors used compasses to navigate, watching magnetized needles point toward magnetic north. But no one knew why. What was pulling on the needle? What made Earth magnetic? The answer lies deep beneath your feet, nearly 2,000 miles down, in Earth's outer core. This is a layer of liquid iron and nickel, heated to thousands of degrees by the decay of radioactive elements and leftover heat from Earth's formation. The outer core is in constant motion, swirling and flowing in complex patterns driven by heat convection and Earth's rotation. When electrically conductive liquid metal flows, it generates electric currents. And electric currents generate magnetic fields. This is the geodynamo, Earth's core, acting like a giant electric generator, creating the planet's magnetic field through the motion of liquid metal. It's the same principle that powers electric generators in power plants, but on a planetary scale and running continuously for billions of years. The magnetic field extends far into space, creating the magnetosphere. It's shaped roughly like a teardrop, compressed on the side facing the sun by the solar wind, a constant stream of charged particles flowing outward from the sun and stretched into a long tail on the night side. The magnetosphere deflects most of the solar wind, channeling it around Earth. But some particles do get through, particularly near the poles where the magnetic field lines converge. These particles spiral along field lines and collide with gases in the upper atmosphere, exciting atoms and causing them to emit light. This is the aurora, the northern and southern lights. Those shimmering curtains of green, red, and purple are the visible sign of the magnetosphere at work, protecting Earth while putting on a spectacular display. Without the magnetic field, Earth would be much less hospitable. Mars once had a magnetic field, but its core cooled and solidified, shutting down the dynamo. Without magnetic protection, the solar wind gradually stripped away much of Mars's atmosphere over billions of years, leaving it cold, dry, and barren. The same thing could have happened to Earth. The magnetic field also affects technology. Solar storms, eruptions of plasma from the sun, can cause geomagnetic storms when they hit Earth's magnetosphere. These can disrupt satellites, interfere with GPS, induce currents in power grids that can cause blackouts, and increase radiation exposure for astronauts. In 1859, a massive solar storm called the Carrington Event caused telegraph systems to fail and sparked fires. If a similar storm hit today, it could cause trillions of dollars in damage to our technology-dependent civilization. Earth's magnetic field isn't constant. It wanders. Magnetic north drifts over time, currently moving from Canada toward Russia at about 30 miles per year. And periodically, the field reverses. North becomes south, south becomes north. These reversals happen every few 100,000 years on average, though the timing is irregular. The last reversal was 780,000 years ago, so we might be overdue. During a reversal, which takes thousands of years, the field weakens and becomes more complex, with multiple poles. This could make Earth more vulnerable to solar radiation, though life has survived many past reversals. Scientists study the magnetic field by examining rocks. When lava cools and solidifies, Magnetic minerals in the rock align with Earth's magnetic field at that moment, freezing a record of the field's direction. By studying magnetized rocks of different ages, especially from the ocean floor, where new rock is constantly forming at mid-ocean ridges, scientists have reconstructed the history of magnetic reversals and learned how the field has changed over millions of years. The discovery of insulin in 1921 transformed diabetes from a fatal diagnosis to a manageable condition. Before 1921, a diagnosis of type 1 diabetes was a death sentence. Children would develop intense thirst, frequent urination, rapid weight loss. Their bodies couldn't produce insulin, the hormone that allows cells to absorb glucose from the blood. Without it, blood sugar would rise to dangerous levels while cells starved, unable to access the energy all around them. Patients would waste away, falling into a coma and dying within months or a few years at most. The only treatment was starvation diets, severely restricting calories to minimize blood sugar spikes. It bought a little time, but condemned patients to a miserable existence of weakness and hunger before the inevitable end. Parents watched their children slowly die, unable to help. Then came Frederick Banting, a young Canadian surgeon with an idea. Scientists knew the pancreas produced something that regulated blood sugar. They'd found that removing the pancreas caused diabetes in dogs. But attempts to extract and use that substance had failed. The problem was that the pancreas also produces digestive enzymes, and these enzymes destroyed the insulin during extraction. Banting thought of a solution: tie off the pancreatic ducts in dogs, causing the enzyme-producing cells to atrophy while leaving the insulin-producing islet cells intact. Then extract insulin from those atrophied pancreases. With the help of Charles Best, a medical student, and biochemist James Collip, who purified the extract, they tried it. In the summer of 1921, they injected their extract into a diabetic dog named Marjorie. Her blood sugar dropped. She survived. They repeated the experiment with other dogs, refining the process. By January 1922, they were ready to try it on a human. Leonard Thompson was 14 years old, weighing just 65 pounds, dying of diabetes. On January 11, 1922, he received the first injection of insulin. The initial batch wasn't pure enough and caused an allergic reaction, but 2 weeks later, with a better purified extract, he received another injection. His blood sugar fell dramatically. He gained weight. His strength returned. He lived another 13 years, eventually dying from pneumonia, a fate common before antibiotics, but far better than the death sentence diabetes had been. The news spread rapidly. Insulin was quickly put into production. Drug companies scaled up manufacturing. Within a year, insulin was available to diabetic patients around the world. Children who'd been wasting away recovered. People could live normal lifespans with diabetes. It was one of the most dramatic medical breakthroughs in history. Banting and his colleague J.J.R. MacLeod won the Nobel Prize in 1923, one of the fastest Nobel Prizes ever awarded for a medical discovery. Banting, feeling that Best had been unjustly excluded, shared his prize money with him. MacLeod shared his with Collip. Insulin doesn't cure diabetes. Patients still need to monitor blood sugar and inject insulin daily. Early on, this meant multiple injections with primitive needles and impure insulin extracted from animal pancreases. But over time, treatments improved. Purer insulin, better needles, glucose meters, insulin pumps, continuous glucose monitors. Each advance made life easier for diabetics. In 1978, Synthetic human insulin was produced using recombinant DNA technology, bacteria genetically modified to produce human insulin. This was safer and more consistent than animal insulin, and could be produced in unlimited quantities. More recently, insulin analogs have been developed, modified versions that act faster or last longer, giving patients more flexibility in managing their blood sugar. Today, millions of people with diabetes live full, healthy lives thanks to insulin. It's not perfect. Managing diabetes requires constant vigilance, and complications can still occur, but it's manageable, and that's a miracle compared to the death sentence it once was. The discovery of insulin is also a story about access and affordability. Banting sold the patent to the University of Toronto for $1, believing that insulin was too important to be controlled by profit motives. Yet today, in some countries, insulin is prohibitively expensive, forcing some diabetics to ration their doses, sometimes with fatal consequences. The battle for affordable insulin continues, a reminder that scientific discoveries, however miraculous, must be accessible to everyone who needs them. So tonight, if you have diabetes or know someone who does, take a moment to appreciate insulin, a molecule produced by your pancreas, or injected if yours doesn't work, allowing your cells to absorb glucose, giving you energy, keeping you alive. It's a simple hormone, just 51 amino acids long, but it's the difference between life and death for millions of people. And its discovery, a century ago in a laboratory in Toronto, changed the world, turning a terminal diagnosis into a manageable condition, giving hope where there was none, allowing children to grow up, allowing people to live full lives. And maybe that's what medicine at its best should be, not just treating symptoms, but restoring possibilities, giving people futures that would otherwise be lost. And tonight, as you rest, whether insulin flows naturally through your veins or is administered by injection or pump, know that you're alive in an age where such miracles are possible, where knowledge and compassion combine to save lives. And maybe that's worth holding on to as you drift towards sleep. The knowledge that we've conquered some demons, solved some problems, turned death sentences into footnotes. There's still much to do, but we've come so far, and that's something. We found that matter comes in different states: solid, liquid, gas, plasma, and exotic forms, like Bose-Einstein condensates. Water is a shapeshifter. Freeze it and it becomes ice, solid and hard. Heat it and it becomes steam, invisible and dispersed. At room temperature, it's liquid, flowing and adapting to its container. Same substance, same molecules. 2 hydrogen atoms bonded to 1 oxygen, but completely different properties depending on temperature and pressure. These are states of matter, different ways that atoms and molecules organize themselves depending on how much energy they have. For most of history, people recognized only 3 states: solid, liquid, and gas. Ancient Greek philosophers proposed these as fundamental elements along with fire and earth. But they were wrong about the elements. Water isn't an element, it's a compound. Yet right that matter can take different forms. In solids, atoms or molecules are locked in place, held by strong bonds in fixed positions. They can vibrate but can't move freely. This gives solids definite shape and volume. Ice is solid water. Diamond is solid carbon. Iron is solid at room temperature. In liquids, molecules have more energy. They're still close together, still attracted to each other, but they can slide past one another. Liquids have definite volume but take the shape of their container. Water, oil, mercury, all liquids at room temperature. In gases, molecules have even more energy. They zip around freely, colliding with each other and with container walls. Gases have neither definite shape nor definite volume. They expand to fill whatever space is available. Water vapor, oxygen, nitrogen, all gases at room temperature. Heat is the key. When you add heat to ice, the water molecules vibrate faster until the bonds holding them in place break. The ice melts, becoming liquid. Add more heat and the molecules move even faster, eventually escaping into the air as gas. Remove heat and the process reverses. Gas condenses to liquid, liquid freezes to solid. But there are other states of matter, stranger and less familiar. Plasma is the fourth state, and it's actually the most common in the universe, though rare on Earth. In plasma, gas is heated so much that electrons are stripped from atoms, creating a soup of ions and free electrons. Lightning is plasma. So is the sun. Its entire interior and outer layers are plasma. The aurora is caused by plasma particles from the solar wind. Neon signs contain plasma. Plasma conducts electricity and responds to magnetic fields, properties that make it useful for technologies like fusion reactors and plasma TVs. Then there are exotic states created in laboratories at extreme temperatures. Cool certain gases to within a few billionths of a degree above absolute zero, and they form a Bose-Einstein condensate, where atoms lose their individual identities and act as a single quantum entity. These were predicted by Einstein and Indian physicist Satyendra Nath Bose in the 1920s, but not created until 1995. In a Bose-Einstein condensate, quantum effects become visible at macroscopic scales. The atoms move in perfect synchrony, like a single superatom. At the opposite extreme, at incredibly high pressures deep inside planets, or in laboratory experiments, matter forms strange states. Metallic hydrogen, where hydrogen is compressed so much it conducts electricity like a metal, might exist at Jupiter's core. Superionic ice, where oxygen atoms are locked in a crystal lattice while hydrogen ions flow freely, has been created in labs and might exist in the deep oceans of Uranus and Neptune. There are also liquid crystals, substances that flow like liquids, but have some molecular order like crystals. LCD screens in phones and computers use liquid crystals that align in response to electric fields, controlling light passage to create images. And then there's degenerate matter in extreme astrophysical objects. In white dwarfs, electron degeneracy pressure, a quantum effect, holds up the star against gravity. In neutron stars, matter is so compressed that protons and electrons merge into neutrons, creating a state where a teaspoon would weigh billions of tons. The state of matter depends on the balance between kinetic energy, how fast particles are moving, and potential energy, how strongly they're attracted to each other. Change the temperature or pressure, and you change which state is stable. Water freezes at 0 degrees C at sea level, but at the top of Mount Everest, where pressure is lower, it boils at about 70 degrees. On Mars, where pressure is very low, liquid water is unstable. Ice sublimates directly to vapor without melting. The discovery of chemical bonds explained how atoms stick together to form molecules. Everything you see, touch, taste, smell, every material object is made of molecules. Molecules are clusters of atoms held together by chemical bonds. Water is 2 hydrogen atoms bonded to 1 oxygen. Carbon dioxide is one carbon bonded to two oxygens. DNA is millions of atoms: carbon, hydrogen, oxygen, nitrogen, phosphorus, bonded in a precise sequence that encodes genetic information. But for a long time, no one understood how atoms bonded. Why do two hydrogen atoms join with one oxygen to form water? Why not three hydrogens, or one hydrogen, or none at all? What holds atoms together? The answer emerged gradually through the late 1800s and early 1900s as scientists discovered electrons and began to understand atomic structure. They realized that chemical bonding is all about electrons, specifically the outermost electrons in an atom's electron shells. Atoms are most stable when their outermost electron shell is full. Helium, neon, argon, the noble gases, have full outer shells, which is why they're inert and don't readily form bonds. But most atoms have incomplete outer shells and are eager to fill them. There are two main ways atoms do this. In ionic bonding, one atom transfers electrons to another. Sodium has one electron in its outer shell. It's happy to give it away. Chlorine needs one electron to complete its outer shell. It's happy to take one. Sodium gives its electron to chlorine, becoming a positively charged sodium ion. Chlorine accepts it, becoming a negatively charged chloride ion. Opposite charges attract, and the two ions stick together. Table salt, sodium chloride, held together by the electrostatic attraction between ions. In covalent bonding, atoms share electrons. Hydrogen atoms each have one electron but need two to fill their outer shell. When two hydrogens come together, they share their electrons. Each hydrogen's electron orbits both nuclei. Both atoms now have two electrons, though they're shared, satisfying both. The shared electrons hold the atoms together, a covalent bond. Some atoms can form multiple bonds. Carbon has 4 electrons in its outer shell and needs 8, so it forms 4 bonds. This versatility makes carbon the backbone of organic chemistry. It can bond with itself to form chains and rings, and with hydrogen, oxygen, nitrogen, and other elements to form millions of different compounds. Life is carbon-based because carbon's bonding flexibility allows the complex molecules necessary for biology. Bond strength varies. Some bonds are strong, requiring a lot of energy to break. Diamond is hard because its carbon atoms are covalently bonded in a strong, rigid lattice. Other bonds are weaker. Hydrogen bonds, for instance, are attractions between a slightly positive hydrogen atom in one molecule and a slightly negative atom in another. Water molecules hydrogen bond with each other, which is why water has a relatively high boiling point for such a small molecule, and why ice floats. Ice's crystal structure, held by hydrogen bonds, is less dense than liquid water. Understanding chemical bonds revolutionized chemistry. It explained why elements combine in specific ratios. Valence, the combining capacity of an element, depends on how many electrons it needs to gain, lose, or share to fill its outer shell. It allowed chemists to predict how molecules would form and what properties they'd have. It enabled the synthesis of new materials, plastics, pharmaceuticals, explosives, fertilizers, everything from nylon to aspirin, and it revealed the unity underlying chemistry's diversity. There are millions of known compounds, but they're all just atoms bonded in different arrangements. The same carbon atoms that make up coal, diamond, and graphite also make up DNA, proteins, and fats. The difference is how they're bonded. Change the bonds, and you change the substance entirely. Water is life-giving. hydrogen peroxide with just one extra oxygen atom is toxic. Ethanol gets you drunk. Methanol, differing by just one carbon atom, kills you. Chemical bonds are also dynamic. In your body, bonds are constantly forming and breaking. Enzymes catalyze reactions where bonds break in reactant molecules and form in new arrangements to create product. Molecules. Digestion is bond breaking, large molecules cleaved into smaller ones. Metabolism is bond rearranging, nutrients transformed into energy and building blocks. Growth and repair are bond forming, amino acids linked into proteins, nucleotides into DNA. You are, in a very real sense, a temporary arrangement of chemical bonds. The atoms in your body are ancient. Most are billions of years old, but the bonds holding them together in your particular configuration are recent, formed in the last few years at most, as your body continuously rebuilds itself. When you die, those bonds will break, and the atoms will be recycled, forming new bonds in soil, plants, other organisms. Nothing is permanent except the atoms themselves. The patterns, the arrangements, the bonds, those are temporary. We discovered that Earth is approximately 4.54 billion years old by measuring radioactive decay in rocks and meteorites. For most of history, Earth was thought to be young. Many cultures had creation myths, placing Earth's origin only thousands of years ago. In the 1600s, Archbishop James Ussher famously calculated, based on biblical genealogies, that Earth was created on October 23, 4004 BC, making it about 6,000 years old. But geologists studying rocks and fossils began to suspect Earth was much older. They saw thick layers of sediment that must have taken millions of years to accumulate. They found fossils of extinct creatures radically different from modern life. They observed slow geological processes, erosion, mountain building, continental drift, that required vast timescales. Lord Kelvin calculated, based on how long it would take Earth to cool from a molten state, that it was between 20 and 400 million years old. Better than 6,000 years, but still far too young. The breakthrough came with the discovery of radioactivity. Some atomic nuclei are unstable and decay, transforming into different elements while releasing particles and energy. Crucially, this decay happens at a predictable rate. Each radioactive isotope has a half-life, the time it takes for half of a sample to decay. Uranium-238, for instance, has a half-life of 4.5 billion years. After 4.5 billion years, half of any sample of U-238 will have decayed into lead-206. After another 4.5 billion years, half of the remainder will have decayed, and so on. This provides a clock. If you find a rock containing uranium and lead, you can measure the ratio of uranium to lead and calculate how long the uranium has been decaying, how old the rock is. By dating rocks from around the world, scientists determined that the oldest rocks on Earth are about 4 billion years old, but Earth itself is older than its oldest surviving rocks. Plate tectonics recycles the crust, subducting old rocks back into the mantle. The oldest rocks have been destroyed. To date Earth's formation, scientists turn to meteorites, remnants of the early solar system that haven't been altered by geological processes. By dating meteorites, they found ages consistently around 4.54 billion years. This is when the solar system formed, when the sun ignited, and planets, including Earth, coalesced from the surrounding disk of gas and dust. 4.54 billion years. It's almost incomprehensible. If you compressed Earth's history into a single year, complex life wouldn't appear until November. Dinosaurs wouldn't show up until mid-December. Humans would arrive at 11:36 p.m. on December 31st. All of recorded history would fit into the last minute of the year. Think about what Earth has witnessed in that time. It formed from a disk of debris orbiting a newborn star. It was bombarded by asteroids and comets, including a Mars-sized object that created the Moon. Its surface was molten, then cooled and solidified. An atmosphere formed, initially toxic, no oxygen. Oceans condensed from water vapor. Somewhere, somehow, the first life emerged. Simple single cells that reproduced and evolved. For billions of years, life remained microscopic. Then around 600 million years ago, complex multicellular life exploded in diversity. Plants colonized land. Animals followed. Mass extinctions periodically wiped out most species. Continents drifted, collided, broke apart. Ice ages came and went. And finally, just a moment ago in geological time, humans appeared. All of that history is recorded in rocks if you know how to read them. Fossils preserve ancient life. Rock layers tell stories of ancient seas, deserts, volcanic eruptions. Isotope ratios reveal temperatures, atmospheric compositions, even what ancient organisms ate. Earth is a library, and geologists are learning to read it. And the story isn't over. Earth continues to evolve. Continents are still drifting. Mountains are rising and eroding. New species are evolving, others going extinct. The planet is dynamic, ever-changing, responding to forces internal and external. Heat from radioactive decay, energy from the sun, the impacts of life itself. You're part of this story, a recent chapter in a very long book. Every atom in your body has been part of Earth for billions of years, cycling through rocks, oceans, atmosphere, countless organisms before ending up in you. You're not separate from Earth's history. You're continuous with it, made of the same matter, shaped by the same processes. Tonight, as you rest on this ancient world, consider the deep time beneath you. The rock under your home, under your city, might be millions or even billions of years old. It has seen so much, endured so much, witnessed transformations you can barely imagine. And it's still here, still solid, still supporting life, still turning, still orbiting the sun as it has for 4.54 billion years. There's something humbling and comforting in that perspective. Your problems, your worries, your joys and sorrows, they're real and they matter. But they're also tiny, fleeting, brief notes in a symphony billions of years long. The Earth will continue long after you're gone, indifferent but not hostile, simply existing, simply turning, following the laws of physics that have governed it since the beginning. And maybe that takes some pressure off. You don't have to carry the weight of eternity. You only have to be here now, for this brief moment, this tiny fraction of geological time. And that's enough. That's more than enough. It's everything. The discovery of the structure of benzene revealed that some molecules form ring shapes, opening up organic chemistry. Chemistry in the early 1800s was a puzzle. Scientists knew that organic compounds, substances from living things, were made mainly of carbon, hydrogen, and oxygen. But they couldn't figure out how these atoms arranged themselves. Why did carbon form such a bewildering variety of compounds? What was the structure? Benzene was particularly puzzling. Its chemical formula, C6H6, was known, but its structure was a mystery. It didn't behave like other hydrocarbons. It was unusually stable, resistant to reactions that should have broken it apart. Something about its structure made it special. In 1865, German chemist August Kekulé claimed he discovered the structure after a daydream. He was dozing by the fireplace when he envisioned atoms dancing, forming chains and structures. Then, he later wrote, he saw a snake biting its own tail, an Ouroboros, the ancient symbol of cyclical renewal. He woke with the realization: benzene wasn't a chain, it was a ring. Benzene is 6 carbon atoms arranged in a hexagonal ring, each carbon bonded to one hydrogen. The bonds between carbons alternate between single and double bonds, or rather, there's something in between. Resonance structures where electrons are delocalized, shared across the entire ring. This delocalization creates exceptional stability, explaining benzene's unique properties. The discovery revolutionized organic chemistry. Ring structures, aromatic compounds, were everywhere in nature and crucial for life. Amino acids like phenylalanine and tryptophan contain aromatic rings. DNA bases, adenine, guanine, thymine, cytosine, are rings. Chlorophyll, hemoglobin, many hormones and neurotransmitters, rings are fundamental to biochemistry. And they're not just biological. Benzene and its derivatives are key to industrial chemistry. Plastics like polystyrene, synthetic fibers like nylon, dyes, pharmaceuticals, explosives, pesticides. Many modern materials and chemicals are built on aromatic rings. Understanding ring structures also revealed why carbon chemistry is so diverse. Carbon can form chains, branches, rings, multiple rings fused together, 3-dimensional cages. It can bond with itself and with other elements in seemingly endless combinations. This versatility is why carbon is the basis of life, and why organic chemistry, the chemistry of carbon compounds, is a vast field with millions of known compounds. Kekulé's dream story is probably embellished or even fabricated. He didn't mention the snake dream until decades after the discovery, and historians are skeptical. But the discovery itself, however it happened, was real and important. It showed that molecular structure matters. The same atoms arranged differently have completely different properties. It showed that intuition and visualization are valuable in science, that sometimes you need to imagine structures you can't see to understand how they work. Today we can actually see molecular structures with scanning, tunneling, microscopes, and other techniques. Benzene's hexagonal ring isn't just a theory or a model. It's real, observable, a physical arrangement of atoms that we can image. The structure Kekulé proposed based on chemical behavior has been confirmed by direct observation, and the lesson extends beyond chemistry. Structure determines function. This is true in biology. Proteins fold into specific shapes that determine what they do. It's true in architecture. The arrangement of materials determines a building's strength and beauty. It's true in society. The structure of institutions shapes how they function. Patterns matter. Arrangements matter. The way components connect determines what the whole can do. Tonight, as you rest, benzene rings are everywhere, in and around you. The molecules in your DNA contain them. The proteins in your body include amino acids with aromatic rings. The materials around you, plastics, fabrics, maybe medications you've taken, many contain benzene-derived compounds. These rings, these simple hexagons of carbon, are woven into the fabric of modern life and ancient biology alike. And maybe there's a metaphor in the ring itself, a structure with no beginning or end, each part connected to the next, a cycle, a wholeness. Maybe that's how we should think about knowledge, about communities, about life, not as linear progressions, but as interconnected systems where everything connects back to everything else, where there's no true starting point, just continuous relationships, continuous cycles, patterns that persist because they're stable, because they work, because they're beautiful in their symmetry and completeness. And as you drift towards sleep, maybe you can imagine yourself as part of a larger ring, connected to others, part of a pattern that extends beyond you, stable and enduring, a structure that holds together because each piece supports the others. And maybe that's enough, to be one carbon atom in the benzene ring of existence, bonded to neighbors, sharing electrons, part of something stable and beautiful and whole. We learned that distant supernovae serve as standard candles that let us measure cosmic distances with remarkable precision. One of the hardest problems in astronomy is measuring distances. When you look at a star, you can see how bright it appears, but you don't know if it's bright because it's intrinsically luminous, or because it's close, dim because it's inherently faint, or because it's far away. It's like seeing car headlights at night. Are they from a nearby motorcycle or a distant truck? Astronomers needed standard candles, objects with known intrinsic brightness. If you know how bright something actually is, you can compare that to how bright it appears and calculate its distance. The dimmer it looks, the farther away it must be. In the 1920s, Henrietta Swan Leavitt discovered that a certain type of variable star, Cepheid variables, had a relationship between their pulsation period, how long they take to brighten and dim, and their intrinsic brightness. Measure the period, and you know the luminosity. Measure the apparent brightness, and you can calculate the distance. Edwin Hubble used Cepheids to measure distances to nearby galaxies, proving they were island universes, far beyond the Milky Way. But Cepheids are only visible in relatively nearby galaxies. For greater distances, astronomers needed brighter standard candles. They found them in type Ia supernovae, exploding stars that all reach roughly the same peak brightness. Type Ia supernovae occur when a white dwarf star in a binary system accretes matter from its companion. When the white dwarf reaches a critical mass, about 1.4 times the Sun's mass, the Chandrasekhar limit, it can no longer support itself against gravity. It collapses, triggering runaway fusion that tears the star apart in a catastrophic explosion. Because they all explode at the same mass, they all release roughly the same energy and reach roughly the same peak brightness, about 5 billion times brighter than the Sun. That makes them visible across enormous distances. A type Ia supernova briefly outshines its entire host galaxy. Astronomers can spot them in galaxies billions of light years away, measure their apparent brightness, and calculate the distance. In the 1990s, 2 teams of astronomers used type Ia supernovae to measure distances to faraway galaxies. They expected to find that the universe's expansion was slowing, pulled back by gravity. Instead, they discovered the expansion is accelerating. Distant supernovae were fainter than expected, meaning they were farther away than they should be if expansion were constant or slowing. This led to the discovery of dark energy and won the 2011 Nobel Prize in Physics. Standard candles have revolutionized our understanding of the universe's size and structure. We now know the universe is about 93 billion light years in diameter, the observable part anyway. We know it's 13.8 billion years old. We know it's expanding and accelerating. None of this would be possible without accurate distance measurements, and supernovae are among our best tools. But supernovae are also just beautiful, cosmically speaking. When a star explodes, it briefly becomes one of the brightest objects in the universe. It outshines billions of normal stars. For a few weeks, it's visible across the cosmos, a beacon announcing the death of a star and the birth of a supernova remnant that will enrich space with heavy elements, possibly triggering new star formation, continuing the cycle of stellar life and death. These explosions are rare, only a few per galaxy per century. But in a universe with hundreds of billions of galaxies, supernovae are occurring constantly somewhere. As you lie there tonight, somewhere in the cosmos, a white dwarf is reaching critical mass. Somewhere, fusion is accelerating out of control. Somewhere, a star is tearing itself apart, releasing more energy in seconds than our sun will emit in its entire 10 billion year lifetime, becoming a brief, brilliant light in the darkness, visible across billions of light years to astronomers who will use it to measure the universe, to understand its expansion, to probe the nature of dark energy. And maybe there's poetry in that. Stars die, yes, but their deaths illuminate. They become lighthouses, guiding us toward understanding. Even in ending, they serve a purpose, teaching us about the cosmos, revealing secrets of distance and expansion and the fate of the universe. Nothing is wasted. Even destruction creates knowledge, creates elements, creates possibilities for new stars, new planets, new life. The universe recycles everything, transforms everything, finds use for everything. And maybe that's a comforting thought as you drift towards sleep, that endings can be meaningful, that even in dying, things can shine brighter than ever, can leave a legacy that echoes across billions of years and billions of light years, teaching, illuminating, guiding those who come after toward greater understanding. And maybe that's enough, to shine when you can, to illuminate what you're able, and to trust that even your ending might light the way for someone, somewhere, sometime. The discovery of the greenhouse effect showed that certain gases trap heat in the atmosphere, keeping Earth warm enough for life. Earth should be colder. If you calculate the temperature our planet should have based on the distance from the sun and the amount of sunlight we receive, you get about 0 degrees, 18 degrees. That's well below the freezing point of water. Earth should be a frozen ice ball, hostile to life as we know it. But Earth's average temperature is actually about 59 degrees, 15 degrees. What's keeping us warm? The answer is the greenhouse effect, discovered in the 1820s by French mathematician Joseph Fourier. He calculated that Earth should be colder than it is, and proposed that the atmosphere must be trapping heat somehow. In the 1850s and 60s, scientists like John Tyndall discovered that certain gases, carbon dioxide and water vapor especially, absorb infrared radiation while allowing visible light to pass through. Here's how it works. Sunlight, mostly visible light and ultraviolet, passes through the atmosphere and warms Earth's surface. The surface radiates heat back out as infrared radiation, but greenhouse gases in the atmosphere absorb much of that infrared, then re-radiate it in all directions, including back toward the surface. This traps heat, keeping Earth warmer than it would otherwise be. It's called the greenhouse effect, by analogy to a greenhouse, though the mechanism is different. Greenhouses stay warm mainly by preventing warm air from escaping. And it's essential for life. Without it, most of Earth's water would freeze. Oceans would be ice. Life, if it existed at all, would be restricted to isolated warm spots near volcanic vents. The main greenhouse gases are water vapor, carbon dioxide, methane, nitrous oxide, and ozone. Water vapor is the most abundant and has the strongest effect, but its concentration varies naturally with temperature. Carbon dioxide is second most important and is more stable, making it a key long-term climate regulator. For millions of years, Earth's CO2 levels fluctuated naturally. Volcanic eruptions released it, weathering of rocks, and photosynthesis removed it. These processes roughly balanced, keeping climate relatively stable, with some notable exceptions like ice ages. But since the Industrial Revolution, humans have been burning fossil fuels, coal, oil, natural gas, releasing carbon that was locked underground for millions of years. Atmospheric CO2 has increased from about 280 parts per million in 1800 to over 420 parts per million today. This enhanced greenhouse effect is warming the planet faster than at any time in human history, causing climate change with consequences we're only beginning to grapple with. Rising seas, changing weather patterns, ecosystem disruptions. The greenhouse effect itself isn't bad, it's necessary, but too much can be harmful, as Venus demonstrates. Venus has a thick CO2 atmosphere that creates a runaway greenhouse effect, heating the surface to over 900 degrees, 475 degrees, hot enough to melt lead. Venus may once have had oceans, but the greenhouse effect boiled them away, and the planet became a hellish desert. Earth isn't becoming Venus. Our situation is different, but the principle is the same. Change the atmosphere's composition, and you change the climate. And climate affects everything: agriculture, water supplies, habitability of coastal regions, ecosystems, weather extremes. Understanding the greenhouse effect is crucial for understanding and addressing climate change. It's also a reminder of how interconnected Earth's systems are. The atmosphere regulates temperature, which affects oceans and ice sheets, which affect ocean currents and weather patterns, which affect ecosystems and agriculture, which affect human societies. Change one part, and ripples spread through the entire system. Tonight, as you lie warm and comfortable, the greenhouse effect is working, keeping Earth's temperature stable enough for life, for liquid water, for you. It's a delicate balance, maintained by the composition of the atmosphere, by the cycling of carbon through rocks and oceans and living things, by processes that have kept Earth habitable for billions of years. And maybe there's a lesson in that balance. Systems have equilibria, stable states they naturally tend toward. Push them too hard or too fast, and they shift to new equilibria that might be less hospitable. But with understanding and care, equilibria can be maintained or gently guided toward better states. It takes awareness, effort, collaboration. It takes recognizing that we're not separate from the system, but part of it, that our actions have consequences, that the atmosphere wrapping around the planet is thin and precious and shared by everyone. We found that some materials become superconductors at low temperatures, conducting electricity with zero resistance. Imagine a wire carrying electric current. Normally, the wire resists the flow of electrons, converting some of the electrical energy into heat. This is why wires get warm, why power lines lose energy over long distances, why your phone charger feels warm to the touch. Resistance is just a fact of life for normal conductors. But in 1911, Dutch physicist Heike Kamerlingh Onnes discovered something remarkable. He was studying the electrical resistance of mercury at very low temperatures, cooling it with liquid helium to just a few degrees above absolute zero. At 4.2 Kelvin, 452 degrees Celsius, the resistance didn't just decrease, it vanished completely. The mercury had become a superconductor. In a superconductor, electrons flow without any resistance whatsoever. If you start a current flowing in a superconducting loop, it will keep flowing forever, without any power source, without losing any energy. Experiments have shown superconducting currents lasting for years without measurable decay. It's the closest thing to perpetual motion that exists in nature. How does this happen? At normal temperatures, electrons moving through a conductor collide with atoms, losing energy as heat. That's resistance. But at very low temperatures in certain materials, something strange occurs. Electrons pair up through interactions with the atomic lattice, forming what are called Cooper pairs. These pairs can move through the lattice without scattering, without resistance. They form a coherent quantum state, all moving together, undisturbed by the atomic vibrations that normally create resistance. Superconductivity has remarkable properties beyond zero resistance. Superconductors expel magnetic fields, the Meissner effect. If you place a magnet near a superconductor, the superconductor generates currents that create an opposing magnetic field, pushing the magnet away. This can cause magnetic levitation, a magnet floating above a superconductor, held up by magnetic repulsion. It's the principle behind maglev trains that float above their tracks, eliminating friction. The catch is temperature. Most superconductors only work at extremely low temperatures, close to absolute zero, requiring expensive liquid helium cooling. This limits practical applications. Scientists have searched for decades for room temperature. Superconductors, materials that would be superconducting at everyday temperatures. Progress has been slow but real. In 1986, high-temperature superconductors were discovered, materials that become superconducting at liquid nitrogen temperatures, 320 degrees Celsius. That's still cold, but much easier and cheaper to achieve than liquid helium temperatures. In recent years, researchers have found materials that are superconducting at even higher temperatures, though often only under extreme pressures. If room temperature, ambient pressure superconductors could be found, the implications would be revolutionary. Power transmission without loss, electricity generated anywhere could be delivered anywhere without waste. Powerful magnets for fusion reactors, particle accelerators, MRI machines, all without energy-intensive cooling. Ultra-fast, energy-efficient computers, levitating vehicles, technologies we can barely imagine. For now, superconductors are used where the cooling cost is justified. MRI machines use superconducting magnets to create the strong, stable magnetic fields needed for imaging. Particle accelerators like the Large Hadron Collider use superconducting magnets to steer particles. Some experimental power cables use superconductors, and scientists continue searching for better materials, for the holy grail of room temperature superconductivity. Superconductivity is also just deeply weird. It's a macroscopic quantum phenomenon. Quantum effects that are usually only visible at atomic scales become apparent in objects large enough to see and touch. A superconductor is, in a sense, a single quantum state extending across trillions of atoms, all acting in perfect unison. It's matter behaving in ways that defy classical physics, that hint at the strange rules governing the quantum world. Tonight, as you rest, electricity is flowing through wires all around you, in your walls, in your devices, in power grids spanning continents. And that electricity encounters resistance, loses energy, creates heat. It's inefficient but manageable. But somewhere, in laboratories and medical facilities, superconductors are at work, cooled to frigid temperatures, carrying current without loss, defying the usual rules, operating in a quantum regime where resistance simply doesn't exist. And maybe there's a metaphor there, or at least a dream. What if we could live our lives with less resistance? Not zero resistance. That might not be possible or even desirable, might require conditions too extreme to sustain, but less friction, less wasted energy, less struggle against the inevitable obstacles. Maybe that's what wisdom is, in a way. Learning to move through life with less resistance, to flow around obstacles rather than fighting them, to conserve energy for what matters, to find the path of least resistance without sacrificing direction. And maybe rest itself is a kind of superconductivity, a state where resistance drops away, where energy flows freely, where the usual struggles cease for a while, and you exist in a simpler, more coherent state, all parts of yourself aligned and flowing together, undisturbed. So sink into that state now. Let resistance fade, let the day's struggles evaporate, and exist for a while in this cooler, quieter state where everything flows easily, effortlessly, without friction. And maybe that's what sleep is, a nightly return to superconductivity, a chance to exist without resistance, to restore, to realign, to prepare for tomorrow when resistance will return, but when perhaps you'll be better equipped to navigate it, refreshed by this brief sojourn in the frictionless realm of dreams. The discovery of prions revealed that proteins alone, without DNA or RNA, can cause infectious diseases like mad cow disease. For most of history, infections were thought to be caused by living organisms, bacteria, viruses, fungi, parasites. Even viruses, though not technically alive, contain genetic material, DNA or RNA, that carries instructions for making more viruses. The dogma was clear. Infection requires genetic material. Then came prions, and everything got stranger. In the 1980s, Stanley Prusiner was studying a group of mysterious diseases, scrapie in sheep, Creutzfeldt-Jakob disease in humans, others. These diseases caused progressive neurological damage, leaving the brain riddled with holes, sponge-like. They were infectious. You could transmit them from one animal to another, but no one could find the infectious agent. No bacteria, no virus, no genetic material. Prusiner proposed something radical. The infectious agent was a protein. Not a virus with a protein coat, but just protein, with no DNA or RNA at all. He called these infectious proteins prions, short for proteinaceous infectious particles. The idea was met with skepticism and ridicule. How could a protein be infectious? Proteins are just molecules, strings of amino acids folded into specific shapes. They don't reproduce. They don't contain information. How could they cause disease? Here's how. Prions are misfolded versions of a normal protein found in neurons. The normal protein has a particular shape. The prion version has a different, abnormal shape. And here's the key. When a prion encounters a normal protein, it can cause the normal protein to misfold into the prion shape. That newly misfolded protein can then convert more normal proteins. It's a chain reaction, a self-propagating cascade of misfolding. As prions accumulate, they clump together, forming aggregates that damage and kill neurons. The brain develops holes, loses function. Symptoms progress: memory loss, personality changes, loss of coordination, dementia. And it's always fatal. There's no cure. Mad cow disease, bovine spongiform encephalopathy, is caused by prions. It emerged in the UK in the 1980s when cattle were fed meat and bone meal from other cattle, including infected animals. The prions spread through the cattle population. Then, horrifyingly, the disease jumped to humans who ate infected beef, causing a variant of Creutzfeldt-Jakob disease. More than 200 people died before the outbreak was controlled. Prions are terrifying, partly because they're so hard to destroy. Normal sterilization techniques that kill bacteria and inactivate viruses, heat, radiation, disinfectants, don't reliably destroy prions. They're just proteins, and proteins are very stable. You need extreme conditions, prolonged high heat, strong bases or acids, to denature them. Prusiner won the Nobel Prize in 1997 for discovering prions, though controversy lingered for years. Many scientists remained skeptical until the evidence became overwhelming. Now prions are accepted as a real, if bizarre, category of infectious agent. And they're not just exotics. Prion-like mechanisms may play a role in more common diseases. Alzheimer's disease involves the accumulation of misfolded amyloid beta and tau proteins. Parkinson's involves misfolded alpha-synuclein. These proteins seem to spread from cell to cell, converting normal proteins to abnormal forms, much like prions. They're not infectious in the traditional sense. You can't catch Alzheimer's from someone. But the underlying mechanism is similar: misfolded proteins propagating their abnormal shape. It's a strange and unsettling concept. Information of a sort can be encoded not in genetic sequences but in protein shapes. A misfolded protein carries information about its abnormal shape and can propagate that information by causing other proteins to adopt the same shape. It's a dark mirror of how life works, information being copied and spread, but with destructive consequences instead of constructive ones. Tonight, as you rest, your neurons are full of proteins, folded into precise shapes that allow them to function: ion channels, receptors, structural proteins, enzymes. For the vast majority of people, these proteins maintain their proper shapes, doing their jobs, keeping your brain working. The system is robust, resilient, with mechanisms to detect and destroy misfolded proteins. But the existence of prions is a reminder of fragility, of how much depends on shape, on structure, on the precise three-dimensional arrangement of atoms in molecules. Change the shape slightly, and function disappears, or worse, turns destructive. Life is precise, and precision is vulnerable, yet also remarkable. The fact that proteins fold correctly billions of times, in trillions of cells, across decades, with only rare failures, that's astonishing. Your body is a marvel of quality control, of molecular machinery that mostly works, mostly preserves the right shapes, mostly maintains order against the constant threat of entropy and misfolding. We learned that the universe is flat, or very nearly flat on the largest scales, like an infinite sheet rather than a sphere or saddle. When we talk about the shape of the universe, we're not talking about what it looks like from the outside. There is no outside. We're talking about the geometry of space itself, how distances and angles work, how parallel lines behave. It's geometry on the grandest possible scale. There are three possibilities for the overall shape of the universe. It could be positively curved, like the surface of a sphere. In such a universe, if you traveled far enough in what seemed like a straight line, you'd eventually return to your starting point. Parallel lines would eventually converge. The universe would be finite but without edges. You could travel forever without hitting a boundary, but there would be a limited amount of space. Or the universe could be negatively curved, like a saddle. In this geometry, parallel lines diverge. Space curves away from itself. The universe would be infinite, expanding outward in all directions without limit. Triangles would have angles that add up to less than 180 degrees. Or the universe could be flat, not flat like a pancake, still three-dimensional, but flat in the sense that parallel lines stay parallel. Triangles have angles that add up to exactly 180 degrees. The rules of Euclidean geometry we learned in school apply. A flat universe is infinite, stretching on forever in all directions. For decades, determining which geometry our universe has was one of cosmology's central questions. The answer depends on the density of matter and energy. Too much density, and gravity curves space into a sphere. Too little, and space curves into a saddle. Just the right amount, the critical density, produces a flat universe. Measurements of the cosmic microwave background, particularly from satellites like WMAP and Planck, have given us the answer. The universe is flat, or so close to flat that we can't detect any curvature. The density is within about 1% of the critical density. Parallel lines stay parallel. Space extends infinitely in all directions. This raises questions. Why is the density so precisely balanced? If it were even slightly different, just one part in a trillion different shortly after the Big Bang, the universe would be noticeably curved today. This seems like an incredible coincidence. Inflation theory offers an explanation. In the first fraction of a second after the Big Bang, space expanded exponentially, faster than light, growing by a factor of at least 10^26. This expansion would flatten any initial curvature, just as inflating a balloon makes its surface appear flatter from the perspective of something tiny on that surface. If the universe inflated enough, any curvature would be stretched so flat that we couldn't detect it, even if the actual universe is curved on scales far larger than we can observe. A flat universe has implications for the future. It will expand forever. Galaxies will continue moving apart, accelerated by dark energy. There's no big crunch, no eventual collapse back into a singularity. The universe will grow colder, darker, more dilute, until eventually stars burn out, black holes evaporate, and everything reaches a state of maximum entropy. Heat death, the final equilibrium where nothing interesting can happen anymore. But that's trillions upon trillions of years away. For now, we live in a flat universe, where geometry makes intuitive sense, where the angles of triangles behave as expected, where space stretches infinitely in all directions. It's simultaneously comforting. The rules we learned apply, and humbling. Infinite space means infinite possibilities, infinite places, perhaps infinite variations, all following the same geometric rules, all part of the same vast, flat cosmos. Tonight, as you lie there, you're on a small planet in an infinite flat universe. Above you, beyond the atmosphere, space extends without limit. There's no edge to reach, no boundary to cross. If you could travel infinitely fast in any direction, you'd never run out of space, never loop back to where you started, never reach a wall or a corner. Just more space, more galaxies, more stars, forever. It's dizzying if you think about it too much, but maybe it's also freeing. In an infinite, flat universe, there's room for everything, for every possibility, for every story, for every moment. You're here, now, occupying one tiny region of that infinite space, and that's enough. You don't need to explore it all, comprehend it all, reach its boundaries. You just need to be here, in this moment, in this small corner of infinity, resting peacefully under an endless sky, part of a cosmos so vast it defies imagination, yet so orderly it follows simple geometric rules. And maybe there's peace in that, in knowing the universe is both incomprehensibly large and elegantly simple, both infinite and flat, both boundless and comprehensible. So rest now, held by Earth's gravity, surrounded by infinite flat space, part of a geometry so grand and so simple that even infinity makes sense within it. The discovery of neurotransmitters showed how chemical messengers enable communication between neurons in the brain. Your thoughts are chemicals. Every sensation, every memory, every emotion, every decision, all of it arises from neurons communicating with each other. And that communication happens through chemicals called neurotransmitters. We've talked about how neurons generate electrical signals, waves of depolarization that travel down axons. But when that electrical signal reaches the end of the neuron, it can't jump directly to the next neuron. There's a gap, the synapse, about 20 nanometers wide. The signal has to cross that gap somehow. In the early 1900s, scientists debated whether neural communication was electrical or chemical. Some argued that electricity must somehow jump the gap. Others proposed that neurons released chemical substances that carried the signal. The debate was settled by Otto Loewy in an elegant experiment in 1921. He stimulated the vagus nerve of a frog's heart, which slowed the heart rate. He collected the fluid around that heart and applied it to a second heart, which also slowed. Something chemical had been released by the nerve and carried in the fluid. Loewy called it Vagusstoff, later identified as acetylcholine, the first known neurotransmitter. Here's how it works. When an electrical signal reaches the end of a neuron, it triggers the release of neurotransmitter molecules stored in tiny vesicles. These molecules diffuse across the synaptic gap and bind to receptors on the next neuron. Depending on the neurotransmitter and receptor, this either excites the next neuron, making it more likely to fire, or inhibits it, making it less likely to fire. One neuron might receive inputs from thousands of others, some excitatory, some inhibitory. Whether it fires depends on the balance of all these inputs. Dozens of neurotransmitters have been discovered. Each has different effects, acts on different receptors, plays different roles. Acetylcholine is involved in muscle control, attention, and memory. Dopamine is associated with reward, motivation, and movement. Parkinson's disease results from dopamine-producing neurons dying. Serotonin regulates mood, sleep, and appetite. Many antidepressants work by increasing serotonin levels. GABA is the main inhibitory neurotransmitter, calming neural activity. Anxiety medications often enhance GABA signaling. Glutamate is the main excitatory neurotransmitter, crucial for learning and memory. Neurotransmitters are why drugs affect the mind. Caffeine blocks adenosine receptors, preventing the signal that makes you feel tired. Nicotine mimics acetylcholine, stimulating those receptors. Opioids bind to opioid receptors, blocking pain signals and producing euphoria. Alcohol enhances GABA and inhibits glutamate, producing sedation. Psychedelics like LSD bind to serotonin receptors, altering perception and thought. SSRIs like Prozac prevent serotonin reuptake, leaving more serotonin in synapses to bind receptors. Mental illnesses often involve neurotransmitter imbalances or receptor dysfunctions. Depression may involve low serotonin or dopamine. Schizophrenia may involve excessive dopamine activity in certain brain regions. ADHD may involve dopamine and norepinephrine dysregulation. Understanding neurotransmitters has led to treatments, though they're imperfect. Brains are complex, and adjusting one neurotransmitter affects many processes, causing side effects. What's fascinating is how chemicals create subjective experiences. When dopamine is released in your brain's reward centers, you feel pleasure, motivation, desire. When serotonin levels drop, you might feel sadness or anxiety. When adrenaline floods your system, you feel alert, energized, ready for action. These subjective feelings, so immediate and personal, are the result of molecules binding to proteins, triggering cascades of chemical reactions, altering the patterns of neural firing. It's reductive to say you are just chemicals, but it's also true that chemicals shape experience profoundly. Alter the chemicals, and you alter the experience. This doesn't diminish the reality of feelings. Love is no less real because it involves oxytocin and dopamine. It just means that subjective experience and physical processes are two sides of the same coin, two ways of describing the same phenomenon. Tonight, as you settle into sleep, neurotransmitters are shifting. Adenosine, which has been building up all day, is binding to receptors, making you feel drowsy. Melatonin is being released by your pineal gland, signaling that it's night, promoting sleep. As you drift off, your brain will cycle through different sleep stages, each characterized by different patterns of neurotransmitter release and neural activity. Serotonin and norepinephrine levels drop, allowing REM sleep with its vivid dreams. Growth hormone is released, promoting tissue repair. Neurotransmitters involved in memory consolidation strengthen some synapses and weaken others, integrating the day's experiences. You're a chemical symphony, and sleep is one movement of that symphony. A time when the balance shifts, when certain instruments quiet while others play, when the music changes character but continues, always continues, keeping you alive, keeping you you. And maybe there's something beautiful in understanding this, that your inner life, so rich and complex, emerges from the elegant dance of molecules, from neurotransmitters finding their receptors, from chemistry becoming consciousness. And as you drift now toward sleep, trust in that chemistry, in the ancient systems that regulate wakefulness and rest, in the molecules that will guide you into dreams and eventually bring you back to waking. You're in good hands, chemical hands perhaps, but hands that have been refined by billions of years of evolution, hands that know what they're doing. So let go, let the neurotransmitters do their work and rest. We found that some particles have antimatter counterparts with opposite charge, and when they meet, both annihilate in pure energy. For every particle in the universe, there's a mirror image, antimatter. An electron has a negative charge. Its antimatter counterpart, the positron, has a positive charge. A proton is positive, an antiproton is negative. For every matter particle, there's an antimatter particle with opposite charge, but otherwise identical properties. Antimatter was predicted by Paul Dirac in 1928. He was working on a quantum equation describing electrons and found that it had two solutions, one for normal electrons, one for something with the opposite charge. He initially thought it might be the proton, but the math didn't work. Then, in 1932, Carl Anderson discovered positrons in cosmic rays, proof that Dirac's prediction was real. When a particle meets its antiparticle, they annihilate. Their masses convert entirely to energy, according to EMC2. An electron and positron annihilating produce two gamma-ray photons, pure electromagnetic radiation, carrying away the energy that was locked in their mass. It's the most efficient energy conversion possible. 100% of mass becomes energy, far more efficient than nuclear fission or fusion. This raises a profound question. Where is all the antimatter? When the universe began, the Big Bang should have created equal amounts of matter and antimatter. And if that were true, everything would have annihilated shortly after creation, leaving a universe of pure energy with no atoms, no stars, no planets, no life. Obviously, that didn't happen. We're here, made of matter. Stars and galaxies are made of matter. We found no evidence of significant antimatter in the universe, no antimatter galaxies, no annihilation flares that would occur at the boundaries between matter and antimatter regions. So why does matter dominate? There must have been some asymmetry in the early universe, some process that produced slightly more matter than antimatter. Perhaps one extra matter particle for every billion matter-antimatter pairs. The pairs annihilated, producing the cosmic microwave background radiation, but the tiny excess of matter survived, eventually forming everything we see. What caused this asymmetry? We don't know. It's one of physics' great unsolved problems. There must be some difference in how matter and antimatter behave, some violation of symmetry that favored matter. Experiments have found small differences in how certain particles and their antiparticles decay, but not enough to explain the matter-antimatter imbalance. The answer might involve physics beyond the standard model, processes that occurred in the first fractions of a second after the Big Bang. Antimatter isn't just theoretical. We can create it and study it. Particle accelerators produce antimatter regularly. PET scanners, positron emission tomography, used in medicine work by detecting positrons emitted by radioactive tracers. Antimatter is difficult and expensive to produce and even harder to store. It annihilates instantly on contact with normal matter, but it's real and useful. There are proposals to use antimatter as spacecraft fuel. The energy density is unmatched. A few milligrams could power a spacecraft to Mars. But production and storage challenges are enormous. We've only created tiny amounts, nanograms, and storing it requires magnetic traps to keep it away from the walls of any container. Antimatter also appears in nature, albeit rarely. Certain radioactive decays produce positrons. Thunderstorms and lightning produce antimatter through interactions of gamma rays with matter. Even bananas emit positrons occasionally from the radioactive decay of potassium-40. The existence of antimatter is a reminder of symmetries in nature. For every action, an equal and opposite reaction. For every particle, an antiparticle. The universe seems to love balance, dualities, mirror images. Yet the universe we inhabit is fundamentally asymmetric, dominated by matter, not an equal mix. Understanding why might reveal deep truths about the universe's origin and evolution. Tonight, as you rest, You're made entirely of matter. No antimatter in your body. If there were, you'd annihilate in a flash of gamma rays. The atoms that make you up are stable, their particles coexisting peacefully. No antiparticles to threaten them. You're part of the matter-dominated universe, a descendant of that tiny excess that survived the primordial annihilation, heir to an asymmetry whose origin remains mysterious. And maybe there's something poignant in that. We exist because of an imbalance, an imperfection, a slight tilt toward matter in the first moments of creation. Perfect symmetry would have meant perfect annihilation. A universe of pure radiation, with no structure, no complexity, no life. We're here because something broke the symmetry, because the universe chose matter over balance, existence over perfection. And maybe that's a lesson, that life, growth, creation all require breaking perfect symmetries, embracing imbalances, accepting that perfection might be sterile, while imperfection is fertile. So rest now in your asymmetric, imperfect, matter-dominated form, grateful for the tiny excess that made your existence possible, holding gently the knowledge that you are, in the deepest sense, an accident of cosmic asymmetry, a consequence of broken symmetry, a child of imbalance. And maybe that's beautiful, to exist not because everything was perfect, but because something was just slightly off, just enough off to allow stars and planets and people and thoughts and dreams. And tonight, that's enough. The discovery of restriction enzymes gave us molecular scissors that cut DNA at specific sequences, launching genetic engineering. DNA is a long molecule, sometimes billions of base pairs long in a single chromosome. For decades after its structure was discovered, scientists could observe it, sequence it slowly and laboriously, but not manipulate it precisely. They couldn't cut it in specific places, couldn't insert new sequences, couldn't edit the code of life with precision. Then, in the 1960s and 70s, scientists discovered restriction enzymes, molecular scissors found in bacteria. Bacteria produce these enzymes to defend against viruses. When a virus injects its DNA into a bacterium, restriction enzymes recognize specific sequences in the viral DNA and cut it, destroying the invader. The bacterium protects its own DNA by chemically modifying those same sequences so the enzymes don't cut them. Each restriction enzyme recognizes a specific DNA sequence, typically 4 to 8 base pairs long. EcoRI, one of the most commonly used, recognizes the sequence GATTC and cuts between the G and A. BAMHI recognizes GGATCC and cuts there. Hundreds of restriction enzymes have been isolated from different bacteria, each recognizing different sequences. This gave scientists the tools they needed. Want to cut a gene out of one organism's DNA? Use restriction enzymes to make precise cuts at the gene's boundaries. Want to insert that gene into another organism? Cut the recipient DNA with the same enzymes, creating compatible ends, then splice the pieces together with another enzyme called DNA ligase. This is recombinant DNA technology, the foundation of genetic engineering. The first practical application came in 1978 when scientists inserted the human insulin gene into bacteria, creating the first genetically engineered drug. Those bacteria became insulin factories, producing human insulin more efficiently and safely than extracting it from animal pancreases. Today, most insulin is made this way, as are many other drugs, human growth hormone, clotting factors for hemophiliacs, vaccines. Restriction enzymes enabled the creation of GMO crops. plants with inserted genes for pest resistance, herbicide tolerance, improved nutrition. They enabled gene therapy research, where corrected genes are inserted into patients' cells to treat genetic diseases. They enabled CRISPR and other modern gene editing techniques, which use similar principles, but with even greater precision. They also enabled DNA fingerprinting. Cut DNA from a crime scene and a suspect with restriction enzymes, and you get patterns of fragments. Compare the patterns, and you can identify or exclude suspects with near certainty. This has revolutionized forensics, solved countless crimes, exonerated innocent people. Restriction enzymes are part of why biology became an engineering discipline. We went from passively observing life to actively modifying it, from accepting the genetic lottery to rewriting the code. This power brings ethical questions. Should we modify human embryos to eliminate genetic diseases, create new organisms, patent life forms, bring back extinct species? These aren't easy questions, and society is still grappling with them. But the scientific impact is undeniable. Restriction enzymes and the techniques they enabled have transformed our understanding of genetics, evolution, development, disease. We can study how genes work by removing them and observing what changes. We can trace evolutionary relationships by comparing DNA sequences. We can diagnose genetic diseases by detecting specific mutations. And it all started with the bacterial defense system, millions of years old, evolved to protect single-celled organisms from viruses. Bacteria couldn't have known that their restriction enzymes would someday be used by humans to revolutionize medicine and agriculture. Evolution doesn't plan, doesn't foresee. It just tinkers, trying random variations, keeping what works for survival. And sometimes those solutions, refined over eons, turn out to be useful in ways that have nothing to do with their original function. Tonight, as you rest, restriction enzymes and their descendants are at work in laboratories around the world, cutting DNA, enabling research, producing medicines, editing genes. They're being used to study diseases, develop treatments, improve crops, understand life's machinery. These molecular scissors, borrowed from bacteria, are cutting and pasting the code of life, rewriting evolution's 4-billion-year-old text, enabling possibilities that would have seemed like magic just decades ago. And maybe there's wonder in that, in how a bacterial defense mechanism became a tool for human innovation, in how evolution's old solutions become starting points for new technologies, in how understanding nature allows us to work with it, to borrow its tools, to gently or not so gently modify the living world. It's a power that demands wisdom, care, ethical consideration, but it's also a power that can heal, can feed, can illuminate. And as you drift towards sleep, maybe hold that thought, that knowledge can be power, that power can be used well or badly, and that we're all responsible for how we use the tools we've been given, the scissors that cut, the ligases that join, the ability to read and edit the book of life. It's a heavy responsibility, but also a privilege. And maybe that's worth thinking about as you rest, as your own DNA quietly does its work. Unedited, natural, ancient, holding the information that makes you you, written in a language we're only beginning to truly read, and, with care and humility, beginning to learn how to write. We learned that black holes actually emit radiation through a quantum process at their event horizons, called Hawking radiation. Black holes are supposed to be black. They trap everything, even light, allowing nothing to escape. Once something crosses the event horizon, the point of no return, it's gone forever, pulled toward the singularity at the center by gravity so intense that not even the fastest thing in the universe, light, can overcome it. But in 1974, Stephen Hawking discovered something remarkable. Black holes aren't completely black. They emit radiation, now called Hawking radiation, and over unimaginably long timescales, they can evaporate completely. Here's how it works. Quantum mechanics says that empty space isn't truly empty. It's full of quantum fluctuations, where pairs of particles and antiparticles constantly pop into existence and then annihilate each other, all within a tiny fraction of a second. Normally, these virtual particles appear and disappear so fast that they can't be observed directly. But near a black hole's event horizon, something strange can happen. A particle-antiparticle pair appears just outside the horizon. Before they can annihilate, one falls into the black hole, while the other escapes into space. From outside, it looks like the black hole is emitting a particle. The particle that fell in had negative energy from the black hole's perspective, so the black hole loses a tiny bit of mass. The escaped particle is real and carries energy away. This Hawking radiation is incredibly faint for large black holes. A black hole with the mass of the Sun would have a temperature of only 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background. It would take 1067 years to evaporate, far longer than the current age of the universe. Larger black holes are even colder and evaporate even more slowly, but smaller black holes would be hotter and evaporate faster. A black hole with the mass of a mountain would evaporate in about the current age of the universe. A black hole with the mass of a large building would evaporate in seconds, releasing energy equivalent to millions of nuclear bombs. No such small black holes are known to exist. They can't form from collapsing stars, but they might have formed in the early universe under extreme conditions. Hawking radiation revealed a deep connection between quantum mechanics, general relativity, and thermodynamics. Black holes have temperature and entropy. They're thermodynamic objects, not just gravitational ones. The entropy of a black hole is proportional to the area of its event horizon, not its volume, which hints at profound truths about the nature of information and space. This leads to the black hole information paradox. Quantum mechanics says information can't be destroyed. The universe keeps a record of everything. But if something falls into a black hole and the black hole evaporates, where does the information go? Hawking radiation appears to be thermal, random, carrying no information about what fell in, but that would violate quantum mechanics. Physicists have debated this for decades. Some think information is preserved in subtle correlations in the Hawking radiation. Others think it's stored somehow on the event horizon. Recent work suggests information might leak out through quantum entanglement between the inside and outside of the black hole. But there's no consensus yet. Resolving the paradox might require a theory of quantum gravity, a theory that unifies quantum mechanics and general relativity, which we don't yet have. What's certain is that Hawking radiation shows black holes aren't eternal. Given enough time, far more time than the universe has existed, for stellar mass and larger black holes, they'll evaporate, returning their energy to the universe, leaving nothing behind except perhaps ghosts of information encoded in radiation. The universe recycles everything, even black holes. Tonight, as you rest under a sky where black holes lurk in distant regions, too small and faint to see, know that even these ultimate prisons, these cosmic traps, aren't permanent. They're slowly, imperceptibly evaporating, giving back what they took, dissolving into the quantum foam from which they emerged. It's a process so slow that it makes geological time look like a heartbeat. But it's real, a consequence of the strange marriage between gravity and quantum mechanics. And maybe there's something oddly hopeful in that. Even the most permanent seeming things aren't forever. Even black holes, the ultimate end states, the points of no return, eventually give back, eventually fade. Nothing is truly eternal except change, except transformation, except the slow unwinding of structure back into energy, order back into entropy. But that's trillions of years away. Time so long they lose meaning. For now, tonight, things persist. Stars shine. Black holes lurk. You breathe and think and rest. And that's enough. You don't need eternity. You have now. And now, tonight, is enough. So rest, knowing that even black holes aren't forever, that nothing is, but also that nothing needs to be. Impermanence isn't tragedy, it's reality. And within that reality, there's beauty, meaning, value, right here, right now, as you drift towards sleep. The discovery of the ozone layer showed that Earth has a high-altitude shield protecting life from harmful ultraviolet radiation. High above you, about 15 miles up, there's a layer of the atmosphere where oxygen takes a different form. Instead of O2, two oxygen atoms bonded together. It's O3, ozone, 3 atoms joined in a bent molecule. This ozone layer, though diffuse and spread across the stratosphere, is crucial to life on Earth's surface. Ozone is created when ultraviolet light from the sun strikes oxygen molecules, breaking them into individual atoms. These atoms then bond with other O2 molecules to form O3, and ozone, once formed, absorbs UV light, breaking apart and then reforming in a constant cycle. In the process, it absorbs most of the sun's ultraviolet B and all of its ultraviolet C radiation, the wavelengths most harmful to living tissue. UV radiation damages DNA, causing mutations that can lead to cancer. It also damages proteins and other biological molecules. Before the ozone layer formed, life could only exist in water deep enough to filter out UV, or in shaded areas, or underground. Land was essentially uninhabitable. The ozone layer formed gradually as photosynthetic organisms produced oxygen. Initially, that oxygen was absorbed by dissolved iron in the oceans and by surface minerals. But eventually, around 2.4 billion years ago, oxygen began accumulating in the atmosphere. As oxygen levels rose, an ozone layer formed. This was one of several factors that eventually allowed life to colonize land, leading to the terrestrial ecosystems we know today. The ozone layer was discovered in 1913 by French physicists, but its importance wasn't fully appreciated until much later. Then in the 1970s, scientists discovered something alarming. Certain human-made chemicals, chlorofluorocarbons or CFCs used in refrigerators, air conditioners, and aerosol sprays, were destroying ozone. CFCs are stable at ground level, but when they reach the stratosphere, UV light breaks them apart, releasing chlorine atoms. A single chlorine atom can destroy thousands of ozone molecules through a catalytic cycle. It breaks apart ozone, releasing oxygen. But then, the chlorine is freed to attack another ozone molecule over and over. In the 1980s, scientists discovered a massive ozone hole over Antarctica, a region where ozone levels dropped by more than 50% every spring. It was caused by CFCs accumulating in polar stratospheric clouds and being released all at once when sunlight returned in spring. The ozone hole was growing, and if CFC emissions continued, it would expand, exposing more of Earth's surface to dangerous UV levels. This led to one of the most successful international environmental agreements ever, the Montreal Protocol, signed in 1987. Countries agreed to phase out CFCs and replace them with less harmful alternatives. The agreement worked. CFC levels in the atmosphere peaked in the 1990s and have been declining since. The ozone layer is recovering. By mid-century, it should return to pre-1980 levels. It's a rare environmental success story, proof that when humanity recognizes a problem and acts collectively, we can solve it. But it's also a reminder of fragility. Our atmosphere, which seems so vast and robust, can be altered by human activities. The ozone layer, a diffuse scattering of molecules far above our heads, is all that stands between us and radiation levels that would make Earth's surface uninhabitable for most complex life. Tonight, as you rest beneath that protective layer, UV radiation from the sun is being absorbed high above, shielding you from harm. You don't think about it, don't see it, but it's there. A quiet guardian, the result of chemistry and physics, maintained by the constant interaction of sunlight and oxygen. It's been there for billions of years, allowing life to flourish on land, allowing your ancestors to leave the safety of the oceans and eventually evolve into you. And we nearly damaged it irreparably through ignorance. CFCs seemed harmless, inert, stable, convenient. No one realized they would drift into the stratosphere and destroy ozone. It was only through scientific research, observation, and international cooperation that we caught the problem in time and reversed it. Maybe that's a lesson worth holding on to as you drift toward sleep. The Earth is resilient, but not invincible. Its systems, atmosphere, climate, ecosystems, are complex and interconnected, and we don't always understand the consequences of our actions until it's almost too late. But we can learn. We can change. We can act together to protect the systems that sustain us. The ozone layer is healing, a testament to what's possible when science informs policy and the world works together. And maybe that's a hopeful note to end on, that despite our capacity for harm, we also have the capacity for wisdom, for correction, for care. The ozone layer above you is recovering, mending itself, returning to health. And maybe we can too, individually, collectively, as a species. There's hope in that. Hold on to it and rest. We found that Earth's climate has cycled through ice ages and warm periods driven by orbital variations called Milankovitch cycles. Earth's climate is not stable. Over hundreds of thousands of years, it cycles between ice ages, when glaciers cover much of the northern continents, and interglacials, warm periods like the one we're in now. These cycles have been happening for millions of years, a rhythm of freeze and thaw, advance and retreat, ice and ocean. For a long time, scientists wondered what caused ice ages. In the 1800s, glacial deposits and striations on rocks far from current glaciers revealed that ice had once covered vast areas now temperate. But why? What cooled the Earth enough to lock so much water in ice? In the 1920s, Serbian engineer Milutin Milankovitch proposed an answer. Ice ages are caused by variations in Earth's orbit and axial tilt. Earth's orbit isn't perfectly circular. It varies from nearly circular to slightly elliptical, over a cycle of about 100,000 years. Earth's axial tilt, currently about 23.5 degrees, varies between 22 and 24.5 degrees over a cycle of about 41,000 years. And the direction of the tilt, which hemisphere points toward the sun during which season, precesses like a wobbling top over a cycle of about 26,000 years. These variations, called Milankovitch cycles, affect how much sunlight different parts of Earth receive at different times of year. When the northern hemisphere has mild summers, not warm enough to melt all the winter snow, ice accumulates year after year, eventually forming glaciers. Those glaciers reflect sunlight, cooling the planet further, allowing more ice to form, a feedback loop. Eventually, orbital configurations shift, summers warm, ice melts, and an interglacial begins. For decades, Milankovitch theory was controversial, but in the 1970s, analysis of deep-sea sediment cores revealed a record of climate cycles going back millions of years. The cycles matched Milankovitch's predictions. Ice ages and interglacials occurred at the frequencies he predicted. His theory was confirmed. We're currently in an interglacial, the Holocene, which began about 11,700 years ago. All of human civilization, from the first agriculture to the present, has occurred during this unusually stable warm period. Before the Holocene, humans existed during the last ice age, but in much smaller numbers, as hunter-gatherers adapting to harsh, variable climates. Based on Milankovitch cycles alone, Earth should be slowly cooling toward the next ice age, thousands of years from now. But human activities, particularly greenhouse gas emissions, are overriding natural cycles. We're warming the planet faster than orbital cycles would cool it. The next ice age, if it happens, is likely tens of thousands of years away. And it might not happen at all if we continue altering the atmosphere. Ice ages aren't gentle. During the last glacial maximum, 20,000 years ago, ice sheets miles thick covered Canada, much of northern Europe, and parts of Asia. Sea levels were 400 feet lower, because so much water was locked in ice. The coastlines were different. You could walk from Siberia to Alaska, from England to France. The climate was dry, cold, harsh. Many species went extinct or were pushed into refugia, small areas where conditions were tolerable. But ice ages also drove evolution and adaptation. Species that survived developed tolerance for cold, developed migration strategies, developed complex behaviors. Humans who endured the ice ages developed language, culture, technology, tools and clothing and fire that allowed survival in extreme conditions. In a sense, we are who we are, partly because our ancestors survived ice ages. Tonight, as you rest in a warm, stable climate, know that this stability is unusual. For most of the past million years, Earth's climate has been colder, harsher, more variable. The 10,000 years of Holocene stability allowed agriculture, cities, civilization. It's a gift of timing, a fortunate interglacial that happened to coincide with our species' rise. But it's also fragile. Climate can change, has changed, will change. Milankovitch cycles are slow and predictable, but they're also powerful. Add human-induced changes on top, and we're in uncharted territory, a world warmer than it's been for hundreds of thousands of years, changing faster than at any time in human history. It's a reminder, maybe, that stability is not the default. Change is. Earth's climate has never been static. It dances to rhythms of orbital mechanics, wobbles and tilts, and eccentricities playing out over millennia, shifting ice and sea, forcing life to adapt or perish. We're lucky to live when we do, in a warm, stable moment. But luck doesn't last forever, and maybe that's worth remembering, worth respecting, worth protecting. The rare gift of climatic stability that made everything we know possible. So rest now, in this moment of warmth and stability, grateful for the wobbles and tilts that brought us here, mindful that the dance continues, that change is always coming, and that our job, perhaps, is to navigate it wisely, to preserve what we can, to adapt where we must, and to remember always that we're guests in a much longer story, brief beneficiaries of a climate sweet spot that won't last forever, but that, for now, holds us gently and allows us to dream. The discovery of crystallography revealed that atoms and solids are arranged in orderly, repeating patterns. There's a hidden order in the solid world around you. It seems chaotic. Rocks, metals, wood, plastic, all so different. But at the atomic level, many solids have crystalline structure. Atoms arranged in regular, repeating patterns that extend in 3 dimensions. This was first suspected when people noticed that crystals, minerals like quartz or salt, naturally form with flat faces, meeting at specific angles. Why would nature produce such geometric regularity? In the 1600s, scientists speculated that crystals were made of tiny, invisible building blocks, arranged in regular patterns, but they had no way to see atoms or prove the idea. The breakthrough came in 1912 when Max von Laue discovered that X-rays, passing through crystals, create interference patterns. Just as light waves create patterns when passing through narrow slits, X-rays bouncing off regularly spaced atoms in a crystal create patterns of spots on photographic film. The pattern's details reveal the atomic arrangement, the spacing between atoms, the symmetry of the structure. This technique, X-ray crystallography, has been used to determine the structures of countless materials. It revealed that common salt, sodium chloride, is a cubic lattice of alternating sodium and chloride ions. It showed that diamond is carbon atoms arranged in a tetrahedral lattice, explaining its extraordinary hardness. It revealed the double helix structure of DNA, one of the most famous applications of the technique. Crystals come in many symmetries: cubic, hexagonal, tetragonal, and more. The symmetry determines properties. Graphite and diamond are both pure carbon, but their structures are completely different. Graphite has layers of carbon atoms in hexagonal sheets that slide easily over each other, making it soft and slippery, good for pencil lead and lubricants. Diamond has carbon atoms in a rigid 3-dimensional network, making it the hardest natural substance. Even materials that seem amorphous, glass for instance, have some local order, though not the long-range repeating patterns of crystals. And many materials are polycrystalline, composed of many tiny crystals with different orientations, giving them different properties than single large crystals. Understanding crystal structure has been crucial for materials science. Want to design a stronger metal? Understand how atoms pack together, how dislocations move through the crystal lattice, how adding other elements affects structure. Want to create semiconductors for electronics? Understand silicon's crystal structure, how impurities disrupt it, how that creates the electrical properties that make transistors possible. Crystallography also revealed beauty. Crystals have symmetry, patterns that repeat, geometries that appeal to something deep in our aesthetic sense. Snowflakes, with their six-fold symmetry, are crystalline water ice. Their intricate forms arise from water molecules arranging themselves in hexagonal patterns as they freeze. Each snowflake is unique in detail, but all follow the same underlying symmetry, the same crystallographic rules, and crystals form naturally, driven by thermodynamics. When a liquid cools or a saturated solution evaporates, atoms or molecules arrange themselves into the lowest energy configuration, which often means a regular, repeating pattern. It's self-assembly, order emerging from disorder, patterns arising spontaneously because they're stable, because they minimize energy, because the universe favors certain geometries. There's something deeply satisfying about discovering that the solid world has hidden structure, that chaos is underlain by order, that atoms don't just pile up randomly, but organize themselves into regular, repeating, symmetric patterns. It suggests that order is natural, that structure emerges inevitably from the properties of matter and the laws of physics. Tonight, as you rest, you're surrounded by crystals, hidden ones mostly in metals, minerals, ceramics. The bed frame might contain iron crystals. Salt crystals might be in your kitchen. Quartz crystals are in electronics. Ice crystals might be forming on windows if it's cold enough. All of them, at the atomic level, are ordered, regular, symmetric, following patterns determined by the nature of their constituent atoms and the laws governing how those atoms interact. And maybe your life has hidden structure too, patterns you don't see in the moment, but that emerge when you look back. Rhythms and cycles and repeating themes, a crystalline order in what seems like chaos. Maybe we're all like atoms in a crystal, following rules we don't fully understand, arranging ourselves in patterns larger than we can perceive, part of a structure that has symmetry and beauty when viewed from the right perspective. So rest now within whatever structure holds you, family, community, routines, beliefs, trusting that there's order even in uncertainty, patterns even in randomness, and that your place within the larger crystal is necessary, meaningful, part of what makes the whole structure stable and beautiful. And maybe that's enough, to be one atom in a vast crystal, arranged just so, reflecting light in your own small way. Part of a pattern that extends beyond you, but includes you, always. We learned that some species can exchange genes horizontally, not just from parent to offspring, especially microorganisms. For most complex life, genes pass vertically, from parent to offspring through reproduction. You got half your genes from your mother, half from your father. They got theirs from their parents, and so on, back through time. It's a neat, orderly tree, generations branching, but genes only flowing down through the branches. But for microorganisms, bacteria especially, it's messier. Bacteria can transfer genes horizontally, from one individual to another, even between different species, without reproduction. It's as if you could acquire genes from a tree or a fish just by being near them. It sounds absurd, but it's common in the microbial world. There are several mechanisms. In transformation, bacteria can absorb naked DNA from their environment, DNA released when other bacteria die. In transduction, viruses that infect bacteria can pick up genes from one bacterium and transfer them to another. In conjugation, bacteria can form temporary connections called pili and transfer plasmids, small circular pieces of DNA, directly from one cell to another. This horizontal gene transfer has profound implications. It means bacterial evolution isn't just a slowly branching tree. It's a tangled web, with genes flowing between lineages, creating genetic mosaics. A bacterium's genome might contain genes from dozens of different ancestral species. It also means bacteria can adapt much faster than vertical inheritance alone would allow. If one bacterium evolves resistance to an antibiotic, it can share that resistance gene with other bacteria, even different species. This is why antibiotic resistance spreads so rapidly. Bacteria don't have to wait for mutations and natural selection to slowly spread resistance through reproduction. They can just trade genes, passing resistance around like information. This is terrifying from a medical perspective, but fascinating from an evolutionary one. It suggests that early life, before complex multicellular organisms evolved, might have been even more promiscuous with genes. The earliest organisms might have freely exchanged genetic material, creating a communal gene pool from which modern lineages eventually separated. Some scientists argue that horizontal gene transfer was crucial for early evolution. Different primitive cells might have specialized, some good at producing energy, others at building membranes, others at replicating DNA. By sharing genes, they could benefit from each other's innovations. Eventually, some of these specialists merged permanently, forming the first complex cells with organelles like mitochondria and chloroplasts. Former free-living bacteria that became permanent residents. Horizontal gene transfer isn't limited to bacteria. It's been found in some single-celled eukaryotes, and there's evidence that some genes in plants and animals, including humans, were acquired horizontally from bacteria or viruses millions of years ago. Our genomes contain DNA sequences from ancient viral infections, endogenous retroviruses that inserted their genes into our ancestors' genomes and now are passed down like any other gene. It's a reminder that the boundaries between organisms aren't as clear as we once thought. We're not isolated genetic islands. We're nodes in a web, connected by flows of genetic information, vertical through reproduction, but also horizontal through viruses, through symbiosis, through ancient transfers. Life is communal at a genetic level, constantly mixing and sharing and recombining. Tonight, as you rest, bacteria in your gut are likely exchanging genes, trading plasmids, picking up DNA from their environment, adapting to the conditions in your intestines. They're evolving, not just through slow mutation and selection, but through rapid gene swapping, creating new combinations, trying out new strategies. It's a genetic free-for-all happening inside you right now, invisible and constant. And maybe there's a metaphor there about ideas, culture, knowledge. We don't just inherit ideas vertically from parents and teachers. We exchange them horizontally from friends, books, strangers on the internet, cultures different from our own. And sometimes the best ideas come from unexpected sources, from horizontal transfers, from borrowing and recombining from different domains. Maybe creativity is like horizontal gene transfer, taking elements from disparate sources and combining them in new ways, creating something novel, adapted to new challenges. So as you drift towards sleep, maybe appreciate the messy, interconnected reality of life, the way information flows not just down through time, but across between lineages, species, individuals. Nothing is truly isolated. Everything exchanges, shares, borrows, recombines. And from that exchange comes diversity, adaptation, resilience. We're all part of the flow, nodes in the network, temporarily organized patterns that take in, transform, and pass on information, genetic, cultural, experiential. And maybe that's what it means to be alive, to be a temporary arrangement that participates in larger flows, that contributes something, however small, to the great exchange, the horizontal and vertical transfers that carry information, innovation, and life itself forward through time and space. Rest now, part of that flow, knowing you'll wake still connected, still exchanging, still part of the web. The discovery of chaos theory showed that some systems are inherently unpredictable, even though they follow deterministic rules. For centuries, scientists believed that if you knew the initial conditions of a system perfectly and understood the laws governing it, you could predict its future indefinitely. The universe was like a vast clockwork, deterministic, predictable, knowable. Laplace, the French mathematician, famously claimed that an intelligence knowing all positions and velocities of every particle could predict everything that would happen forever. But in the 1960s, meteorologist Edward Lorenz was running computer simulations of weather patterns. To save time, he started one simulation from the middle of a previous run, entering the numbers from a printout. But the printout showed numbers rounded to 3 decimal places, while the computer stored 6. The tiny difference, less than 1 part in 1,000, shouldn't have mattered much, but it did. The new simulation diverged wildly from the original. Within a short time, the weather in the 2 simulations was completely different. Lorenz had discovered sensitive dependence on initial conditions, what came to be called the butterfly effect. The idea is that a butterfly flapping its wings in Brazil might, through a chain of tiny influences, eventually affect whether a tornado forms in Texas. This was chaos theory, the study of systems that are deterministic but unpredictable. They follow rules, but tiny differences in starting conditions lead to vastly different outcomes. You can't predict their long-term behavior because you can never know the initial conditions precisely enough, and tiny errors grow exponentially. Weather is chaotic. So is turbulent fluid flow. So are some chemical reactions, some ecosystems, some aspects of the solar system's motion. Double pendulums, pendulums hanging from pendulums, exhibit chaotic behavior, swinging unpredictably despite following simple physical laws. Chaos theory revealed that the universe is more complex than clockwork. Determinism doesn't guarantee predictability. Even simple systems with simple rules can produce complex, unpredictable behavior. And there's often hidden order within chaos, strange attractors, fractal patterns, structures that emerge despite the apparent randomness. Fractals became associated with chaos theory, self-similar patterns that repeat at every scale. Coastlines are fractal-like. Zoom in, and you see the same jagged patterns at smaller scales. Ferns, river networks, blood vessels, all show fractal-like structures. The Mandelbrot set, a mathematical object, is a beautiful example. Infinite complexity arising from a simple equation. Chaos theory changed how we think about prediction and control. Weather forecasts are reliable only a few days out because of chaos. Small errors compound, and eventually the forecast becomes worthless. Long-term prediction of complex systems, climate, ecosystems, economies, is fundamentally limited. We can understand general trends but not precise outcomes. But chaos isn't randomness. Chaotic systems are deterministic. The same initial conditions produce the same outcome. It's just that in practice, we can never specify initial conditions perfectly, and tiny uncertainties grow into large unpredictabilities. And maybe there's freedom in that. If the universe were perfectly predictable, everything would be predetermined. Every choice, every outcome, already decided from the moment of the Big Bang. But chaos means that even in a deterministic universe, the future is open, unknowable, sensitive to the smallest perturbations. Tiny choices, tiny actions might have large consequences. You can't know what will happen, can't predict or control outcomes with certainty. All you can do is act, choose, influence the initial conditions, and see how the system evolves. Tonight, as you lie there, the world is chaotic. Weather systems are swirling unpredictably, economies fluctuating, ecosystems adapting, your own thoughts and feelings following trajectories sensitive to tiny internal and external influences. You can't predict tomorrow with certainty, can't know how your life will unfold, can't control outcomes with precision. But maybe that's okay. Maybe unpredictability isn't something to fear, but something to accept, even embrace. It means the future isn't written. It means possibilities remain open. It means small actions can matter, can ripple outward in ways you can't foresee. You don't need perfect knowledge or control. You just need to do your best, make your choices, accept that some things are beyond prediction or control, and trust that the system, chaotic though it is, has its own strange attractors, its own emergent patterns, its own way of finding order in chaos. We found that mitochondria in our cells have their own DNA, and likely originated as independent bacteria billions of years ago. Inside each of your cells are hundreds of tiny structures called mitochondria. They're often called the powerhouses of the cell because they produce most of your cellular energy, converting nutrients into ATP, the energy currency your cells use for everything, from muscle contraction to thinking to repairing DNA. But mitochondria are strange. They don't quite seem to belong to your cells. They have their own DNA, small circular chromosomes separate from the DNA in your cell nucleus. They reproduce independently, dividing on their own schedule like bacteria. They have their own ribosomes, their own membranes. In many ways, they act like cells within cells. In the 1960s, biologist Lynn Margulis proposed a radical explanation. Mitochondria were once free-living bacteria. Billions of years ago, a primitive eukaryotic cell engulfed an aerobic bacterium, one that could use oxygen to efficiently extract energy from food. Instead of digesting it, the two formed a partnership. The bacterium lived inside the cell, producing energy. The host cell provided protection and nutrients. Over time, the bacterium transferred most of its genes to the host cell's nucleus, becoming fully integrated, an organelle rather than a separate organism. But it retained a few genes and some independence, remnants of its bacterial origin. This is endosymbiotic theory, the idea that complex cells arose through symbiosis, different organisms merging to form something new. It was controversial at first, but evidence accumulated. Mitochondrial DNA is circular like bacterial DNA, not linear like nuclear DNA. Mitochondrial ribosomes are similar to bacterial ribosomes, not eukaryotic ones. The inner membrane of mitochondria resembles bacterial membranes. And phylogenetic analysis, comparing DNA sequences, shows that mitochondria are most closely related to a group of bacteria called alpha proteobacteria. The same story holds for chloroplasts in plants and algae. These organelles perform photosynthesis, capturing light energy to make sugar. They too have their own DNA, their own ribosomes, their own membranes. They too originated as free-living bacteria, cyanobacteria, that were engulfed and eventually became integrated into eukaryotic cells. This means you are, quite literally, a collaboration. Your cells contain the descendants of ancient bacteria, guests that became permanent residents, partners whose contributions are so essential that you couldn't live without them. Every breath you take, every movement you make, every thought you think, all powered by mitochondria, by the evolutionary legacy of bacteria that merged with your single-celled ancestors almost 2 billion years ago. And mitochondria are still somewhat independent. When a cell divides, mitochondria must divide too, replicating their DNA and splitting, sometimes unevenly. This is why mitochondrial diseases exist. Mutations in mitochondrial DNA can cause problems, often affecting tissues with high energy needs like muscles and neurons. And because mitochondria are inherited only from the mother, sperm contribute almost no cytoplasm, and thus no mitochondria, to the fertilized egg. Mitochondrial DNA is passed down matrilineally. Your mitochondrial DNA came from your mother, who got it from her mother, and so on, in an unbroken line stretching back millions of generations to the first eukaryotes. Scientists use mitochondrial DNA to trace evolutionary relationships and human migrations. Because it's inherited from one parent and doesn't recombine, it's like a molecular clock, accumulating mutations at a steady rate. By comparing mitochondrial DNA from different people, scientists have traced humanity's origins to Africa and mapped how populations spread around the world. Endosymbiosis is one of evolution's most important innovations. It allowed the evolution of complex, energy-rich eukaryotic cells, which could grow larger, develop complex structures, eventually form multicellular organisms. Without mitochondria, complex life as we know it probably wouldn't exist. Plants couldn't photosynthesize efficiently without chloroplasts. Animals couldn't move, think, or exist without the energy mitochondria provide. And it's a reminder that evolution isn't just competition and selection. It's also cooperation, symbiosis, different organisms coming together to create something neither could achieve alone. The boundaries between organisms are blurrier than they seem. You're not a single organism, but a collective. Human cells plus mitochondria, plus the bacteria in your gut, plus maybe ancient viral DNA integrated into your genome. Life is collaborative, interdependent, constantly forming partnerships and alliances. Tonight, as you rest, your mitochondria are hard at work. Each one is a tiny factory, taking in oxygen and nutrients, running them through biochemical pathways, producing ATP. Billions of mitochondria across trillions of cells, all descendants of ancient bacteria, all working to keep you alive. They're silent partners, invisible laborers, the legacy of a merger that happened so long ago, it's written into the structure of every complex cell on Earth. And maybe there's gratitude in recognizing that. You're alive because of cooperation at the cellular level, because different organisms merged and learned to work together. Maybe that's a model for how we should live, not as isolated individuals, but as collaborators, recognizing our interdependence, appreciating the contributions of others, understanding that the best outcomes often come from partnerships where different strengths combine into something greater than the sum of parts. So rest now, trusting in the ancient partnership within your cells, the bacteria turned organelles that power your existence, and maybe carry that spirit of collaboration with you into tomorrow, recognizing that we're all better together, that boundaries are often illusions, and that life at every scale is fundamentally about connection, cooperation, and the beautiful complexity that emerges when separate things become one. The discovery of telomeres revealed that chromosomes have protective caps that shorten with each cell division, acting like a cellular clock. At the end of each chromosome, like the plastic tips on shoelaces, there are protective caps called telomeres. They're sequences of repetitive DNA. In humans, thousands of copies of the sequence T-tag-G repeated over and over. They don't code for proteins or carry genetic information. They're just there to protect the chromosome. Why are they needed? Because of how DNA replication works. When a cell divides, its DNA must be copied. Enzymes called DNA polymerases do this, but they have a quirk. They can't copy all the way to the very end of a linear DNA molecule. A small section at each chromosome's tip is left unreplicated. Without telomeres, this would mean losing actual genes with each division. But telomeres act as buffers. They're the part that gets lost, protecting the important genetic information further in. This was discovered in the 1970s by Elizabeth Blackburn and others studying single-celled organisms. They found these repetitive sequences at chromosome ends and realized their function. Telomeres protect chromosomes from degrading, from fusing with other chromosomes, from being recognized as broken DNA that needs repair. But here's the catch. Telomeres shorten with each cell division. Each time a cell divides, its telomeres get a little shorter. After many divisions, telomeres become critically short. When that happens, the cell stops dividing. It enters a state called senescence, still alive but no longer reproducing. Eventually, it may die or be cleared by the immune system. This is one reason we age. Our cells have a built-in limit to how many times they can divide, the Hayflick limit, named after the scientist who discovered it. Stem cells in our body can divide many times, replenishing tissues. But eventually, telomeres shorten, division slows, tissues lose their ability to regenerate efficiently. We accumulate senescent cells, which can contribute to aging and age-related diseases. Some cells don't follow this rule. Stem cells and reproductive cells produce an enzyme called telomerase that adds telomere sequences back onto chromosomes, maintaining their length. This allows these cells to divide indefinitely without telomeres running out. Telomerase is like a reset button, restoring the cellular clock. Cancer cells also activate telomerase. This is part of what makes cancer dangerous. The cells can divide indefinitely without hitting the Hayflick limit. They become immortal in a sense, dividing endlessly, forming tumors. About 85–90% of cancers have active telomerase, which is one reason telomerase inhibitors are being investigated as potential cancer treatments. Telomeres and telomerase research has fascinated people because it touches on aging and mortality. If shortened telomeres contribute to aging, could lengthening them extend life? Some experiments in mice suggest that activating telomerase can extend lifespan and improve health. But it's risky. Too much telomerase might increase cancer risk. Studies have shown that stress, poor diet, and lack of exercise correlate with shorter telomeres, while healthy lifestyle choices correlate with longer ones. But correlation isn't causation. It's not clear whether telomere length is a cause or consequence of health. Still, telomeres have become a marker of biological age, distinct from chronological age. Some people's cells are older or younger than their years suggest, based on telomere length. Blackburn won the Nobel Prize in 2009 for this work. Her discovery revealed a fundamental aspect of cellular biology and opened new questions about aging, cancer, and mortality. Telomeres are molecular timers, counting down cell divisions, enforcing limits. They're part of why complex organisms age and die. Our cells can only renew themselves so many times before running out of buffer. But they're also a protection mechanism. Without telomeres, chromosomes would be unstable, and cancer might be even more common. The limit on cell division prevents damaged cells from dividing indefinitely. It's a trade-off. Telomeres protect us when we're young, but their shortening contributes to aging as we get older. Tonight, as you rest, your cells are at various stages of this process. Some have long telomeres, lots of divisions left. Others are nearing their limits, approaching senescence. Each day, some cells divide. Telomeres shorten slightly. The molecular clock ticks forward. It's imperceptible, gradual, but relentless. You're aging cell by cell, division by division, telomere by telomere. But it's not just decay, it's also protection. Those shortening telomeres are guarding your genetic information, preventing chaos, maintaining order. And you're constantly renewing stem cells with active telomerase, producing fresh cells, replacing old ones, keeping you functional. You're a balance between renewal and limitation, between the immortality of stem cells and the mortality of specialized cells, between the potential for endless division and the necessity of limits. And maybe that balance is life itself. Not immortality, but a carefully managed process of growth, maintenance, decline, and eventual end. Telomeres remind us that we're temporary, that our cells are counting down, that time is finite. But they also remind us that we're designed to last, protected, maintained, renewed for decades if we're lucky. And maybe that's enough. Maybe finite time is what gives meaning to each moment, what makes each day valuable, what encourages us to live fully while we can. So rest now, knowing your cellular clocks are ticking, but slowly, and that tomorrow will come, and you'll wake still here, still renewed enough to greet another day, still held together by molecular machinery that knows how to balance immortality's dangers with mortality's inevitability. And maybe that's the sweetest spot of all, neither forever nor too soon, but just long enough to matter, to love, to live, to leave a mark, however small, on the world. We learned that Earth's inner core is solid iron, despite being hotter than the sun's surface, kept solid by immense pressure. Beneath your feet, about 4,000 miles down, is Earth's inner core, a sphere of solid iron roughly the size of the moon. The temperature there is astonishing, around 9,800 degrees, 5,400 degrees, hotter than the sun's surface. At such temperatures, iron should be liquid or even gas, but it's solid. The reason is pressure, the weight of the entire Earth. All the rock, all the mantle, all the outer core, presses down on the inner core with pressures reaching 3.6 million atmospheres. Under such immense pressure, atoms are forced so close together that they can't move freely. Despite the tremendous heat, the iron remains solid, its atoms locked in a crystalline structure. We've never been to the inner core and never will. It's far too deep, too hot, too inaccessible. But we know it's there and what it's like by studying seismic waves. When earthquakes occur, they send waves rippling through Earth. By measuring how these waves travel, how they speed up or slow down, how they reflect or refract at boundaries between different layers, seismologists have mapped Earth's interior. Primary waves, P waves, can travel through solids and liquids. Secondary waves, S waves, only travel through solids. By observing which waves reach which locations and how they're altered, scientists determined that Earth has a liquid outer core. S waves don't pass through it. Surrounding a solid inner core, S waves can pass through it, though indirectly. The inner core is relatively new, geologically speaking. Early in Earth's history, the core was entirely liquid. As Earth slowly cooled, the innermost part began to solidify, forming a solid sphere that has been growing ever since. It's still growing today, about 1 millimeter per year, as more iron crystallizes out of the liquid outer core. This process releases heat and lighter elements, driving convection currents in the outer core. Those currents, combined with Earth's rotation, generate the magnetic field through the geodynamo process. So the inner core's growth indirectly powers the magnetosphere that protects us from solar radiation. The inner core also rotates slightly faster than the rest of Earth, about 1 extra degree per year. This was discovered by analyzing seismic waves from earthquakes that occurred decades apart at similar locations. The inner core's rotation affects how waves travel through it, and the pattern had shifted, indicating rotation. It's like Earth has a planet within a planet, spinning at its own rate. Why does the inner core rotate faster? It's likely dragged along by magnetic fields generated in the outer core, which can transfer angular momentum. But the details are still being studied. The inner core remains one of Earth's most mysterious regions, despite all we've learned. There's something almost poetic about the inner core, a solid sphere of iron, unimaginably hot and pressurized, hidden at Earth's heart, invisible and inaccessible, yet essential to the planet's structure and dynamics. It's been there for billions of years, slowly growing, quietly spinning, contributing to processes that make life on the surface possible. Tonight, as you lie on Earth's surface, 4,000 miles of rock and metal separate you from that iron heart. You've never seen it, never will, yet it's there, solid despite the heat, crystalline despite the pressure, spinning slightly faster than you, generating magnetic fields that ripple up through the mantle and crust to create the magnetosphere that shields you from the solar wind. It's a reminder, perhaps, that there are depths to everything, hidden layers, invisible cores, foundations that support what's visible but remain unseen. Maybe we're all like Earth, with our own inner cores, solid centers of identity, belief, values, held together under pressure, shaped by heat and time, hidden from view but essential to who we are. And maybe there's strength in that, in having a solid core, something fundamental that holds steady despite external changes, despite heat and pressure and time. Your core might not be iron, might not be physical, but it's there, the part of you that remains you, that maintains integrity under pressure, that keeps spinning, that generates the fields that protect you, that defines you. The discovery of the neutrino revealed a nearly massless, ghostly particle that rarely interacts with matter. Every second, about 100 trillion neutrinos from the sun pass through your body. They stream through you at nearly the speed of light, and you feel nothing. They don't interact with your cells, don't deposit energy, don't disturb atoms. They're ghosts, passing through matter as if it weren't there. Neutrinos were first proposed in 1930 by Wolfgang Pauli to solve a puzzle in nuclear physics. When a neutron decays into a proton and electron, the energy and momentum didn't seem to add up. Something was carrying away some of the energy, but invisibly. Pauli proposed a new particle, electrically neutral, nearly massless, barely interacting with anything. He called it a little neutral one, a neutrino. For 26 years, neutrinos remained theoretical. They were so hard to detect that Pauli joked he'd committed the ultimate sin, proposing something undetectable. But in 1956, Frederick Rains and Clyde Cowan finally detected neutrinos coming from a nuclear reactor. They used a massive detector filled with water and surrounded by photomultiplier tubes. Very rarely, a neutrino would interact with a proton in the water, producing a flash of light. They detected a few events per hour, proof that neutrinos were real. Why are neutrinos so elusive? Because they only interact through the weak nuclear force and gravity, not through electromagnetism or the strong force. Most particles interact electromagnetically, which is why light reflects off your skin, why atoms repel each other, why matter feels solid. But neutrinos ignore all that. A neutrino could pass through a light year of solid lead and probably not interact with a single atom. 3 types of neutrinos exist, associated with the 3 charged leptons: electron neutrinos, muon neutrinos, and tau neutrinos. They're produced in nuclear reactions, in the sun, in supernovae, in nuclear reactors, in cosmic ray collisions with the atmosphere. They're everywhere, streaming through space at nearly light speed, carrying information about their sources. For decades, neutrinos were thought to be massless. But in the late 1990s, experiments detected neutrino oscillation, neutrinos changing from one type to another as they travel. This is only possible if neutrinos have mass, even if it's incredibly tiny. The discovery won the 2015 Nobel Prize and revealed that the standard model of particle physics is incomplete. It assumed neutrinos were massless, but they're not. Neutrinos are now used to study phenomena we can't observe any other way. When a star collapses into a supernova, most of the energy is released as neutrinos, not light. In 1987, detectors on Earth picked up neutrinos from a supernova in the Large Magellanic Cloud, 168,000 light-years away, confirmation that supernovae produce neutrino bursts. Those neutrinos had traveled for 168,000 years, passing through galaxies, clouds of dust, planets, arriving at Earth and passing through it, with a few caught by detectors. There's even a cosmic neutrino background, left over from the Big Bang, like the cosmic microwave background, but made of neutrinos. These neutrinos have been traveling since the universe was about 1 second old, cooled now to low energies, filling all of space. We can't detect them yet. They barely interact with anything, but they're there, hundreds per cubic centimeter, an invisible sea of particles from the dawn of time. Tonight, as you rest, neutrinos from the sun are streaming through you. Neutrinos from cosmic rays hitting the atmosphere are passing through Earth and through you. Ancient neutrinos from supernovae that exploded millions of years ago are reaching Earth now. having traveled across the galaxy, most passing through unnoticed. You're immersed in a bath of neutrinos, constantly, invisibly, harmlessly. And maybe there's something comforting in that. The universe is filled with things we can't see, can't feel, can't directly detect. Neutrinos remind us that our perception is limited, that most of reality is invisible to us. But it's there, real, following laws, carrying information, participating in the cosmos. Maybe there are other invisible things we miss. Not physical particles, necessarily, but influences, connections, forces that shape our lives without our awareness. Maybe kindness we offer ripples outward, like neutrinos, mostly unseen, rarely interacting, but occasionally touching someone, making a difference, carrying energy and information forward. Maybe we're all like neutrinos in a way, small, transient, passing through the world, rarely leaving traces, but still real, still part of the fabric of reality, still carrying something forward. We found that sound cannot travel through a vacuum because it requires a medium like air, water, or solid material to propagate. Sound is vibration. When you speak, your vocal cords vibrate. Those vibrations push air molecules, which push other air molecules, creating a wave of pressure that travels outward. When the wave reaches someone's ear, it vibrates their eardrum, which their brain interprets as sound. Sound needs something to travel through, a medium, whether gas, liquid, or solid. In space, there is no air. It's not just thin air, it's vacuum, almost completely empty. And in vacuum, sound cannot travel. There's nothing to vibrate, nothing to carry the wave. If you were floating in space and someone floated by and shouted at you, you'd hear nothing. If a nearby spacecraft exploded, you'd see the flash. Light doesn't need a medium, but you'd hear silence. This was demonstrated as early as the 1600s. Robert Boyle placed a ringing bell inside a glass jar and pumped out the air. As the air thinned, the bell became quieter. When the jar was nearly evacuated, the bell was silent, even though it was clearly still ringing. Sound needs air. Hollywood gets this wrong constantly. Space battles in movies are full of roaring explosions, screaming engines, whooshing spacecraft. It's dramatic and immersive, but completely inaccurate. Real space is silent. The only sounds astronauts hear are vibrations conducted through their spacecraft or suit, footsteps through the floor, the hum of machinery through metal, their own breathing and heartbeat. But outside, nothing. The universe's most violent events, supernovae, black holes colliding, stars exploding, occur in absolute silence. Sound does travel through other media, though. In water, sound travels about 4 times faster than in air, which is why whale songs can travel hundreds of miles through the ocean. In solids, sound can travel even faster. In steel, it's about 15 times faster than in air. This is why you can hear trains coming, by putting your ear to the railroad track. The sound travels faster and farther through the metal. Different media affect sound's speed and quality. Helium is less dense than air, so sound travels faster through it, making voices higher pitched. Not because helium changes your vocal cords, but because it changes how sound waves travel through your vocal tract, shifting the resonances. Sulfur hexafluoride, denser than air, slows sound and deepens voices. Dolphins and bats use sound for echolocation, emitting clicks and listening for echoes, building sonic maps of their surroundings. They can see with sound in darkness or murky water. Whales communicate across vast ocean distances with low-frequency calls that travel hundreds of miles. Elephants use infrasound, frequencies below human hearing, to communicate across miles of savanna. Sound is also how we've probed Earth's interior. Seismologists study how seismic waves, essentially sound waves from earthquakes, travel through the planet, revealing layers, boundaries, the liquid outer core, and solid inner core. Similar techniques using artificially generated sound waves are used to explore for oil and gas, to map the ocean floor, to study the structure of materials. And sound is deeply embedded in human culture. Music, speech, laughter, crying, all sound. We communicate primarily through sound, express emotions with it, create art with it. Silence can be peaceful or oppressive, comforting or eerie. Sound shapes our experience of the world. Tonight, as you lie in bed, you're surrounded by sounds. Maybe the hum of electronics, the whisper of wind, distant traffic, your own breathing. Each sound is a wave traveling through air, vibrating your eardrums, interpreted by your brain. The sounds are information about your environment, about what's nearby, about the state of things. Even in quiet, there's rarely true silence. Listen carefully and you'll hear something. Air conditioning, a clock ticking, blood flowing past your eardrums. And maybe there's something meditative in attending to sound, in noticing the sonic texture of the moment, in appreciating that sound is touch at a distance, vibrations traveling through matter, eventually touching your body, becoming sensation, becoming perception. Every sound you hear is matter vibrating, air molecules dancing, energy rippling through the medium, connecting source to listener. So as you drift toward sleep, maybe listen for a moment. Notice the sounds, the silences between them, the way sound fades as you relax. And know that when you sleep deeply, your conscious perception of sound will diminish, but your ears will still work, still vibrate, still send signals to your brain, monitoring the environment, ready to wake you if something important sounds. You're always listening, even in sleep, always connected to the world through vibration, through the medium of air, through the physics of pressure waves, and the biology of hearing. And maybe tomorrow, remember that space is silent, that silence is the default, that sound is a gift of atmosphere, of living on a planet wrapped in air, in a medium that carries vibration, that lets us hear each other, music, nature, the world. And maybe that's worth appreciating, the medium that surrounds us, invisible and essential, carrying waves connecting us, making sound, and therefore communication, and therefore much of what makes us human possible. The discovery of the citric acid cycle revealed how cells extract energy from food in an elegant circular pathway. You eat food. Somehow that food becomes energy. Energy for your muscles to contract, your neurons to fire, your heart to beat, your cells to function. But how? What's the mechanism that transforms the chemical energy in food into the ATP your cells use? Part of the answer is the citric acid cycle, also called the Krebs cycle, after Hans Krebs, who worked out the details in the 1930s. It's a series of chemical reactions that occur in mitochondria, the powerhouses of your cells. The cycle takes acetyl-CoA, a molecule derived from carbohydrates, fats, and proteins, and breaks it down completely, extracting energy in the process. Here's how it works. Acetyl-CoA, a 2-carbon molecule, enters the cycle. It combines with a 4-carbon molecule called oxaloacetate, forming citric acid, 6 carbons. Through a series of steps, enzymes rearrange bonds, remove CO2, transfer electrons to carriers like NADH and FADH2, and eventually regenerate oxaloacetate. The cycle is now ready to accept another acetyl-CoA and start again. The beauty is in the circular nature. The cycle doesn't run out of intermediates. They're regenerated with each turn. It's self-sustaining, efficient, elegant, and it's ancient. All aerobic organisms, from bacteria to humans, use some version of the citric acid cycle. It's been preserved and refined over billions of years because it works so well. The energy extracted in the cycle isn't used directly. Instead, it's temporarily stored in NADH and FADH2. These carriers shuttle electrons to the electron transport chain, a series of protein complexes embedded in the mitochondrial inner membrane. As electrons pass through the chain, energy is released and used to pump protons across the membrane, creating a gradient. That gradient drives ATP synthase, an enzyme that generates ATP. It's like a water wheel, turned by a proton flow, producing energy currency the cell can use. The cycle also produces CO2 as a waste product. This is the CO2 you breathe out. When you inhale, oxygen enters your lungs and reaches your cells, where it's the final electron acceptor in the electron transport chain, combining with electrons and protons to form water. When you exhale, you release CO2 produced by the citric acid cycle. Breathing in brings oxygen to power the cycle. Breathing out expels the waste. Krebs won the Nobel Prize in 1953 for this discovery. His work revealed one of metabolism's central processes, a pathway that connects the breakdown of all major nutrients. Carbohydrates are broken down to acetyl-CoA. Fats are broken down to acetyl-CoA. Proteins are broken down to various intermediates, some of which enter the cycle directly. Everything eventually funnels into this central pathway, where energy is extracted efficiently. Disruptions to the cycle cause problems. Mutations in cycle enzymes can cause metabolic diseases. Cancer cells often have altered metabolism, bypassing normal regulation, producing energy less efficiently but faster. The Warburg effect. Understanding the cycle has been crucial for understanding metabolism, disease, and cellular energetics. And it's happening right now, in your cells. Thousands of cycles per second in each mitochondrion, millions of mitochondria per cell, trillions of cells in your body. It's a vast, coordinated effort. Enzymes catalyzing reactions, carriers shuffling electrons, protons pumping, ATP synthase spinning, producing energy continuously. This is what keeps you alive, what powers your thoughts, your movements, your heartbeat, your existence. Tonight, as you rest, the citric acid cycle continues. Your cells are still metabolizing, still extracting energy, though more slowly as your activity decreases. The cycle doesn't stop, it just slows, adjusting to demand. Even in sleep, your brain requires enormous energy to maintain consciousness, to dream, to consolidate memories. Your heart keeps beating, your lungs keep breathing, your cells keep functioning, all powered by this ancient, elegant cycle, turning and turning, extracting life from food, breath by breath, turn by turn. And maybe there's something profound in the circular nature of it. Life is cyclical. Energy flows in circles, nutrients cycle, seasons repeat, generations turn over. The citric acid cycle is a microcosm of larger patterns. It takes in, transforms, releases, and returns to the beginning, ready to start again. There's no end, just continuous transformation, continuous flow. Maybe we can learn from that, not to seek endings, completions, final states, but to embrace cycles, growth and rest, work and recovery, waking and sleeping. Everything in cycles, in balance, in flow. The citric acid cycle has been turning for billions of years, in countless organisms, extracting energy, sustaining life, never stopping, never completing, just turning, always turning. And maybe that's what life is, not a line with a beginning and end, but a cycle, a flow, a continuous transformation. So rest now, trusting the cycles, metabolic cycles in your cells, circadian cycles in your brain, seasonal cycles in the world, life cycles stretching back through your ancestors and forward through descendants. All cycles, all turning, all part of the same vast, elegant pattern that sustains everything. And you're part of it, turning with it, flowing with it, here now in this moment of the cycle. Resting, restoring, preparing for the next turn. And that's enough. That's everything. We learned that different wavelengths of light carry different amounts of energy, with ultraviolet having more punch than infrared. Light seems simple. It illuminates, lets us see, feels warm on our skin. But light is electromagnetic radiation, and it comes in a spectrum of wavelengths, each with different properties and energies. Visible light, the narrow band we can see, ranges from red, longer wavelengths around 700 nanometers, to violet, shorter wavelengths around 400 nanometers. But the electromagnetic spectrum extends far beyond what we can see. Longer than red is infrared, then microwaves, then radio waves. Shorter than violet is ultraviolet, then X-rays, then gamma rays. The key insight is that shorter wavelengths carry more energy. This is a consequence of quantum mechanics. Light consists of photons, packets of energy. A photon's energy is inversely proportional to its wavelength, so ultraviolet photons have more energy than visible light photons, which have more energy than infrared. This explains why different types of light have different effects. Infrared feels warm because its photons have just enough energy to make molecules vibrate, producing heat, but not enough to break chemical bonds. Visible light can be absorbed by molecules, exciting electrons to higher energy levels, but usually without causing permanent damage. Ultraviolet, however, carries enough energy to break chemical bonds, including bonds in DNA. This is why UV causes sunburn and increases cancer risk. It damages DNA in skin cells, potentially causing mutations. Your body tries to repair the damage and often succeeds, but sometimes mutations slip through, accumulating over time. X-rays have even more energy and can pass through soft tissue, getting absorbed mainly by denser materials like bone, which is why they're useful for medical imaging. But they also damage DNA, which is why X-ray exposure is minimized, and technicians leave the room during imaging. Gamma rays, the most energetic, are produced in nuclear reactions and cosmic events. They can pass through almost anything, ionizing atoms and causing severe radiation damage. Fortunately, Earth's atmosphere absorbs most cosmic gamma rays, and we're not regularly exposed to significant amounts. At the other end of the spectrum, radio waves have very long wavelengths and very low energy. They pass through walls and bodies without interaction, which is why radio and Wi-Fi work indoors. They don't have enough energy to affect molecules significantly, which is why they're generally safe. Though heating effects from high-intensity microwaves are possible, that's how microwave ovens work, using a specific frequency that water molecules absorb efficiently. The fact that energy depends on wavelength explains many phenomena. Sunlight includes UV, which damages skin. Sunscreen works by absorbing or reflecting UV specifically, letting visible light through. Greenhouse gases like CO2 and water vapor absorb infrared radiation, trapping heat and warming the planet. Photosynthesis uses visible light, specifically red and blue wavelengths, to drive chemical reactions, while green light is mostly reflected, which is why plants look green. And the sun emits across a wide spectrum, but peaks in the visible range. This isn't coincidence. Our eyes evolved to detect the wavelengths most abundant in sunlight. If we'd evolved around a different star, we might see different wavelengths as visible. Understanding light's energy spectrum has enabled technologies. Solar panels convert visible and some infrared light to electricity. UV sterilization uses UVC to kill bacteria and viruses. Infrared cameras detect heat signatures. X-ray crystallography determines molecular structures. Radio telescopes observe the universe in wavelengths, invisible to optical telescopes, revealing phenomena like pulsars and the cosmic microwave background. Tonight, you're surrounded by electromagnetic radiation of many wavelengths. Visible light if you're reading by lamp, infrared from warm objects, including your own body, radiating heat, radio waves from nearby transmitters and routers, possibly some weak X-rays or gamma rays from natural background radiation, radon in the ground, cosmic rays that made it through the atmosphere. Most of it passes through you harmlessly, lacking energy to significantly interact with your molecules. And maybe there's a metaphor there about energy and effect. Not all influences are equal. Some pass through us without effect. Low energy interactions, superficial encounters. Others have just enough energy to warm us, to make us feel something without causing harm. And some carry enough energy to change us, to break bonds, to alter structure, for better or worse. And maybe wisdom is learning to recognize which is which, to seek out the wavelengths that warm without burning, that illuminate without damaging, that carry just enough energy to nourish growth without overwhelming with intensity. So as you rest, bathed in the gentle infrared glow of your own body heat, perhaps shielded from harmful UV by walls and night, maybe appreciate the spectrum of life, the range of energies we encounter, from the gentle to the intense, from the harmless to the transformative, and maybe rest in the knowledge that you can choose, to some extent, which wavelengths you expose yourself to, which energies you absorb, which influences you let affect you. The spectrum is wide, but not every wavelength needs to reach you. Some you can filter, shield, reflect, and the ones that do reach you, may they be the warming kind, the illuminating kind, the kind that brings energy without harm, light without burning, growth without damage. Rest in that hope, in that possibility, and let only the gentlest frequencies reach you now, in this quiet time, as you slip towards sleep. The discovery of pulsars in 1967 revealed rapidly spinning neutron stars that sweep radio beams across space like cosmic lighthouses. In 1967, graduate student Jocelyn Bell Burnell was analyzing data from a radio telescope when she noticed something strange, a signal that pulsed with remarkable regularity, exactly once every 1.337 seconds. The pulses were incredibly precise, more accurate than any clock on Earth. At first, the team joked that it might be signals from extraterrestrials. They even called the source LGM-1 for little green men. But soon they found more pulsing sources in different parts of the sky. These weren't aliens, but something natural, and something no one had predicted. They were pulsars, neutron stars, the collapsed cores of massive stars that exploded as supernovae. A neutron star is unimaginably dense. Take a star's worth of matter, perhaps 1.5 times the sun's mass, and compress it into a sphere only about 12 miles across. A teaspoon of neutron star material would weigh 1 billion tons. Neutron stars spin rapidly, sometimes hundreds of times per second, because they conserve angular momentum as they collapse, like an ice skater spinning faster when pulling in their arms. And they have powerful magnetic fields, trillions of times stronger than Earth's. Charged particles accelerate along the magnetic field lines, producing beams of radio waves that shoot out from the magnetic poles. As the neutron star spins, these beams sweep through space like a lighthouse beam. If one happens to point toward Earth during its rotation, we see a pulse, a brief flash of radio waves, then darkness as the beam points elsewhere, then another pulse, over and over with clock-like regularity. The fastest known pulsar spins 716 times per second, the slowest spin once every few seconds. But all are remarkably stable, better timekeepers than atomic clocks over short periods. Their stability comes from their enormous rotational inertia. They're like cosmic flywheels, massive and spinning so fast that nothing can easily speed them up or slow them down. Pulsars gradually slow as they lose energy to radiation and particle emission. Eventually, after millions or billions of years, they'll spin so slowly that they no longer pulse detectably. They become quiet neutron stars, dark and invisible except through gravitational effects. Pulsars have been used to test physics in extreme conditions. Near a neutron star, gravity is so strong that general relativity's predictions differ significantly from Newtonian physics. Observations of pulsars in binary systems have confirmed relativity's predictions with incredible precision. The 1993 Nobel Prize was awarded for using binary pulsar observations to indirectly detect gravitational waves. Einstein's prediction that accelerating masses should create ripples in space-time. Some pulsars are in binary systems with other neutron stars or black holes. As they orbit, they emit gravitational waves, losing energy, causing the orbit to shrink. Eventually, they'll spiral inward and merge in a catastrophic collision, releasing a burst of gravitational waves. One such merger was detected in 2017, producing both gravitational waves and light. The first multi-messenger observation of such an event. Pulsars are also potential navigational beacons. Their precise timing and fixed positions make them like cosmic GPS satellites. The Voyager spacecraft carry golden records with diagrams showing Earth's location relative to several pulsars, a map that should remain valid for millions of years. Jocelyn Bell Burnell's discovery was one of the most important in astronomy, yet her male advisors received the Nobel Prize without her. This sparked controversy and discussions about recognition in science. She handled it with grace, continuing a distinguished career, receiving many honors, and advocating for women and minorities in science. Tonight, as you rest, pulsars are spinning throughout the galaxy, thousands of them, remnants of ancient stars, rotating hundreds of times per second, sweeping beams of radio waves through the void. Most don't point toward Earth, but a few do, and radio telescopes are detecting their pulses, timing them, studying them, learning about physics in conditions we can never replicate on Earth. And maybe there's something poignant in pulsars, stars that died explosively, but left behind something that persists, something that spins and signals, that marks time with precision, that serves as beacons in the darkness. Maybe that's a metaphor for legacy, for how we might endure after our own bright burning is done. Not as we were, perhaps, but transformed, compacted, spinning out signals that might guide others, that might teach, that might endure long after the explosion fades. We found that ice has many different crystalline forms depending on temperature and pressure, at least 20 distinct types. You know ice. It's what forms in your freezer, what makes your drink cold, what you slip on in winter. It's water in solid form, simple, right? Except ice isn't simple at all. The ice you know, ice IH, called hexagonal ice, is just one of at least 20 known crystalline forms of ice. Each has a different arrangement of water molecules, different properties, and exists under different conditions of temperature and pressure. Ice IH, the common form, exists at normal pressures and temperatures below 0 degrees C. Its crystal structure is hexagonal, which is why snowflakes have six-fold symmetry. But apply higher pressure, and water molecules rearrange into different structures. Ice 2, Ice 3, Ice V, Ice Vi, Ice 7, each is stable in different pressure and temperature regimes. Some are denser than liquid water and sink. Others have bizarre properties. Ice 7 can exist at room temperature if you compress it to extreme pressures, millions of atmospheres. Ice X, predicted to exist at even higher pressures, has hydrogen bonds so compressed that hydrogen atoms sit midway between oxygen atoms, creating a symmetric structure. Some exotic ices may exist inside giant planets. Uranus and Neptune likely have thick layers of hot, high-pressure ice, sometimes called superionic ice, where oxygen atoms are locked in a lattice while hydrogen ions flow freely like a liquid. This isn't ice as we know it, but it's a solid phase of water, just under extreme conditions. Ice then is ferroelectric. Its molecules align in a way that creates a permanent electric dipole. Ice 16 is formed by rapidly cooling water at high pressure. Ice Sun then has a structure that was only recently discovered. The diversity is astonishing. Why so many forms? Because water molecules are simple but versatile. Each water molecule can form hydrogen bonds with up to 4 neighbors. Depending on pressure and temperature, molecules arrange themselves into different networks. Some open and low density, others compact and high density, some ordered, others disordered. Understanding ice phases isn't just academic, it's relevant to planetary science. The icy moons of Jupiter and Saturn likely contain exotic ice phases in their deep interiors, affecting their structure and potential for subsurface oceans. It's relevant to understanding Earth's history. At high pressures in subducting slabs, water might transform into dense ice phases, affecting how water is transported into the mantle. It's even relevant to food science. The formation of ice crystals affects texture in frozen foods, and there's beauty in the diversity. Water, the most familiar substance, harbors complexity and variety we're still discovering. Even something as simple as frozen water has depth, has phases and structures and possibilities that require extreme conditions to reveal. Tonight, if there's ice in your freezer, it's ice IH, hexagonal, ordinary, the form stable at everyday pressures. But in laboratories, scientists are creating and studying other ice phases, compressing and heating water, exploring the phase diagram, discovering new forms. And deep in giant planets, exotic ices exist in conditions we can barely replicate. structures we can only model and predict. Maybe there's a lesson in ice's diversity. Things that seem simple often aren't. Familiar things have hidden depths, and conditions matter. Change the pressure, the temperature, the context, and you get something completely different from the same starting material. Water is water, but ice is many things, depending on where and how it forms. Maybe people are like that too, the same essential substance, but taking different forms depending on conditions, on pressure, on temperature, on what life throws at them. And maybe that's not inconsistency, but flexibility, adaptability, the ability to exist in multiple forms while remaining fundamentally yourself. So as you rest tonight, perhaps appreciate the complexity hidden in simplicity, the variety within sameness, the many forms that emerge from a single substance, and maybe extend that appreciation to yourself, to others, recognizing that we're all water, in a sense, capable of many forms, shaped by conditions, sometimes frozen, sometimes flowing, sometimes under such pressure we transform into something exotic, almost unrecognizable, but still fundamentally us. And maybe that's okay. Maybe that's beautiful. Maybe that's just how it is to be, made of simple components that can arrange in infinite ways, taking the form that fits the moment, the pressure, the temperature of life. Rest in whatever form you're in right now. It's the right form for this moment, this pressure, this temperature. And tomorrow, maybe you'll be a different form, and that's okay too. You're still you, still water, still capable of flowing, freezing, transforming, enduring. And that's enough. That's everything. The discovery of circadian rhythms showed that living organisms have internal clocks that track the 24-hour day-night cycle. You get sleepy at night, you wake in the morning. Your body temperature fluctuates through the day. You get hungry at regular times. These aren't just learned habits. They're driven by internal biological clocks, circadian rhythms that operate even without external time cues. Circadian comes from Latin, circa, about, and dies, day, about a day. The rhythms aren't exactly 24 hours. They're usually a bit longer, around 24.2 hours in humans. But they're close, and they synchronize to the actual 24-hour day through light exposure and other cues. The existence of circadian rhythms was discovered by observing organisms in constant conditions. In the 1700s, French scientist Jean-Jacques Dortu de Mairan noticed that mimosa plants opened their leaves during the day and closed them at night. Even when kept in complete darkness, the rhythm persisted without light cues, suggesting an internal timer. Similar experiments with animals, including humans, confirmed internal clocks. People isolated in caves or bunkers with no time cues still maintain roughly 24-hour sleep-wake cycles, though they tend to drift slightly longer or shorter than 24 hours, showing the clock is internal but usually needs daily resetting by light. The molecular basis was discovered in the 1970s and 80s. Circadian rhythms are generated by clock genes that form feedback loops. Certain genes are transcribed, producing proteins that accumulate, then inhibit their own transcription, then degrade, allowing transcription to start again. This cycle takes about 24 hours. Different tissues have their own clocks, coordinated by a master clock in the brain's suprachiasmatic nucleus, which receives light input from the eyes. Circadian rhythms regulate much more than sleep. Body temperature, hormone release, blood pressure, immune function, metabolism, cell division. Many processes follow daily rhythms. Disrupting these rhythms through shift work, jet lag, or irregular schedules can harm health, increasing risk of obesity, diabetes, cardiovascular disease, cancer, and mental health problems. Light is the primary synchronizer. Blue light especially affects the circadian clock, suppressing melatonin production and signaling daytime. This is why bright screens before bed can interfere with sleep. They trick your brain into thinking it's still daytime. Conversely, morning light exposure helps synchronize the clock, promoting alertness during the day and sleepiness at night. Circadian rhythms exist in nearly all organisms, from bacteria to plants to animals. They evolved because they provide adaptive advantages, allowing organisms to anticipate daily changes, to be active when conditions are favorable, to coordinate internal processes with external cycles. Even cyanobacteria have circadian clocks, helping them time photosynthesis to daylight hours. The 2017 Nobel Prize in Physiology or Medicine was awarded for discoveries about circadian rhythms. The work revealed how life has internalized the rotation of the planet, how evolution has built clocks into cells, how organisms are synchronized not just to each other but to Earth itself, to the daily spin that creates day and night. Tonight, as you prepare for sleep, your circadian clock is signaling that it's night. Melatonin levels are rising, making you drowsy. Body temperature is dropping. Alertness is fading. Your brain is shifting into sleep mode, preparing for the rest and restoration that nighttime brings. This isn't just fatigue. It's your biology following rhythms refined over millions of years, rhythms that connect you to the spinning earth, to the cycle of light and dark, to the ancient patterns of day and night. And when morning comes, your clock will signal awakening. Melatonin will drop, cortisol will rise, body temperature will increase. You'll naturally become more alert, your body preparing for activity, synchronized to the day. You are, quite literally, a creature of Earth's rotation. Your internal timekeeping exists because the planet spins, because day follows night, because evolution found it advantageous to anticipate and prepare for predictable changes. You're synchronized to the cosmos at a fundamental biological level, your cells keeping time with the planet, your rhythms harmonizing with the spin that's been constant for billions of years. We learned that Earth's atmosphere has distinct layers with different properties, from the troposphere to the exosphere. Above you, the atmosphere extends upward in layers, each with different characteristics, different compositions, different roles in the system that makes Earth habitable. You live at the bottom of an ocean of air, miles deep, held by gravity, protecting and sustaining life. The lowest layer, where you breathe and live, is the troposphere. It extends from the surface to about 7 miles up at the poles, 12 miles at the equator. This is where weather happens. Clouds form, storms brew, rain falls. Temperature decreases with altitude in the troposphere, which is why mountain peaks are cold. Most of the atmosphere's mass, about 75%, is in this layer, compressed by gravity near the surface. Almost all water vapor is here too, which is why weather is confined to the troposphere. Above the troposphere is the stratosphere, extending to about 30 miles up. Here, something interesting happens. Temperature increases with altitude. This is because of the ozone layer, which absorbs ultraviolet radiation from the sun, converting UV energy to heat. The stratosphere is stable and calm. Jets fly here to avoid turbulent weather. The air is thin, dry, and clear. Above that is the mesosphere, extending to about 50 miles up. Temperature drops again with altitude here, reaching the coldest temperatures in Earth's atmosphere, around 130 degrees, 90 degrees at the mesopause, the boundary with the next layer. Meteors burn up in the mesosphere, friction with the thin air heating them to incandescence. Those shooting stars you see are typically happening 40 to 60 miles overhead in the mesosphere. The thermosphere extends from about 50 miles to 400 miles or more. Temperature increases dramatically with altitude here, reaching up to 3,600 degrees, 2,000 degrees C. Though temperature is misleading, the air is so thin that there are very few molecules to transfer heat. You wouldn't feel hot here. You'd freeze from radiating your own heat into near vacuum. The International Space Station orbits in the thermosphere, about 250 miles up. Auroras occur here too, as charged particles from the sun collide with atmospheric gases, exciting them to glow. Finally, the exosphere, the outermost layer, gradually fading into space. There's no clear boundary. The atmosphere just gets thinner and thinner until it merges with the interplanetary medium. Some satellites orbit in the exosphere. Earth's atmosphere is held by gravity. Lighter gases like hydrogen and helium can escape to space. They move fast enough to exceed escape velocity. That's why Earth's atmosphere is mostly nitrogen and oxygen, heavier gases that remain bound. Mars, with weaker gravity, lost much of its atmosphere over billions of years. Venus, with strong gravity and no magnetic field, has a thick atmosphere but lost its water vapor to space, broken apart by solar radiation. The atmosphere does more than provide air to breathe. It distributes heat. Warm air rises and moves poleward. Cold air sinks and moves equatorward, creating circulation patterns that moderate climate. It blocks harmful radiation. Ozone absorbs UV. Other molecules absorb X-rays and gamma rays. It creates pressure. Air pressure at sea level is about 14.7 pounds per square inch, pushing on you from all directions, balanced by pressure inside your body. It burns up meteors, protecting the surface from most space debris. It scatters light, making the sky blue during the day and red at sunset. And it's surprisingly thin. If Earth were the size of an apple, the atmosphere would be thinner than the apple's skin. The breathable part, the troposphere, would be thinner than the skin's outer layer. We live in a delicate envelope, a thin shell of gas between the solid surface and the vacuum of space. Tonight, as you lie beneath miles of air, consider the layers above you. Weather is happening in the troposphere, clouds drifting, winds blowing. The stratosphere is calm, ozone molecules absorbing. Tomorrow's UV. The mesosphere is cold and dark, perhaps with a few meteors streaking through. The thermosphere glows faintly with auroras near the poles, and satellites zip through, orbiting. And beyond, the exosphere fades into space, the last whispers of Earth's atmosphere mixing with the solar wind. You're at the bottom of it all, pressed gently by 14.7 pounds per square inch of air, held down by gravity, breathing a mixture refined over billions of years to be just right for life like yours. And maybe that's worth a moment of appreciation for the atmosphere, for the layers that protect and sustain, for the delicate balance that makes Earth habitable, for the thin shell of gas that stands between you and the void. The discovery of the strong nuclear force explained what holds atomic nuclei together against the electromagnetic repulsion of protons. Inside every atomic nucleus, there's a battle. protons, all positively charged, should repel each other violently, like charges repel, and the electromagnetic force pushing them apart is enormous at such close distances. A nucleus with multiple protons should fly apart instantly. And yet, it doesn't. Something holds it together. That something is the strong nuclear force, the strongest force in nature. It's what binds protons and neutrons together in the nucleus, overcoming electromagnetic repulsion, creating stable atoms. Without it, only hydrogen, with its single proton, could exist. There would be no carbon, no oxygen, no heavy elements, no chemistry, no complexity, no life. The strong force was discovered gradually through experiments in the early to mid-1900s. Physicists probing the nucleus found that protons and neutrons were bound by a force much stronger than electromagnetism, but with a crucial difference. It only operates over incredibly short distances, about the diameter of a proton, 10-15 meters. Beyond that, it drops to zero almost instantly. This short range is key. At distances larger than a nucleus, the strong force doesn't matter. Atoms interact through electromagnetism. But inside the nucleus, the strong force dominates, binding protons and neutrons, collectively called nucleons, into a tight cluster. It's like incredibly strong glue that only works if things are already touching. The strong force doesn't care about electric charge. It binds proton to proton, neutron to neutron, proton to neutron, all equally. This is why neutrons help stabilize nuclei. In small nuclei, the number of protons and neutrons is roughly equal. But larger nuclei need more neutrons than protons because electromagnetic repulsion grows stronger as more protons are added. Extra neutrons don't add to the repulsion, they're neutral, but do contribute strong force attraction, helping to hold the nucleus together. There's a limit, though. Beyond a certain size, around 209 nucleons, the size of bismuth, nuclei become unstable. Add more protons, and electromagnetic repulsion overcomes even the strong force's efforts, bolstered by neutrons. This is why elements heavier than bismuth are radioactive. Their nuclei eventually break apart through decay processes, seeking more stable configurations. The strong force is mediated by particles called gluons, which glue quarks together inside protons and neutrons. And actually, the force binding protons and neutrons in a nucleus is a residual effect of the more fundamental force binding quarks inside nucleons. It's like how molecules can stick together through residual electromagnetic forces, even though they're electrically neutral overall. The details are complex, involving quantum chromodynamics, but the result is simple. The strong force holds nuclei together. Nuclear energy comes from the strong force. In nuclear fission, a heavy nucleus splits into smaller ones. The smaller nuclei are more tightly bound per nucleon, so energy is released. The difference in binding energy, converted to heat and radiation. In nuclear fusion, light nuclei combine into heavier ones. Again, the product is more tightly bound, releasing energy. The sun's power comes from fusion, hydrogen nuclei combining to form helium, releasing energy through the strong force's rearrangement. Understanding the strong force was crucial for understanding atoms, nuclear physics, particle physics, stars, the origin of elements. It's one of the four fundamental forces, along with electromagnetism, weak nuclear force, responsible for radioactive decay, and gravity. These four forces govern everything in the universe, and the strong force is the strongest, about 100 times stronger than electromagnetism, 1,000,000 times stronger than the weak force, and unimaginably stronger than gravity at nuclear scales. Yet you never feel it directly because its range is so short. It's hidden inside every atom, invisible, working only at scales trillions of times smaller than anything you can see, but utterly essential. Tonight, as you rest, every atom in your body contains a nucleus held together by the strong force. Trillions upon trillions of protons and neutrons bound against electromagnetic repulsion, stable because of the strongest force in nature working at the smallest scales. The carbon, nitrogen, oxygen in your body, all forged in stars through fusion, assembled through the strong force, then scattered by supernovae, eventually becoming you. You're built from nuclear physics. The forces inside atomic nuclei, invisible and unimaginably strong, are what allow complex atoms to exist, what allow chemistry, what allow life. Without the strong force, the universe would be only hydrogen, boring, simple, incapable of producing anything interesting. But with it, elements form, chemistry happens, planets coalesce, life emerges, consciousness arises. We found that water is most dense at 39 degrees, not at its freezing point, which is why ice floats. Water is weird. It's so familiar that its strangeness is easy to miss. But it breaks the rules in ways that are crucial for life. One of the strangest properties is how its density changes with temperature. For most substances, the solid form is denser than the liquid. Molecules pack more tightly in a solid crystal. When you freeze most liquids, they sink in their own liquid form, but ice floats in water. Why? Water reaches its maximum density at about 39 degrees C, 4 degrees C, a few degrees above freezing. As water cools below this temperature, it actually becomes less dense. When it freezes at 32 degrees, 0 degrees C, it expands, becoming about 9% less dense than liquid water. This is why ice floats and why pipes burst when water freezes inside them. The expansion exerts enormous pressure. The reason for this anomaly is hydrogen bonding. Water molecules are polar, slightly negative near the oxygen, slightly positive near the hydrogens. This allows them to form hydrogen bonds with neighboring molecules. In liquid water, these bonds constantly form and break, allowing molecules to pack relatively closely. But as water cools toward freezing, molecules slow down and hydrogen bonds become more stable. The bonds arrange molecules into a hexagonal crystal structure, ice age, which has more empty space than liquid water. The molecules are locked in place in an open lattice, held at specific distances and angles by hydrogen bonds. This open structure is less dense than the liquid, so ice floats. If ice didn't float, Earth would be a very different place. When lakes and oceans froze in winter, ice would sink to the bottom. More ice would form at the surface and sink, gradually filling bodies of water with ice from the bottom up. Eventually, most water would be frozen solid, year-round, even in summer, because ice at the bottom would be insulated from melting. Only a thin surface layer might thaw temporarily. But because ice floats, it forms an insulating layer on top. Water below remains liquid, protecting aquatic life through winter. Fish, plants, and other organisms survive beneath the ice. When spring comes, the ice melts from the top down and life continues. This property also affects global climate. Floating sea ice reflects sunlight, cooling the planet. But it also insulates the ocean beneath, moderating heat loss. The balance between these effects is delicate and important for climate stability. Water's maximum density at 4 degrees C also creates interesting circulation patterns in lakes. As surface water cools in autumn, it becomes denser and sinks, replaced by warmer water from below. This continues until the entire lake reaches 4-degree maximum density. Further cooling makes surface water less dense, so it stays on top, eventually freezing. In spring, surface ice melts and the process reverses. This overturn mixes nutrients and oxygen through the water column, crucial for aquatic ecosystems. Water's weirdness doesn't stop there. It has an unusually high heat capacity. It takes a lot of energy to change its temperature. This moderates climate, preventing extreme temperature swings. It has high heat of vaporization. It takes a lot of energy to evaporate water, which is why sweating cools you efficiently. It's a universal solvent, dissolving more substances than any other liquid, enabling chemistry and biology. All these properties stem from water's molecular structure and hydrogen bonding. They're interconnected, each one contributing to making water the perfect medium for life. Life as we know it evolved in water, depends on water, is mostly made of water. The human body is about 60% water by weight. Your cells, your blood, your brain, all aqueous solutions, chemistry happening in water, enabled by its unique properties. Tonight, as you rest, your body is regulating water, maintaining hydration, balancing electrolytes, filtering blood through kidneys, producing sweat or urine as needed. Water flows through you constantly, carrying nutrients, removing waste, moderating temperature, enabling reactions. You're a walking water system, a temporary pattern organized in aqueous solution, held together by chemistry that only works because water is weird in exactly the right ways. And outside, water cycles through the environment, evaporating from oceans, forming clouds, falling as rain, flowing in rivers, seeping into ground, perhaps freezing into ice that floats, protecting life below, reflecting sunlight, moderating climate. The water cycle, powered by solar energy, distributing water globally, making continents habitable, has been running for billions of years, sustaining life, shaping landscapes, regulating climate. The discovery of the Doppler effect showed that waves get compressed or stretched depending on the motion of their source. You've heard it countless times. An ambulance approaching, its siren high-pitched and urgent. As it passes, the pitch drops noticeably, the sound becoming lower, more stretched out. The siren itself doesn't change, but your perception of it does because of relative motion. This is the Doppler effect, named for Austrian physicist Christian Doppler, who described it in 1842. The principle is simple but profound. Sound travels as waves at a fixed speed through air, about 770 meters at sea level. When a sound source moves towards you, it catches up with its own waves, compressing them. The wavelength decreases, frequency increases, and you hear a higher pitch. When the source moves away, it stretches the waves. Wavelength increases, frequency decreases, pitch drops. Doppler used sound as an example, but he predicted the effect should apply to all waves, including light. He was right. Light from an approaching source is shifted toward shorter wavelengths, bluer, blue shift. Light from a receding source is shifted toward longer wavelengths, redder, red shift. This has enormous implications for astronomy. When Edwin Hubble studied distant galaxies in the 1920s, he found their light was redshifted, shifted toward longer wavelengths. This meant galaxies were moving away, and the farther away a galaxy, the greater its redshift, meaning faster recession. This was evidence that the universe is expanding. Today, astronomers use Doppler shifts routinely to measure velocities. A star's spectrum shows characteristic absorption lines at specific wavelengths. If those lines are shifted toward red, the star is moving away. Toward blue, it's approaching. By measuring the shift, astronomers calculate the velocity. This technique has detected planets orbiting other stars. As a planet orbits, its gravity tugs on the star, causing the star to wobble slightly, moving toward Earth, then away, in a periodic pattern. The star's spectral lines shift back and forth accordingly, blue, then red, then blue again. By measuring these tiny shifts, sometimes less than a meter per second, astronomers have found thousands of exoplanets. Doppler is also used in weather radar. Radar sends out radio waves and measures reflections from raindrops. If drops are moving toward the radar, strong winds approaching, the reflected waves are blue shifted. Moving away, red shifted. This allows meteorologists to measure wind speeds inside storms, identifying rotation that might spawn tornadoes. Police radar guns use Doppler too, measuring the shift in reflected radio waves to calculate a vehicle's speed. Medical ultrasound uses Doppler to measure blood flow. Sound waves reflected from moving blood cells shift in frequency, allowing doctors to see how fast blood is flowing and in which direction, identifying blockages or abnormalities. The Doppler effect is evidence of something fundamental. Waves have objective existence independent of source and observer, but perception depends on relative motion. It connects motion and frequency, space and time, in ways that foreshadowed relativity. At high velocities approaching light speed, relativistic Doppler effects occur. Time dilation and length contraction combine with classical Doppler, creating more complex shifts that have been precisely measured and confirmed. Tonight, sounds around you are Doppler shifted if their sources are moving. A passing car, a flying insect, even your own voice if you move your head while speaking, all subject to Doppler. Mostly the effects are small, unnoticed, but they're there, subtle distortions of frequency caused by motion, evidence of the wave nature of sound. And light from distant galaxies is streaming toward Earth, redshifted by the expansion of space itself, carrying information about velocities, distances, the universe's structure and evolution. Astronomers observe these shifts, measure them, use them to map the cosmos, to trace its history back to the Big Bang, forward to its eventual fate. The Doppler effect is one of those beautiful unifying principles, applicable to sound, light, water waves, any wave phenomenon. It's math describing reality, equations predicting observations, theory matching experiment. It's science working as it should, revealing patterns, making predictions, connecting seemingly disparate phenomena under common principles. We learned that some materials are liquid crystals, having properties between liquids and solids, the basis for LCD screens. Most matter is either solid, liquid, or gas, molecules locked in place, flowing freely, or dispersed in space. But some materials exist in intermediate states, showing properties of multiple phases simultaneously. Liquid crystals are one such state. They flow like liquids but maintain some molecular order like crystals. In normal liquids, molecules are randomly oriented, tumbling and moving chaotically. In crystals, molecules are fixed in regular arrays, ordered in all three dimensions. Liquid crystals are in between, Molecules can move and flow, but they maintain orientational order, aligned in particular directions, creating structures with symmetry. Several types of liquid crystals exist. Nematic liquid crystals have molecules aligned parallel to each other, but no positional order. They point the same direction, but aren't arranged in a fixed lattice. Smectic liquid crystals have molecules aligned in layers. Cholesteric liquid crystals twist gradually, forming helical structures. Each type has different properties and uses. Liquid crystals were discovered in 1888 by Austrian botanist Friedrich Reinitzer, who noticed that cholesterol benzoate had two melting points. At one temperature, it became a cloudy liquid. At a higher temperature, it became clear. The cloudy state was a liquid crystal phase. For decades, liquid crystals were scientific curiosities with no practical use. Then in the 1960s, researchers discovered that liquid crystals could be controlled with electric fields. Apply a field, and molecules reorient. Remove it, and they relax back. This made them perfect for displays. LCD screens work by sandwiching a liquid crystal layer between polarizing filters. Normally, the liquid crystal twists light polarization, allowing light through. Apply a voltage, and the molecules reorient, blocking light. By controlling voltage pixel by pixel, images form. LCDs revolutionize displays. They're thinner, lighter, and use less power than older cathode ray tubes. They're in phones, computers, TVs, watches, calculators, everywhere. But liquid crystals aren't just technological. They're biologically important too. Cell membranes can exhibit liquid crystal properties. Lipid molecules aligned in bilayers that flow laterally, but maintain structural order. DNA, at high concentrations, forms liquid crystal phases. Even some tissues and bodily fluids show liquid crystal properties, affecting how they respond to stress or flow. Liquid crystals are also beautiful. Because they're ordered, they interact with light in interesting ways, creating iridescent colors. Some cholesteric liquid crystals reflect specific wavelengths depending on temperature, creating thermochromic materials. Mood rings use liquid crystals that change color with temperature. Beetle shells and butterfly wings sometimes contain liquid crystal structures, producing structural coloration, colors from physical structure rather than pigments. The existence of liquid crystals expands our understanding of matter's possible states. Phase isn't binary or even ternary. There are many intermediate states, each with unique properties. Matter is more versatile than simple categories suggest. Between the rigid order of crystals and the chaos of liquids, there's a spectrum of partial order, of structures that flow yet align, of states that defy simple classification. And maybe that's a reminder about value and potential. Things that seem useless or exotic might someday become essential. Research driven by curiosity without immediate application might eventually transform society. Liquid crystals had no clear purpose for a century, but patient research, incremental understanding, eventually revealed their potential. And now they're everywhere, integral to daily life, a bridge between solid and liquid, making possible technologies that define the digital age. The discovery of messenger RNA revealed how genetic information flows from DNA to proteins, the central dogma of molecular biology. DNA holds the instructions for building proteins, but it doesn't build them directly. DNA stays safely in the cell nucleus, protected, stable, preserved. To make a protein, the relevant gene is copied into a temporary messenger molecule, messenger RNA or mRNA, which carries the instructions out to the protein-making machinery in the cytoplasm. This flow of information, DNA to RNA to protein, is called the central dogma of molecular biology, articulated by Francis Crick in 1958. It's the fundamental principle of how genetic information is expressed, how the code in DNA becomes the structures and functions of living cells. The process starts with transcription. An enzyme called RNA polymerase binds to DNA at the start of a gene, unwinds the double helix, and synthesizes mRNA by matching RNA nucleotides to the DNA template. When the gene ends, the mRNA is released. It's a single-stranded copy of one DNA strand, with uracil substituting for thymine. The mRNA then leaves the nucleus and attaches to a ribosome, the cell's protein factory, a complex machine made of ribosomal RNA and proteins. The ribosome reads the mRNA 3 nucleotides at a time. Each 3-nucleotide codon specifies an amino acid. Transfer RNAs, tRNAs, bring the appropriate amino acids, matching their anticodons to mRNA codons. The ribosome links amino acids into a growing protein chain. When a stop codon is reached, the protein is released, ready to fold into its functional shape and do its job, catalyzing reactions, transporting molecules, signaling, providing structure, whatever its function is. mRNA is temporary. After being translated into protein, it's degraded, recycled. This allows cells to control protein production, make more mRNA to increase protein. Levels degrade mRNA to decrease them. It's dynamic, responsive, allowing cells to adapt to changing conditions quickly. Understanding mRNA has revolutionized biology and medicine. Scientists can sequence mRNA to see which genes are active in cells, tissues, or organisms under different conditions. They can compare healthy and diseased tissue, identifying genes that are over or underexpressed in disease. And recently, mRNA has become a medical tool. The COVID-19 mRNA vaccines work by delivering synthetic mRNA encoding the virus's spike protein. Cells translate this mRNA, producing spike protein, which the immune system recognizes as foreign, generating immunity. The mRNA degrades quickly. It doesn't integrate into DNA or persist long-term. It's just temporary instructions that train the immune system, then vanish. This was the first widespread use of mRNA vaccines, but it likely won't be the last. Researchers are developing mRNA therapies for cancer, genetic diseases, infectious diseases. The principle is simple. Deliver mRNA encoding a therapeutic protein. Let the patient's own cells produce it. It's like giving cells a temporary software update, new instructions to execute, then discard. mRNA research won the 2023 Nobel Prize in Physiology or Medicine. Katalin Karikó and Drew Weissman figured out how to modify mRNA to avoid triggering excessive immune responses, making it practical for medical use. Their work, which took decades and overcame skepticism, enabled the rapid development of COVID vaccines and opened a new era of mRNA therapeutics. Tonight, in your cells, mRNA molecules are being transcribed, transported, translated. Genes are being expressed, proteins produced, cellular functions maintained. The flow of information from DNA to RNA to protein continues constantly, driving metabolism, growth, repair, immune function, everything your cells do. You're a walking expression of the central dogma, genetic information flowing from stable DNA archives through temporary mRNA messengers to functional protein workers. Information becomes structure, code becomes chemistry, instructions become life, and all of it mediated by mRNA, humble messengers carrying temporary copies of permanent instructions. enabling the controlled, regulated expression of your genome. We found that the aurora borealis and aurora australis occur when charged particles from the sun interact with Earth's magnetic field. On cold, clear nights near the poles, the sky sometimes dances. Curtains of light shimmer and ripple, green, red, blue, violet, flowing across the heavens in patterns that defy prediction, beautiful beyond words. The northern lights, aurora borealis, the southern lights, aurora australis. Humans have watched them with wonder for thousands of years, inventing myths to explain them, never fully understanding until recently. The aurora begins 93 million miles away on the sun. The sun constantly releases a stream of charged particles, electrons and protons, called the solar wind. This wind flows outward through the solar system at hundreds of miles per second. Sometimes solar storms erupt, coronal mass ejections or solar flares, sending bursts of particles far more intense than the usual wind. When these particles reach Earth, they encounter the magnetosphere, Earth's magnetic field, extending tens of thousands of miles into space. The magnetosphere deflects most particles, channeling them around Earth. But some particles, particularly near the poles where field lines converge, spiral down along magnetic field lines toward the atmosphere. At altitudes around 60 to 200 miles up in the thermosphere, these particles collide with atmospheric gases. Oxygen and nitrogen atoms absorb energy from the collisions, exciting electrons to higher energy levels. When electrons drop back down, they emit photons, light. Oxygen produces green and red colors. Nitrogen produces blue and purple. The specific colors depend on altitude, particle energy, and atmospheric composition. The aurora usually appears as curtains or bands because charged particles follow magnetic field lines, which converge near the poles. The curtains align roughly with those field lines, marking paths particles follow as they spiral down. The aurora is dynamic, shimmering, rippling, changing, because the solar wind varies, because Earth's magnetic field fluctuates, because the interaction is turbulent and chaotic. Auroras aren't unique to Earth. Jupiter, Saturn, Uranus, and Neptune all have auroras, spectacular displays in their thick atmospheres, powered by their strong magnetic fields and interactions with the solar wind. Even Mars has auroras, though without a global magnetic field, they're localized and less dramatic. Humans have long been fascinated by auroras. Indigenous peoples in polar regions have myths explaining them. Spirits dancing, ancestors playing games, reflections from ocean ice, warnings of war. Norse mythology associated them with Bifrost, the rainbow bridge to Asgard. Only in the early 1900s did scientists begin to understand them, with Norwegian physicist Christian Birkeland proposing that they were caused by solar particles interacting with Earth's magnetic field. Today, auroras are monitored by satellites and ground-based cameras. Space weather forecasts predict when strong auroras might occur, warning power companies and satellite operators. Severe magnetic storms can disrupt power grids, damage satellites, interfere with communication. The same processes that create beautiful lights can cause technological problems. But mostly, auroras are just beautiful. They're visible reminders of invisible forces, the solar wind, Earth's magnetic field, the interaction between sun and planet. They're physics made visible, energy converted to light, the cosmos putting on a show. The discovery of radiocarbon dating gave us a clock for measuring the age of organic materials up to about 50,000 years old. Time is hard to measure when you're looking backward. How old is that wooden beam in an ancient building? When did those people live in that cave? How long ago did that mammoth die? For most of history, these questions were unanswerable. We could make guesses, compare artifacts, order things relatively, but absolute dates were elusive. Then came radiocarbon dating, discovered by Willard Libby in the 1940s, which revolutionized archaeology, geology, and anthropology by providing a reliable clock for organic materials. Here's how it works. Carbon exists in three isotopes, carbon-12 and carbon-13, which are stable, and carbon-14, which is radioactive. Carbon-14 forms in the upper atmosphere when cosmic rays strike nitrogen, converting it to carbon-14. This carbon-14 combines with oxygen, forming CO2, which mixes through the atmosphere. Plants absorb it during photosynthesis. Animals eat plants. So all living things contain a small amount of carbon-14, roughly constant as long as they're alive, and exchanging carbon with the environment. But when an organism dies, it stops taking in new carbon. The carbon-14 already present begins to decay, transforming back into nitrogen with a half-life of 5,830 years. Measure how much carbon-14 remains compared to carbon-12, and you can calculate how long ago the organism died. It's not perfect. Carbon-14 levels in the atmosphere have varied over time due to changes in cosmic ray intensity, solar activity, and human activities like nuclear testing. But by calibrating against tree rings, dendrochronology, counting annual growth rings in very old trees, and other methods, scientists have created calibration curves that correct for these variations, making radiocarbon dating accurate to within decades for samples up to about 50,000 years old. Beyond that, too little carbon-14 remains to measure reliably. Radiocarbon dating has answered countless questions. It dated the Dead Sea Scrolls to around 2,000 years ago. It showed that humans reached the Americas at least 15,000 years ago. It dated the Shroud of Turin to the Middle Ages, not to Jesus' time. It's dated fossils, settlement layers, ancient art, artifacts, providing timelines for human history and prehistory. It's also shown us that Earth's recent history is more dynamic than we thought. Ice ages came and went on timescales we can now measure. Civilizations rose and fell at dates we can pinpoint. Extinctions of mammoths, giant sloths, saber-toothed cats occurred at times we can now determine, often suspiciously coinciding with human arrival. Radiocarbon dating doesn't just tell us when, it often hints at why, revealing correlations that suggest causation. Other radiometric dating methods exist for older materials. Uranium lead dating, potassium argon dating, and others use longer-lived isotopes to date rocks millions or billions of years old. These methods dated Earth itself to 4.54 billion years, dated the oldest rocks, dated fossils spanning Earth's history. Together, radiometric dating methods have provided an absolute timeline for Earth's history, from formation to present. Libby won the Nobel Prize in 1960 for radiocarbon dating. His work gave humanity a window into the past, a way to measure time's passage in bones and wood and charcoal, a clock written in atoms, ticking backward through history. We learned that some fungi form vast underground networks connecting multiple trees, called mycorrhizal networks, or the Wood Wide Web. Beneath the forest floor, hidden from sight, a network extends through the soil, fungal threads called hyphae, finer than roots, more extensive than you'd imagine. connecting trees to each other, allowing them to communicate and share resources. It's been called the Wood Wide Web, and it's one of nature's most remarkable collaborative systems. Most trees form partnerships with fungi, mycorrhizal associations. The fungi's hyphae extend from tree roots deep into the soil, vastly increasing the root's effective surface area. The fungi absorb water and nutrients, especially phosphorus and nitrogen, far more efficiently than roots alone could, passing them to the tree. In return, the tree provides sugars produced through photosynthesis, which fungi can't make themselves. But the network does more than just extend individual trees' reach. Hyphae from different trees connect, forming networks that link entire forests. Through these networks, trees can transfer carbon, nutrients, even chemical signals. A large tree, well supplied with light and water, might send sugars through the network to smaller trees in its shade, helping them survive until they're tall enough to reach sunlight. Mother trees, as ecologist Suzanne Simard calls them, can support their offspring this way. The network also facilitates communication. When a tree is attacked by insects, it can release chemical signals through its roots and the fungal network, warning nearby trees. Those trees, forewarned, produce defensive compounds, making themselves less palatable or toxic to the insects. The network is a communication system, carrying information, coordinating responses, allowing forests to act not as collections of isolated individuals, but as interconnected communities. This challenges our understanding of forests. We tend to see trees as individuals, competing for resources, each one out for itself. But the mycorrhizal network reveals cooperation, mutual aid, interdependence. Trees are not alone. They're part of a superorganism, a networked system where resources and information flow between individuals, where the health of one affects others, where cooperation is as important as competition. Not all fungi are cooperative. Some are parasitic, taking without giving. And the mycorrhizal network isn't altruistic. Trees tend to favor their own offspring or close relatives when sharing resources. But overall, the network increases forest resilience, helping the whole ecosystem survive droughts, disease, outbreaks, insect attacks. What benefits the network benefits individuals, so cooperation evolves. Humans are just beginning to understand these networks. They're incredibly complex, involving multiple species of fungi and trees, changing seasonally, responding to environmental conditions, disrupting them through clear-cutting, soil compaction, fungicides, can harm forests' health and resilience. Maintaining them by preserving old-growth trees, protecting soil, avoiding monocultures, supports forest health. The Wood Wide Web is a reminder that what we see above ground is only part of the story. Below, hidden in soil, vast networks connect, communicate, collaborate. Life is interconnected, interdependent, far more cooperative than we often assume. The discovery of semiconductors created the foundation for modern electronics by controlling how materials conduct electricity. Most materials are either conductors, allowing electricity to flow easily, or insulators, blocking it almost completely. Copper is a conductor. Electrons move freely through it. Rubber is an insulator. Electrons can barely move at all. For most of history, electronics worked with these two types of materials, using conductors to carry current and insulators to prevent it. But in the mid-1900s, scientists discovered something more interesting: semiconductors, materials that are neither good conductors nor good insulators, but something in between, and whose conductivity can be precisely controlled. Silicon is the most famous semiconductor. Pure silicon conducts electricity poorly at room temperature. It's not quite an insulator, but far from a good conductor. But add tiny amounts of certain impurities, a process called doping, and you can dramatically change its properties. Add phosphorus, which has extra electrons, and you get N-type silicon, with extra negative charges available to carry current. Add boron, which has fewer electrons, and you get P-type silicon, with holes, where electrons are missing, which can also carry current. The magic happens when you put N-type and P-type silicon together, forming a p-n junction. This junction acts like a one-way valve for electrons. Current flows easily in one direction but not the other. That's a diode. Add a third layer and some electrodes, and you get a transistor, a device that can amplify signals or act as a switch, turning current on or off in response to a control signal. Transistors revolutionized electronics. Before them, electronics used vacuum tubes, bulky, hot, power-hungry devices that performed similar functions but were fragile and inefficient. Transistors were tiny, cool, reliable, and could be made incredibly small. They enabled portable radios, then computers, then integrated circuits with thousands, millions, then billions of transistors on a single chip. The computer or phone you might be using to read this contains billions of transistors, each one a tiny semiconductor switch, turning on and off billions of times per second, processing information, running software, displaying images, connecting to networks, all made possible by our ability to control the flow of electrons through semiconductors. Semiconductors also enabled solar panels, photovoltaic cells that convert light to electricity by using p-n junctions to separate electrons and holes created when photons strike the material. LEDs work in reverse. Passing current through a semiconductor junction causes it to emit light, with the color depending on the material's properties. Lasers, sensors, power electronics, radio frequency devices, all depend on semiconductors. The semiconductor industry is one of the world's largest, most technologically advanced industries. Making modern chips requires atomic-scale precision, ultra-clean environments, incredibly complex processes involving hundreds of steps. Yet the principles are the same as when transistors were first invented, controlling electron flow through junctions of doped semiconductors. Silicon dominates, but other semiconductors exist: germanium, gallium arsenide, silicon carbide, gallium nitride, each with properties suited to different applications. Exotic materials like graphene and carbon nanotubes might enable future generations of even smaller, faster, more efficient electronics. Tonight, semiconductors are all around you, likely within reach. Inside devices you use daily but rarely think about. They're processing these words, displaying them, managing power, sensing inputs, communicating wirelessly, performing billions of operations per second, invisibly and reliably, transforming the abstract language of software into physical actions. Lights turning on, speakers producing sound, screens glowing. And all of it depends on our ability to control conductivity, to dope silicon with precise impurities, to create junctions that valve electrons, to build transistors that switch faster than thought, to integrate billions of them onto fingernail-sized chips. It's one of humanity's greatest technological achievements. Taking silicon, one of Earth's most abundant elements, Sand is mostly silicon dioxide, and transforming it into the substrate of the information age. We learned that sound travels at different speeds through different materials, faster in solids than gases. Sound is vibration passing through matter, molecules bumping into molecules, energy propagating through a medium. How fast it travels depends on what it's traveling through, specifically on how readily molecules transmit those vibrations to their neighbors. In air at room temperature, sound travels at about 770 miles per hour, 343 meters per second. That seems fast until you compare it to light, which travels about 1,000,000 times faster. This is why you see lightning before hearing thunder. Light reaches you almost instantly, but sound takes time, about 5 seconds per mile. But sound moves faster through liquids. In water, sound travels at about 3,300 miles per hour, 2,500 meters per second, more than 4 times faster than in air. Water molecules are closer together, denser, so vibrations transmit more efficiently. This is why whales can communicate across hundreds of miles of ocean. Sound carries far and fast through water, and in solids, sound travels even faster. In steel, it's about 13,000 miles per hour, 5,800 meters per second, nearly 17 times faster than in air. In diamond, sound travels at about 26,000 miles per hour, 12,000 meters per second, the fastest of any material at room temperature. Solid atoms are tightly bound, arranged in regular lattices, so vibrations propagate extremely efficiently. This variation in sound speed has practical implications. When you put your ear to railroad tracks, you can hear trains coming from miles away. Sound traveling through steel reaches you long before sound through air. Native Americans supposedly put their ears to the ground to detect distant buffalo herds or approaching horses. Sound through earth travels faster and farther than through air. Ultrasound imaging in medicine exploits sound speed differences. Sound waves sent into the body reflect differently off different tissues, bone, muscle, fluid, organs, because each has different density and elasticity, affecting how sound propagates. By analyzing reflections, doctors create images of internal structures, monitoring pregnancies, diagnosing conditions, guiding procedures, all using sound. Sonar, sound navigation and ranging, uses sound to probe underwater environments. Submarines, ships, and dolphins use sonar to detect objects, measure distances, map the seafloor. Sound is preferred over light or radio waves underwater because those don't penetrate far in water, but sound does, traveling efficiently through the ocean. Temperature also affects sound speed. Warmer air has faster moving molecules, so sound travels slightly faster, about 1.2 meters per second faster per degree Celsius. This creates interesting effects. On hot days, sound can refract, bending downward toward cooler ground, allowing sounds to carry farther. At night, when air near the ground cools, sound refracts upward, which is why distant sounds sometimes seem louder at night. The speed of sound also defines the Mach number, the ratio of an object's speed to the speed of sound in the surrounding medium. Mach 1 is the speed of sound. Faster than that, and you're supersonic. Planes exceeding Mach 1 create sonic booms, shockwaves where compressed air suddenly expands, producing a loud crack. The boom isn't a one-time event when breaking the barrier. It's continuous as long as the plane travels supersonically, but you only hear it when the shockwave passes over you. Tonight, sounds around you are traveling at different speeds through different media. Vibrations from music, voices, or ambient noise propagate through air at 770 mph. If those vibrations reach walls, they travel through the structure much faster. If you're near water, sounds travel faster through it than through air. Everything is vibrating at different speeds depending on the medium, and yet your brain interprets it all seamlessly, constructing a coherent auditory picture of your environment. The discovery of deep-sea hydrothermal vents revealed entire ecosystems thriving in complete darkness, fueled by chemical energy instead of sunlight. For most of Earth's history, we assumed all life depended ultimately on the sun. Plants capture sunlight through photosynthesis. Animals eat plants or other animals. Even deep-sea creatures eat debris that drifts down from the sunlit surface. Everything traced back to photosynthesis, to energy from the sun. Then in 1977, scientists exploring the Pacific Ocean floor near the Galapagos Islands in the deep-diving submersible, Alvin discovered something astonishing. Hydrothermal vents, underwater geysers spewing superheated water from beneath the seafloor, and around them ecosystems teeming with life. Giant tube worms, clams, mussels, shrimp, crabs, fish, all thriving in complete darkness, 7,000 feet down, far from any sunlight. How? The answer is chemosynthesis. Bacteria near the vents use chemicals in the hot water, especially hydrogen sulfide, as an energy source, converting them into organic compounds without sunlight. These bacteria form the base of the food chain, just as plants do on the surface. Tube worms, lacking mouths or digestive systems, host chemosynthetic bacteria in their tissues, receiving nutrition directly from them. Other organisms graze on bacterial mats or eat creatures that do. It's an entirely sunlight-independent ecosystem, powered by Earth's internal heat, by chemistry, by the planet's geology rather than its star. This was revolutionary. It showed life doesn't need sunlight, doesn't need surface conditions. Life can exist in extreme environments, hot, dark, high pressure, toxic, as long as there's a chemical energy source. And it suggested that life might exist in similar environments elsewhere, in subsurface oceans on Jupiter's moon Europa, or Saturn's moon Enceladus, beneath the ice, around hypothetical hydrothermal vents, in darkness powered by chemistry. Hydrothermal vents come in types. Black smokers spew dark, mineral-rich water, hot enough to melt lead, up to 750 degrees, 400 degrees. White smokers are cooler, producing lighter-colored minerals. The hot water rises through cracks in the seafloor, dissolving minerals from rocks, carrying them upward. When the hot, chemical-rich water meets cold seawater, minerals precipitate out, forming chimney-like structures that can grow dozens of feet tall. Life near vents is adapted to extremes. Tube worms can withstand temperatures that would kill most organisms. Some bacteria thrive at temperatures above water's normal boiling point. The high pressure keeps water liquid even at extreme temperatures. These extremophiles expand our understanding of life's limits, showing that life is more resilient, more adaptable, more versatile than we once thought. Hydrothermal vents might have been where life began. The chemical energy, the gradients between hot and cold, the mineral surfaces, all could have facilitated the chemistry that led to the first self-replicating molecules. It's one of several origin of life hypotheses, and a compelling one given that vents provide energy without requiring the complex machinery of photosynthesis. Vents are also ephemeral. They last for decades or centuries before the geological processes powering them shift, and the vent dies. When a vent shuts down, the ecosystem collapses. Creatures die or migrate, seeking new vents. It's a dynamic, shifting landscape with ephemeral oases of life scattered across the deep sea floor, appearing and disappearing over time, each one a temporary paradise fueled by Earth's internal heat. Exploring vents is challenging. They're deep, dark, and remote. Submersibles must withstand crushing pressure. Sampling requires care. Organisms are fragile, adapted to stable deep-sea conditions, but the discoveries have been extraordinary. New species, new metabolisms, new insights into life's possibilities. We learned that hormones act as chemical messengers that travel through the bloodstream to regulate distant organs and processes. Your body is a collection of organs and tissues that need to coordinate. Heart, lungs, liver, kidneys, muscles, brain, all working together, responding to changing conditions, maintaining balance. But how do they communicate? How does one part know what another is doing, what's needed, when to act? The answer is hormones, chemical messengers produced by glands, released into the bloodstream, traveling throughout the body to reach target cells and organs, triggering responses, regulating processes, coordinating functions. The endocrine system, the network of hormone-producing glands, includes the pituitary, thyroid, adrenals, pancreas, ovaries, testes, and others. Each produces specific hormones that regulate specific functions. Insulin from the pancreas regulates blood sugar. Thyroid hormones regulate metabolism. Cortisol from adrenal glands responds to stress. Growth hormone from the pituitary stimulates growth. Sex hormones regulate reproduction and secondary sex characteristics. Hormones work by binding to receptors on target cells. Like a key fitting a lock, a hormone binds to its receptor, triggering changes inside the cell, activating genes, opening ion channels, starting biochemical cascades. Different cells have different receptors, so a hormone affects only those with matching receptors, allowing specificity even though hormones circulate throughout the body. Hormone systems are complex, involving feedback loops. When blood sugar rises, the pancreas releases insulin, which prompts cells to absorb sugar, lowering blood sugar, which reduces insulin release. When thyroid hormone levels drop, the pituitary releases thyroid-stimulating hormone, which prompts the thyroid to produce more hormone. When levels rise, the pituitary reduces TSH. It's self-regulating, maintaining balance, homeostasis. Disruptions cause problems. Too little insulin causes diabetes. Too much thyroid hormone causes hyperthyroidism, weight loss, anxiety, rapid heartbeat. Too little causes hypothyroidism, weight gain, fatigue, depression. Hormone imbalances can affect mood, energy, growth, metabolism, reproduction, almost every aspect of physiology. Understanding hormones has led to treatments. Insulin therapy for diabetes, hormone replacement for thyroid disorders, menopause, gender transition, contraceptives that regulate reproductive hormones, corticosteroids that reduce inflammation. Hormones are powerful medical tools allowing us to supplement deficiencies, block excesses, regulate processes that have gone awry. Hormones also affect behavior and mood. Adrenaline, epinephrine, triggers the fight or flight response, increased heart rate, dilated pupils, energy mobilization. Oxytocin promotes bonding, trust, social connection, released during childbirth, nursing, hugging, sex. Serotonin regulates mood, sleep, appetite. Cortisol responds to stress but can cause problems if chronically elevated. Hormones bridge body and mind, physiology and psychology, showing that mood, emotion, and mental states have chemical bases. Even the sense of hunger and fullness is hormonal. Ghrelin, produced by the stomach, signals hunger. Leptin, from fat cells, signals satiety. Disruptions in these hormones can contribute to obesity, eating disorders, metabolic problems, and hormones change throughout life. Puberty is driven by sex hormones transforming child bodies into adult ones. Pregnancy involves dramatic hormonal changes, supporting fetal development and preparing for birth. Aging brings hormonal declines, menopause, andropause, changes in growth hormone, and thyroid function. Hormones shape the arc of life, orchestrating development, reproduction, aging. The discovery of the fossil record provided a timeline of life's history, showing how species changed and when major groups appeared. Earth is a library, and fossils are its books, a record of life spanning billions of years, preserved in stone, waiting to be read. Each fossil is a snapshot, a moment frozen in time, showing what lived, where, when, and how. Together they tell the story of life's evolution, its diversification, its extinctions and recoveries, its long, slow transformation from simple cells to the complexity we see today. Fossils form rarely. Most organisms decay without trace, but occasionally conditions are right: rapid burial in sediment, lack of oxygen, mineral-rich water. Hard parts, shells, bones, teeth, are most likely to fossilize. Soft tissues rarely preserve except under special conditions. Still, over millions of years, countless organisms have been buried, and some fraction has fossilized, scattered through sedimentary rocks worldwide. Studying fossils reveals patterns. The oldest rocks contain only simple, single-celled organisms, bacteria and archaea. For about 2 billion years, that's all there was. Then, around 2 billion years ago, more complex cells, eukaryotes, appear. Around 600 million years ago, multicellular organisms emerge. And about 540 million years ago, during the Cambrian explosion, most major animal groups appear suddenly in the fossil record, diversifying rapidly. The fossil record shows extinctions, 5 major mass extinctions, and many smaller ones. The Permian-Triassic extinction, 252 million years ago, killed about 96% of marine species. The Cretaceous-Paleogene extinction, 66 million years ago, killed the non-avian dinosaurs. Each extinction was followed by recovery and diversification, with surviving lineages radiating into vacant ecological niches. Fossils also show transitions, intermediate forms linking major groups. Tiktaalik, a 375-million-year-old fossil, has features of both fish and tetrapods, limb-like fins, a mobile neck, a flat head, showing the transition from water to land. Archaeopteryx, from 150 million years ago, has features of both dinosaurs and birds, feathers and wings, but also teeth and a bony tail, showing the transition from reptiles to birds. These transitional fossils fill gaps, demonstrating that evolution proceeds through gradual change, not sudden leaps. The fossil record is incomplete. A tiny fraction of organisms fossilize, and a tiny fraction of fossils are discovered. But it's good enough to reveal major patterns, to trace lineages, to date events, to show that life has changed dramatically over time, that today's species are descended from different forms, that evolution is not speculative but documented in stone. Paleontology, the study of fossils, has revealed Earth's deep history. We know that life began at least 3.5 billion years ago. We know photosynthesis evolved early. Oxygen accumulated. The atmosphere changed. We know life was confined to oceans for billions of years before colonizing land. We know plants came before animals on land, insects before vertebrates. We know dinosaurs dominated for 165 million years before being wiped out. We know mammals diversified after dinosaurs' extinction, eventually giving rise to primates, and eventually us. Fossils also reveal environments. Marine fossils in mountain ranges show that areas now high were once underwater. Desert fossils show ancient wetlands. Tropical fossils in Antarctica show the continent was once warm. The fossil record is also a record of Earth's changing climates, geographies, ecosystems. And fossils humble us. Humans are recent. Our genus, Homo, appeared about 2.5 million years ago, a blink in geological time. Anatomically modern humans emerged around 300,000 years ago. Agriculture started 10,000 years ago. Civilization is even more recent. We're newcomers, latecomers to a story billions of years old, one recent chapter in a very long book. We found that Earth's moon likely formed from debris after a Mars-sized object crashed into the early Earth about 4.5 billion years ago. Look up at the moon. It's been there your entire life. A familiar presence in the night sky, waxing and waning, pulling tides, lighting darkness. But where did it come from? For most of history, no one knew. It seemed eternal, always present, a natural companion to Earth. But the moon is strange. It's unusually large compared to Earth, about 1/4 Earth's diameter, much larger relative to its planet than most moons. Its composition is similar to Earth's mantle, but different from its core. It has very little iron, and its orbit is tilted slightly relative to Earth's equator, which is odd if it formed alongside Earth. In the 1970s, scientists studying moon rocks brought back by Apollo missions developed the giant impact hypothesis. About 4.5 billion years ago, early in Earth's history, a Mars-sized protoplanet, nicknamed Theia, collided with Earth. The impact was catastrophic, vaporizing Theia and blasting huge amounts of material from Earth's mantle into orbit. This debris cloud gradually coalesced, pulled together by gravity, forming the moon. This explains the moon's properties. It's made mostly of material from Earth's mantle, explaining the similar composition but lack of iron, which sank to Earth's core before the impact. It's large because the impact was massive. Its orbit is tilted because the collision was oblique, not head-on. Computer simulations support the giant impact hypothesis. They show that such collisions were common during the solar system's early, chaotic phase, when planets were still forming, when protoplanets orbited crowded regions, when collisions and mergers were frequent. The impact that formed the moon was violent, but not unusual. The impact had other effects. It likely melted Earth's surface, creating a magma ocean that took millions of years to cool. It tilted Earth's axis. Without the moon, Earth's axis might be different, affecting climate and seasons. It gave Earth angular momentum, setting our day length. Initially, the day was only about 5 hours long. Over billions of years, tidal interactions between Earth and Moon have gradually slowed Earth's rotation and pushed the Moon farther away. The Moon is still receding, about 1.5 inches per year. The Moon has profoundly affected Earth. Its gravity creates tides, twice daily rises and falls of ocean levels. Tides may have been crucial for life's emergence, creating tidal pools where chemistry could concentrate, where early organisms could adapt to varying conditions. Tides also dissipate energy, gradually slowing Earth's rotation, stabilizing its axis. The moon stabilizes Earth's axial tilt. Without the moon, Earth would wobble chaotically over millions of years, causing extreme climate variations, sometimes with poles pointed at the sun, sometimes equator on. This instability might have prevented complex life from evolving. Mars, lacking a large moon, wobbles dramatically, contributing to its harsh, variable climate. And the moon lights the night. Before artificial lighting, moonlight extended useful time, allowing nocturnal activity, navigation, hunting, gathering. Many species evolved to exploit lunar cycles. Corals spawn during specific moon phases. Sea turtles nest by moonlight. Some animals hunt or hide depending on moon brightness. The moon shaped life's rhythms, Earth's ecosystems, human culture. Myths and religions have revered the moon. It's been a god, a goddess, a guide, a symbol of change and renewal. Calendars were based on lunar cycles, festivals aligned with moon phases. The moon has appeared in poetry, art, music, science fiction, human imagination for millennia. It's humanity's closest celestial neighbor, the only other world we've walked on, a companion that's shaped our planet and our species. The discovery of interference patterns proved light travels in waves, creating bright and dark bands where waves reinforce or cancel. Light seems simple. It travels straight, bounces off mirrors, bends through lenses. For a long time, scientists debated whether light was made of particles or waves. Newton favored particles. Others disagreed. The debate lasted for centuries. Then, in 1801, Thomas Young performed a simple but profound experiment. He shone light through two narrow slits close together, projecting the result onto a screen. If light were particles, you'd expect two bright lines on the screen, one behind each slit. But that's not what he saw. Instead, Young saw multiple bright and dark bands, an interference pattern. Bright bands where light waves from the two slits arrived in phase, reinforcing each other. Dark bands where waves arrived out of phase, canceling each other. It was unmistakable evidence that light travels as waves. Particles don't interfere like that, but waves do, just as water waves can combine to form larger waves, or cancel to form flat spots. Interference requires waves. When two waves overlap, their amplitudes add. If crests meet crests, they reinforce. Constructive interference, creating bright bands. If crests meet troughs, they cancel. Destructive interference, creating dark bands. Light does this, proving it's a wave. But light is strange. The double-slit experiment becomes even weirder with quantum mechanics. If you send photons, light particles, through the slits one at a time, the interference pattern still appears, slowly, photon by photon. Each photon seems to go through both slits simultaneously, interfering with itself. If you try to observe which slit a photon goes through, the interference pattern disappears. The act of observation changes the outcome. Light is both wave and particle depending on how you measure it. Wave-particle duality, central to quantum mechanics. Interference isn't just theoretical, it's practical. Interferometers use interference to make incredibly precise measurements. LIGO detected gravitational waves by measuring interference patterns in laser light. When gravitational waves passed through, they stretched space, changing the light's path slightly, altering the interference pattern by a fraction of a proton's width. That tiny change confirmed Einstein's prediction and opened a new way to observe the universe. Thin films, soap bubbles, oil slicks, butterfly wings show iridescent colors due to interference. Light reflects from the top and bottom surfaces of the film. the two reflections interfere. Depending on the film's thickness and the light's wavelength, some colors interfere constructively, bright, others destructively, dark, creating shifting rainbow patterns as the film's thickness varies. Anti-reflective coatings on glasses use interference. A thin coating is designed so that light reflecting from the coating's surface interferes destructively with light reflecting from the glass surface beneath, canceling reflections, making lenses clearer. Holography uses interference to record three-dimensional images. A hologram captures the interference pattern between a reference light beam and light reflected from an object. When illuminated correctly, the hologram reconstructs the original light field, creating a 3D image. Interference shows that light is more complex than it appears. It's not just particles flying through space or simple rays obeying reflection and refraction. It's waves, electric and magnetic fields oscillating, propagating, interfering, creating patterns that particles never could. We learned that some materials can remember their original shape after being deformed, called shape memory alloys. Most materials, when bent or stretched, either stay deformed or spring back immediately. But shape memory alloys are different. You can deform them, twist them into new shapes, and they'll stay that way until you heat them. Then, remarkably, they remember their original shape and return to it, untwisting, straightening, recovering. The most common shape memory alloy is nitinol, a nickel-titanium alloy discovered in the 1960s at the Naval Ordnance Laboratory, hence the name Nickel-Titanium Naval Ordnance Laboratory. Nitinol can be trained to remember a shape, then deformed at low temperatures. Heated, sometimes just to body temperature, and it snaps back to the remembered shape. The effect comes from a phase transition. At low temperatures, nitinol is in a martensitic phase, a crystal structure that's flexible, easy to deform. At higher temperatures, it transforms to an austenitic phase, a more rigid structure. The austenite phase remembers the original shape. When you heat deformed martensite, it transforms to austenite, which has a different crystal structure that forces the material back into its trained shape. Shape memory alloys have fascinating applications. In medicine, nitinol stents can be compressed into a small size, inserted into blood vessels, then expand to full size at body temperature, propping open arteries. Orthodontic braces use nitinol wires that exert constant gentle pressure as they try to return to their original shape, gradually moving teeth. Surgical tools made of nitinol can be inserted through small incisions, then change shape inside the body. In engineering, shape memory alloys are used in actuators, devices that convert heat into motion. Heat the alloy, and it changes shape, doing work. Cool it, deform it back, heat it again, and it repeats. They're used in thermostats, safety valves, couplings that tighten when heated, antennas that deploy when satellites leave Earth's shadow, and warm in sunlight. In robotics, shape memory alloys enable soft, flexible actuators that contract like muscles when heated. They're quieter, lighter, and simpler than motors, though slower and less powerful. They mimic biological muscles more closely than traditional actuators. Shape memory isn't unique to alloys. Shape memory polymers exist too, plastics that remember their original shape and recover when heated or exposed to light or other triggers. These might enable self-healing materials, deployable structures, adaptive textiles. The idea that materials can remember is poetic, It's not conscious memory, of course. It's just crystallography, phase transitions, thermodynamics. But the effect feels almost magical, like the material knows what it should be and returns to that state when conditions allow. And maybe that's a metaphor worth holding. Maybe we're shape memory materials in a sense. Life deforms us. Stress, trauma, hardship, circumstances bend us, twist us into shapes we didn't choose. And sometimes we stay that way for a long time, adapted to pressure, accepting deformation as permanent. But maybe, given the right conditions, warmth, safety, support, time, we can remember our original shape, our authentic self, who we were or who we were meant to be before deformation. Maybe recovery is possible. Maybe return is possible. Maybe we can snap back, not to exactly what we were. Materials aren't quite the same after cycling. They fatigue. They change slightly. But to something recognizable, something closer to the shape we remember, the self we were trained to be. The discovery of mirror neurons revealed brain cells that fire both when performing an action and when watching someone else do it. In the 1990s, neuroscientists studying macaque monkeys noticed something unexpected. They were recording activity from individual neurons in the motor cortex, the brain area that plans and executes movements. Certain neurons would fire when a monkey reached for a peanut, which made sense. Motor neurons controlling reaching. But then by accident, a researcher reached for a peanut while a monkey watched. And the same neurons fired, even though the monkey wasn't moving, just observing. These neurons seemed to mirror the observed action, as if the monkey were performing it internally. They called them mirror neurons. Further research showed that mirror neurons activate during both action and observation. When you pick up a cup, certain neurons fire. When you watch someone else pick up a cup, the same neurons fire. Your brain simulates the observed action, running an internal model of what you're seeing. This has profound implications for understanding social cognition. Mirror neurons might be the basis of imitation learning, how children learn by watching, how we pick up skills by observing others. They might underlie empathy. When you see someone in pain, mirror neurons simulate that pain, allowing you to feel what they feel, literally sharing their experience. They might be involved in understanding others' intentions. By simulating observed actions, your brain predicts what will happen next, what the person is trying to do, what they're thinking. You don't just see actions, you understand them because you're internally simulating them, running them through your own motor system. Mirror neurons were found in humans too, though studying individual neurons in living human brains is difficult. Brain imaging shows that similar regions activate during both action and observation. When you watch someone smile, your facial motor areas activate slightly, as if you're about to smile too. You might even smile slightly without realizing, mirroring the expression, feeling the emotion it represents. Some researchers think mirror neuron dysfunction might contribute to autism. Difficulties with empathy, imitation, understanding others might stem from impaired mirroring. But this is controversial, not yet proven. Mirror neurons are part of social cognition, but probably not the whole story. Mirror neurons blur the line between self and other. When you watch someone act, your brain reacts as if you're acting. The boundary between observing and doing becomes fuzzy. You're not passive when watching. You're actively simulating, participating internally, mirroring. This might be why watching skilled performances is pleasurable. Athletes, dancers, musicians, your mirror neurons activate, letting you vicariously experience the action, the skill, the flow. It's not the same as doing it yourself, but it's not just passive observation either. It's somewhere in between, engaged simulation. And maybe this explains why stories, movies, books affect us emotionally. When you read about a character's actions, mirror neurons simulate them. When a character suffers, you feel distress. When they triumph, you feel joy. Fiction works because mirror neurons blur the line between real and imagined, self and other, allowing you to experience lives you've never lived, to feel emotions triggered by others' situations. We found that comets are dirty snowballs of ice and rock from the outer solar system that develop tails when approaching the sun. For most of history, comets were omens, harbingers of change, disaster, divine messages. They appeared unpredictably, blazing across the sky with glowing heads and streaming tails, unlike anything else in the heavens. Kings feared them. Priests interpreted them. No one understood what they were or where they came from. Now we know. Comets are ancient remnants from the solar system's formation, icy bodies that have remained mostly unchanged for 4.6 billion years, wandering the outer reaches of the solar system in vast, elongated orbits. Most of their lives, they're dark, frozen, invisible. Chunks of ice, dust, and rock drifting through the cold darkness beyond Neptune. But occasionally, gravitational perturbations from passing stars, from the giant planets, nudge a comet's orbit, sending it falling inward toward the sun. As it approaches, sunlight warms its surface. Ice sublimates, going directly from solid to gas without melting, releasing dust particles trapped in the ice. This creates a glowing atmosphere around the nucleus called a coma, and pressure from solar radiation, and the solar wind pushes gas and dust away, forming two tails. The dust tail is curved, white or yellowish, made of small particles that reflect sunlight. The ion tail is straighter, bluish, made of ionized gas molecules that glow as they're excited by ultraviolet light. Both tails always point away from the sun, pushed by solar wind and radiation pressure. This means that as a comet leaves the inner solar system after passing the sun, it travels tail first. Comet nuclei are small, typically a few miles across, but their tails can extend millions of miles. The coma can be larger than Jupiter. Comets are impressive not because they're massive, but because sunlight makes their dispersed material visible across vast distances. Comets come from two main reservoirs. Short-period comets, orbiting the sun in less than 200 years, come from the Kuiper Belt, a disk of icy bodies beyond Neptune. Long-period comets, taking thousands or millions of years per orbit, come from the Oort cloud, a vast spherical shell of icy objects surrounding the solar system, extending halfway to the nearest star. Edmund Halley in the 1700s realized that comets seen in 1531, 1607, and 1682 were the same object returning periodically, Halley's Comet, which orbits every 75 to 76 years. It last appeared in 1986 and will return in 2061. Its predictability transformed comets from omens to understood celestial mechanics. Comets have collided with Earth. Most burn up in the atmosphere, creating meteor showers, but larger impacts occur. Some scientists think comets brought water and organic molecules to early Earth, contributing to the origin of life. Others think a comet or asteroid impact killed the dinosaurs 66 million years ago. though that object might have been an asteroid rather than a comet. We've sent spacecraft to study comets up close. In 2014, the Rosetta spacecraft orbited comet 67P Churyumov-Gerasimenko and landed a probe on its surface, the first landing on a comet. Images revealed a dark, irregular, porous object, far from the clean ice ball once imagined. Comets are complex with varied terrains, jets of gas erupting from active regions, organic molecules in their ices. Comets are time capsules. They formed from the same primordial material that built planets, but remained in the cold outer solar system, preserved, unchanged. Studying them reveals conditions in the early solar system, the composition of the nebula from which everything formed, clues about how planets assembled. Tonight, somewhere in the solar system, comets are drifting in darkness, frozen and ancient. Some are inbound, warming, beginning to glow as they approach the sun. Others are outbound, their tails fading, returning to the cold. And somewhere, far beyond Pluto, in the Oort cloud, trillions of comets wait in darkness, barely held by the sun's gravity, preserved for billions of years, waiting for the gravitational nudge that will send them falling inward, into light, into warmth, into visibility. The discovery of the Krebs cycle showed how cells orchestrate dozens of chemical reactions to convert food into usable energy. We talked earlier about the citric acid cycle and how it extracts energy from food. But let's linger here, in the quiet beauty of metabolism, in the elegant choreography of molecules transforming, energy flowing, life persisting through chemistry refined over billions of years. Hans Krebs worked out the cycle in 1937, studying how cells break down nutrients. He discovered a circular pathway of 8 major reactions, each catalyzed by a specific enzyme, each transforming substrates into products, extracting energy little by little, never in one explosive burst, but in controlled, stepwise releases. It's beautiful in its economy. The cycle regenerates its starting molecule, oxaloacetate, with each turn. Nothing is wasted. Intermediates can be siphoned off to build amino acids, nucleotides, other molecules cells need. The cycle is central not just to energy production, but to biosynthesis, to building the molecules of life from simple precursors, and it's universal. From bacteria to humans, nearly all aerobic organisms use some version of the Krebs cycle. It's been preserved for billions of years because it works so well, because it's efficient, because it integrates energy production with biosynthesis, because it's flexible enough to handle inputs from carbohydrates, fats, and proteins. The cycle operates in mitochondria, the descendants of ancient bacteria that merged with our ancestors' cells billions of years ago. So when you metabolize food, you're using machinery that's older than multicellular life, older than plants and animals, older than continents. You're using bacterial chemistry, preserved, refined, integrated into every complex cell on Earth. Each reaction in the cycle is a small miracle of chemistry. Enzymes bring substrates together in precise orientations, stabilize transition states, lower activation energies, allowing reactions that would take millennia to occur in seconds. They're biological catalysts, protein machines shaped by evolution to facilitate specific transformations with incredible specificity and efficiency. And the energy extracted doesn't appear as heat or light, but as chemical bonds. In ATP, the energy currency cells use, and in electron carriers like NADH and FADH2, which shuttle high-energy electrons to the electron transport chain, where more ATP is made. It's controlled, regulated, responsive to cellular needs. When energy demand is high, the cycle speeds up. When demand is low, it slows. Feedback loops and allosteric regulation ensure balance, prevent waste, match production to consumption. Tonight, as you rest, the Krebs cycle turns in your cells, slower than during activity, but still operating, still producing ATP to power maintenance, repair, neural activity, heartbeat, breathing, all the processes that continue even in sleep. Thousands of turns per second in each mitochondrion, millions of mitochondria per cell, trillions of cells in your body, an astronomical number of reactions, all coordinated, all regulated, all extracting energy from the food you ate, keeping you alive through the night. We learned that sound travels at different speeds through different materials, faster in solids than gases. We touched on this earlier, but let's return to sound, to vibration, to the physics of waves traveling through matter, because there's something meditative about understanding how connection happens, how energy propagates, how the universe transmits information through the simple collision of molecules. Sound is intimate. It requires contact, touching, matter pressing against matter. In vacuum, sound cannot exist. There's nothing to vibrate, nothing to carry the wave. But where matter exists, sound travels, transferring energy from molecule to molecule, from atom to atom, each one vibrating, passing that vibration to its neighbors, creating a chain of motion that carries information across space. The speed depends on the medium's properties. In gases like air, molecules are far apart, moving randomly. When one vibrates, it eventually collides with another, passing the vibration along. But collisions are infrequent, so sound travels slowly, about 770 mph in air. In liquids, molecules are closer, colliding more frequently. Sound travels faster, about 3,300 mph in water. This is why whales can communicate across oceans, why submarines use sonar, why sound underwater seems closer, more immediate than it is. In solids, atoms are locked in lattices, touching constantly, held by chemical bonds. Vibrations transmit nearly instantly from one atom to the next through those bonds. Sound travels fastest in solids, 13,000 mph in steel, even faster in diamond, the material with the strongest atomic bonds. So sound speed tells you about connection, about how close molecules are, how strongly they're bound, how efficiently they transmit vibration. Fast sound means tight connection, strong bonds, dense packing. Slow sound means loose connection, weak bonds, sparse distribution. And temperature matters. Warmer materials have faster moving molecules, so vibrations transmit more quickly. Cold materials with sluggish molecules carry sound slower. This is why sound speed changes with weather, why sound can refract through temperature gradients in the atmosphere, bending like light through a lens. Tonight, sound is traveling around you at different speeds. Through air at 770 mph, carrying voices, music, ambient noise. Through walls and floors, much faster, conducting vibrations from neighboring spaces. Through your body, flesh, bone, fluid, at speeds between liquid and solid, carrying your heartbeat's sound to your ears when you press them against a pillow. Carrying your voice's vibrations through your skull when you speak. You're a medium for sound, for vibration, for energy transmission. And so is everything else. The whole world is interconnected through touch, through contact, through the potential for vibration to propagate. Sound connects literally, physically, through chains of molecular collision, through networks of atoms passing energy neighbor to neighbor. And maybe that's a metaphor for how connection works in life. We transmit to those we touch, those we're close to, those we're bonded with. Information, emotion, energy, all pass through contact, through closeness, through the strength of connection. And the speed of transmission depends on the medium, on the quality of bonds, on how tightly connected we are. Loose connections transmit slowly, weakly, like sound, through sparse air. Tight connections transmit quickly, strongly, like sound through solid steel. And maybe wisdom is building strong bonds, creating solid connections, allowing fast transmission of what matters: love, support, understanding, energy, but also recognizing that even loose connections matter. Sound travels through air, slowly but effectively, reaching distant places, dispersing widely. Maybe we need both: tight bonds for fast, strong transmission, and loose connections for breadth, for reaching unexpected places, for carrying sound farther than strong bonds alone could. The discovery of plate boundaries explained where earthquakes and volcanoes cluster, mostly where tectonic plates collide, separate, or slide past each other. Earth's surface is broken into pieces: tectonic plates, massive slabs of crust floating on the semi-molten mantle beneath. And at the boundaries where plates meet, the planet is most active, most dynamic, most dangerous and creative at once. There are 3 types of boundaries: divergent boundaries, where plates pull apart. New crust forms as magma rises from the mantle to fill the gap. The Mid-Atlantic Ridge is a divergent boundary, a massive underwater mountain range where the Eurasian and North American plates separate, where new seafloor is constantly being born, spreading outward, pushing continents apart millimeter by millimeter, year by year. Convergent boundaries where plates collide. If both are oceanic, one dives beneath the other, subduction, creating deep ocean trenches and volcanic island arcs like Japan or the Philippines. If one is oceanic and one continental, the denser oceanic plate subducts, and volcanoes form on land, like the Andes or the Cascade Range. If both are continental, neither subducts. Instead, they crumple upward, forming mountain ranges like the Himalayas, where the Indian plate pushes into the Eurasian plate, raising peaks higher every year. Transform boundaries, where plates slide past each other horizontally. No crust is created or destroyed, just sheared, ground, scraped. The San Andreas Fault in California is a transform boundary, where the Pacific plate slides northwest past the North American plate, causing earthquakes as stress builds and suddenly releases. At plate boundaries, Earth is active. 90% of earthquakes occur at boundaries. Most volcanoes are near boundaries. The ring of fire around the Pacific Ocean is a ring of subduction zones, where oceanic plates dive beneath continental or other oceanic plates, melting, rising as magma, erupting as volcanoes. Iceland sits on a divergent boundary, the Mid-Atlantic Ridge, and has frequent volcanic activity as new crust forms. Plate boundaries are where Earth's interior reaches the surface, where heat and pressure and chemistry create landscapes, shape continents, build mountains, destroy flatlands. They're zones of transformation, of creation and destruction, of danger and renewal. Living near plate boundaries means accepting risk, earthquakes, volcanic eruptions, tsunamis, but also experiencing beauty, hot springs, geysers, dramatic landscapes, fertile volcanic soils, and understanding that Earth is alive geologically speaking, that the surface is temporary, that mountains rise and erode, that continents drift, that nothing is permanent. Tonight, somewhere, a plate boundary is active. An earthquake is shaking a coastline. A volcano is erupting, spewing lava and ash. A subduction zone is grinding, building stress that will release someday, suddenly, violently. And divergent boundaries are spreading, magma rising, new crust forming, continents inching apart. It's been happening for billions of years, since plate tectonics began. It will continue for billions more, until Earth's interior cools enough that convection stops, plates freeze, and Earth becomes a dead world like Mars. But that's far in the future. For now, Earth is alive, its boundaries active, its plates moving, its surface dynamic. And maybe there's a lesson in plate boundaries, that where things meet, where different systems collide or separate or slide past, that's where change happens, where energy is released, where creativity and destruction coexist. Boundaries are active zones, dynamic, risky, but also fertile, dangerous, but also beautiful. Maybe we have our own boundaries, between self and other, between past and future, between comfort and growth. And maybe those boundaries are where life happens, where transformation occurs, where earthquakes of change and volcanoes of creativity erupt. Maybe avoiding boundaries, staying in stable zones far from edges, means avoiding growth, avoiding risk, but also avoiding life's richness, its dynamism, its beauty. We found that some bacteria can survive extreme conditions that would kill most life. Extremophiles living in boiling water, ice, acid, or radiation. Life is resilient more than we once imagined. For a long time, we thought life required narrow conditions: moderate temperature, neutral pH, liquid water, protection from radiation, reasonable pressure. But exploration revealed organisms thriving in extremes we thought were sterile. Thermophiles live in hot springs, thriving at temperatures above 140 degrees, 60 degrees C. Hyperthermophiles survive even hotter, some at 250 degrees, 121 degrees C, above water's normal boiling point. They live near hydrothermal vents, in volcanic hot springs, in superheated environments that would cook most organisms instantly. Their proteins are stabilized by special structures. Their membranes use different lipids that remain fluid at high temperatures. Psychrophiles thrive in cold, polar ice, glaciers, deep ocean waters near freezing. They produce antifreeze proteins, maintain membrane fluidity with special lipids, slow their metabolism to match the cold, but keep functioning. Some organisms can be frozen solid and revive when thawed, their cells protected by cryoprotective molecules. Acidophiles live in acid, pH 2 or lower, as acidic as stomach acid or battery acid. Some inhabit acid mine drainage, others in volcanic acidic hot springs. Their cell membranes prevent acid from entering. Their internal pH stays near neutral, even when surrounded by concentrated acid. Alkaliphiles thrive in bases, pH 9 or higher, in soda lakes, in alkaline soils, in environments where most proteins would denature. They maintain internal pH balance through pumps and buffering systems, thriving where most life cannot. Halophiles love salt, Dead Sea, salt lakes, salt evaporation ponds. They tolerate salt concentrations that would dehydrate most cells, either by pumping salt out continuously or by accumulating compatible solutes that balance osmotic pressure. Barophiles, piezophiles, thrive under pressure, deep oceans, subterranean depths. Some require high pressure to survive, their proteins and membranes adapted to compression, unable to function at normal atmospheric pressure. Radioresistant organisms survive radiation doses thousands of times higher than would kill most life. Deinococcus radiodurans can withstand radiation that fragments its DNA into hundreds of pieces, then repair all the breaks and continue living, earning it the nickname Conan the bacterium. And polyextremophiles tolerate multiple extremes simultaneously: hot, acidic and high pressure, or cold, salty, and high radiation. They expand our definition of habitability, showing that life isn't fragile, isn't limited to a narrow Goldilocks zone, but can adapt, survive, thrive in conditions we thought were uninhabitable. This has profound implications for astrobiology. If life can survive such extremes on Earth, maybe it can survive on Mars, beneath the ice of Europa, in the subsurface oceans of Enceladus, in environments we once considered sterile. Extremophiles suggest life might be common in the universe, that habitable zones are broader than we thought, that wherever there's liquid water and an energy source, however extreme the conditions, life might find a way. Extremophiles also have practical applications. Their enzymes remain active under conditions that denature normal enzymes. Taq polymerase from a thermophilic bacterium is used in PCR, polymerase chain reaction, a technique that revolutionized genetics, enabling DNA sequencing, genetic testing, forensics, medical diagnostics. Industrial processes use extremophile enzymes for high-temperature reactions, acidic or alkaline conditions, anywhere normal enzymes would fail. The discovery of the blood circulation system by William Harvey showed that the heart pumps blood through a closed loop of vessels. For most of history, the cardiovascular system was misunderstood. Ancient physicians thought blood was continuously made in the liver and consumed by organs, flowing outward but never returning. The heart was thought to heat the blood, not pump it. Arteries and veins were seen as separate systems. It was all wrong, but it was accepted for over 1,000 years. Then, in 1628, William Harvey published De Motu Cordis, on the motion of the heart, describing a completely different system. Blood circulates, he said. The heart is a pump. It pushes blood through arteries to the body, and blood returns through veins, completing a circuit. It's a closed loop. The same blood goes around and around, not continuously made and consumed but recycled, endlessly circulating. Harvey's evidence was simple but convincing. He calculated how much blood the heart pumps per beat, multiplied by beats per hour, and got a number far larger than the body's total blood volume, meaning blood must be reused, recirculated, not freshly made. He showed that ligatures on arteries stop blood flow beyond the ligature, while veins swell below it, demonstrating that blood flows away from the heart in arteries and returns in veins. He demonstrated valves in veins that allow flow in only one direction, toward the heart. It was revolutionary. It meant the heart wasn't just heating blood, but doing mechanical work, pumping continuously, circulating blood through a vast network of vessels. And it meant the body was a closed system, maintaining and recycling its fluids, not constantly producing new blood. Harvey didn't know about capillaries, the tiny vessels connecting arteries to veins. Those were discovered later with microscopes. But he predicted they must exist, that there must be connections between the arterial and venous systems for circulation to work. And he was right. The heart pumps about 5 liters of blood per minute at rest, more during exercise. Over a lifetime, it pumps hundreds of millions of liters. Blood circulates your entire body in about 60 seconds, delivering oxygen and nutrients to cells, carrying away waste, distributing hormones, transporting immune cells, regulating temperature, maintaining pH. It's a logistics system, a transport network, essential for multicellular life. The circulatory system's discovery transformed medicine. It explained how poisons affect the whole body. They enter the bloodstream and circulate. It showed how bloodletting could be dangerous. It removes blood that's needed and will return anyway. It enabled transfusions, adding blood to someone who's lost it, replacing what circulates. It paved the way for understanding cardiovascular disease, for surgeries on heart and vessels, for medications that affect blood pressure and flow. We learned that galaxies have supermassive black holes at their centers, millions to billions times the sun's mass. At the heart of almost every large galaxy, including our own Milky Way, lies a monster, a supermassive black hole, millions to billions of times more massive than the sun, compressed into a region smaller than our solar system. These aren't the stellar black holes formed from collapsed stars. These are different, far larger, ancient, perhaps as old as galaxies themselves, and we still don't fully understand how they formed. The Milky Way's supermassive black hole, called Sagittarius A, pronounced Sagittarius A star, has a mass of about 4 million suns. It sits 26,000 light-years away in the galactic center, hidden behind clouds of gas and dust, but detectable through its gravitational effects. Stars orbit it at incredible speeds, some completing orbits in just decades, moving at thousands of miles per second. By tracking these stars' motions, astronomers calculated the black hole's mass and location with precision. In 2022, the Event Horizon Telescope captured the first image of Sagittarius A, a glowing ring of light around a dark center, the black hole's shadow. Other galaxies have even larger black holes. M87's black hole weighs about 6.5 billion solar masses. Some quasars, extremely bright galactic cores, are powered by black holes exceeding 10 billion solar masses, accreting material so voraciously they outshine entire galaxies. How did supermassive black holes form? We don't know for certain. They might have grown from smaller black holes that merged and accreted matter over billions of years, or they might have formed directly in the early universe from the collapse of massive gas clouds. Some might have originated as seeds from the first generation of stars. It's an active area of research, with observations of distant ancient quasars suggesting supermassive black holes existed when the universe was very young, which is puzzling. They shouldn't have had time to grow so massive. Supermassive black holes affect their galaxies profoundly. When matter falls toward them, it forms an accretion disk, a swirling vortex of superheated gas emitting intense radiation. Jets of particles shoot out from the poles at nearly light speed, extending for thousands of light years. The energy released can regulate star formation, heating gas, and preventing it from collapsing into new stars. The black hole and its galaxy co-evolve, their properties correlated. Galaxies with more massive black holes tend to have certain characteristics in their stars' motions and distributions. Despite their name, supermassive black holes aren't cosmic vacuum cleaners sucking everything in. They're dangerous only if you're close. within a few light years. Beyond that, their gravity is no different from any other mass. The Sun orbits the Milky Way's black hole at a safe distance, taking about 230 million years per orbit. Earth will never fall in. The black hole is just one mass among many shaping the galaxy's structure. But in some galaxies, black holes are actively feeding. Quasars, blazars, active galactic nuclei, shining so brightly they're visible across the universe. These were more common in the early universe, when galaxies were younger, more chaotic, with more gas falling into central black holes. Today, most supermassive black holes are quiescent, dormant, including ours, which accretes very little and shines faintly. The discovery of chemical equilibrium showed that many reactions reach a balance point rather than going to completion. In chemistry class, you might have learned that reactions go to completion. Reactants turn into products until the reactants are used up. But that's not always true. Many reactions reach equilibrium, a state where forward and reverse reactions occur at equal rates, where concentrations stabilize, where nothing seems to be happening even though reactions continue. Consider a closed container with nitrogen and hydrogen gas reacting to form ammonia. Initially, nitrogen and hydrogen combine, forming ammonia. But as ammonia accumulates, some breaks down back into nitrogen and hydrogen. Forward and reverse reactions both occur. Eventually, they reach equal rates. Ammonia forms as fast as it decomposes. Concentrations stabilize. The system is at equilibrium. It looks like nothing is happening. But microscopically, reactions continue, forward and reverse, constantly, dynamically. Molecules are still colliding, reacting, transforming. But the overall concentrations stay constant because formation and decomposition balance. Equilibrium isn't stasis, it's dynamic balance. It's like a crowded room where people enter and exit at equal rates. The number inside stays constant, but individuals come and go. The room isn't frozen. It's stable through continuous exchange. Chemical equilibrium applies broadly. In solutions, acids and bases reach equilibrium between ionized and non-ionized forms. In cells, biochemical pathways reach equilibria regulated by enzymes and feedback. In the environment, carbon dioxide equilibrates between atmosphere, ocean, and living organisms. Le Chatelier's principle describes equilibrium behavior. If you disturb an equilibrium, change concentration, temperature, pressure, the system shifts to counteract the disturbance. Add more reactant, and the system responds by producing more product. Remove product, and the system produces more to compensate. It's self-regulating, resilient, maintaining balance through response. This is key to homeostasis, how living organisms maintain internal balance. Your blood pH stays near 7.4 because chemical buffers reach equilibrium between acid and base forms, absorbing or releasing hydrogen ions to resist pH changes. Body temperature stays near 98.6 degrees because heat production and loss equilibrate, regulated by feedback loops. Blood sugar, hormone levels, electrolyte concentrations, all maintained through equilibria, through systems that respond to disturbances by shifting to restore balance. Equilibrium isn't a goal, it's a state that systems naturally reach when forward and reverse processes balance. And it's stable, resilient, responding to change by adjusting, by shifting, by finding a new balance point. Tonight, your body is at equilibrium, countless chemical reactions in balance, concentrations stable, processes offsetting each other. You're not static. You're dynamically balanced, reactions occurring constantly, but averaging to stability, held in homeostasis by equilibria, by feedback, by systems that respond to disturbances. And maybe life itself is about equilibrium, not achieving perfection or finality, but finding balance, responding to disturbances, adjusting to changes, maintaining dynamic stability through continuous adjustment. Maybe health is equilibrium, mental balance is equilibrium, sustainable living is equilibrium with the environment. We found that Earth's water may have arrived partly from comets and asteroids bombarding the young planet. Water is everywhere on Earth, oceans covering 71% of the surface, ice at the poles and in glaciers, water vapor in the atmosphere, groundwater beneath continents, water in living organisms. But where did it all come from? Earth formed hot in the inner solar system, where temperatures were too high for water ice to condense. The inner planets, Mercury, Venus, Earth, Mars, formed from rocky material but were initially dry, baked by the young sun's heat. So how did Earth get its water? The answer might be delivery. Water arrived from elsewhere, from the colder outer solar system, brought by comets and asteroids after Earth formed. During the late heavy bombardment, about 4.1 to 3.8 billion years ago, Earth was pummeled by impacts, asteroids and comets from the outer solar system, perturbed by the giant planets' migrations, falling inward, striking Earth, Moon, and other inner planets. Some of those impactors were water-rich. Comets are icy, formed beyond the snow line where water ice could condense. Asteroids in the outer asteroid belt contain water ice and hydrated minerals. Each impact delivered water, some vaporized by the heat, some trapped in rocks, some accumulating on the surface. Over millions of years, countless impacts brought enough water to fill Earth's oceans. It's not the only source. Earth's interior contains water too, not liquid oceans, but water chemically bound in minerals, trapped in rocks during formation, or delivered by early bombardment and subducted into the mantle. Volcanic outgassing released some of this water, contributing to surface oceans over time. Evidence for extraterrestrial water comes from isotopes. Water molecules have different forms: normal water, H2O, and heavy water with deuterium, 2H or D, a hydrogen isotope. The ratio of deuterium to hydrogen in water, the DH ratio, varies depending on where the water formed. By comparing Earth's DH ratio to comets and asteroids, scientists can estimate how much water came from each source. Current data suggests comets alone didn't bring all Earth's water. Their DH ratios are often too high. But asteroids, particularly those from the outer asteroid belt, have DH ratios similar to Earth's oceans. So asteroids might have been the main water delivery system, with some contribution from comets, outgassing, and possibly other sources. Water made Earth habitable. Without it, life as we know it couldn't exist. Water is the solvent for biochemistry, the medium where reactions occur, the substance that regulates temperature and climate. It's essential, and it came from space, delivered by impacts. A gift from the outer solar system to a dry inner planet. The discovery of symbiosis revealed that many organisms live in mutually beneficial partnerships, from gut bacteria to coral reefs. Life is often portrayed as competition. Survival of the fittest, nature red in tooth and claw, organisms struggling against each other for resources, for survival, for reproductive success. And competition exists, certainly, but it's not the whole story. Cooperation is just as important, perhaps more so. And one form of cooperation is symbiosis, organisms living together, often in mutually beneficial relationships. The word symbiosis originally meant any close relationship between different species. Now it often refers specifically to mutualism, relationships where both partners benefit. Your gut microbiome is symbiotic. Bacteria in your intestines help digest food, produce vitamins, train your immune system. In return, you provide them habitat, food, warmth. Neither you nor they could thrive alone as well as together. Coral reefs are symbioses. Corals are animals, but they host photosynthetic algae, zooxanthellae, in their tissues. The algae photosynthesize, producing sugar that feeds the coral. The coral provides the algae with nutrients and protection. Without this partnership, coral reefs couldn't build massive structures in nutrient-poor tropical waters. When stressed by temperature or pollution, corals expel their algae, coral bleaching, losing their symbionts and often dying. Lichens are symbioses between fungi and algae, or cyanobacteria. The fungus provides structure and protection. The photosynthetic partner provides food. Together they can colonize rocks, tree bark, harsh environments where neither could survive alone. Lichens are pioneer species, breaking down rocks, creating soil, enabling other life. Many plants form symbioses with mycorrhizal fungi. We mentioned this earlier. Fungi extend plant roots' reach, absorbing nutrients efficiently. Plants provide fungi with sugars. It's so common that most plants depend on these partnerships, and forests are interconnected by fungal networks. Nitrogen-fixing bacteria live in root nodules of legumes, beans, peas, clover. They convert atmospheric nitrogen into forms plants can use. In return, plants provide sugars. This partnership enriches soil, reduces need for fertilizer, supports ecosystems. Even mitochondria and chloroplasts are ancient symbioses. Once free-living bacteria that merged with early eukaryotic cells, becoming organelles, so integrated they can't survive independently anymore. Symbiosis challenges the view of life as primarily competitive. It shows that cooperation can be as effective as competition, that mutualism drives evolution, that interdependence creates stability, that partnerships enable possibilities impossible alone. And symbiosis is everywhere, in oceans, on land, in soils, in air, in bodies, partnerships connecting species, creating webs of interdependence, building ecosystems from cooperating parts. Life isn't isolated individuals struggling alone. It's networks, partnerships, communities, organisms living together, supporting each other, creating wholes greater than sums of parts. We learned that empty space isn't truly empty, but seethes with virtual particles popping in and out of existence. Vacuum, empty space, should be nothing. No matter, no energy, no activity, just emptiness, void, null. But quantum mechanics says otherwise. Even in a perfect vacuum, where all particles have been removed, where nothing exists, space isn't truly empty. It seethes with quantum activity, virtual particles appearing and disappearing, borrowing energy from the vacuum for brief instants, then annihilating, returning the energy, leaving no trace except subtle effects measurable through precise experiments. This is quantum foam, zero-point energy, the quantum vacuum, a state that's not nothing but not quite something either, a realm where uncertainty reigns, where particles briefly exist in violation of energy conservation because Heisenberg's uncertainty principle allows it for short enough times, where the vacuum fluctuates, creating particle antiparticle pairs that exist for fractions of a second before annihilating. We know this happens because we can measure effects. The Casimir effect, for instance, placed two uncharged metal plates very close together in vacuum, and they attract each other. Why? Because virtual particles exist in wavelengths. Between the plates, only certain wavelengths fit, but outside, all wavelengths exist. This creates a pressure difference, fewer virtual particles pushing from inside than outside. So the plates are pushed together by the imbalance in quantum vacuum fluctuations. The Lamb shift, a tiny energy difference in hydrogen's electron states, arises from interactions with vacuum fluctuations. Hawking radiation, black holes emitting particles, occurs because virtual particles near the event horizon can be split, with one falling in and one escaping, making it real, causing the black hole to lose mass. And perhaps dark energy, the mysterious force accelerating the universe's expansion, is related to vacuum energy, to the energy inherent in empty space, though the measured value is vastly smaller than quantum theory predicts, a discrepancy called the cosmological constant problem, one of physics' biggest unsolved mysteries. The quantum vacuum suggests that nothingness doesn't exist, that space has properties, energy, structure even when empty, that true emptiness is impossible because the universe doesn't allow it, because quantum mechanics forbids absolute zero, absolute stillness, absolute void. It's philosophically profound. Even nothing is something. Even emptiness has substance. Even void has activity. There's no escape from existence, no true absence, no actual null. The universe is fundamentally full, always active, never truly empty, never truly still. Tonight, the space around you, the air you breathe, the vacuum between atoms in your body, the emptiness between electrons and nuclei, all seething with virtual particles, with quantum fluctuations, with activity invisible and unmeasurable directly but real, proven, part of the fabric of reality. And maybe there's comfort in knowing emptiness isn't truly empty, that void has substance, that even when you feel hollow, alone, empty, there's still quantum activity, still energy, still potential. Maybe emptiness is never complete, never absolute. Maybe there's always something, some fluctuation, some potential, some seed of what might be, waiting in the void, ready to emerge. The discovery that we can edit genes using CRISPR technology has given us precise molecular scissors to rewrite the code of life itself. And so we arrive at the 100th discovery, the newest on our list, the most recent revolution. CRISPR, a tool that allows us to edit DNA with unprecedented precision, to change the genetic code, to rewrite the blueprint of life. It's borrowed from bacteria, refined by scientists, and it's transforming biology, medicine, agriculture, and raising profound ethical questions about what we should and shouldn't do with the power to edit life itself. CRISPR stands for Clustered Regularly Interspaced Short Palindromic Repeats, a mouthful that refers to sequences in bacterial DNA that are part of an immune system. Bacteria encounter viruses, and some bacteria can remember those encounters by storing snippets of viral DNA in their genomes between these repeated sequences. When the virus returns, the bacteria use those stored sequences to recognize and destroy it, cutting the viral DNA with an enzyme called Cas9. Scientists realized this system could be reprogrammed. Instead of targeting viral DNA, it could target any DNA sequence you specify. Design a guide RNA matching the sequence you want to edit, pair it with Cas9 enzyme, and the system finds that sequence in a genome and cuts it. The cell's repair machinery then fixes the break, and you can influence how it's repaired, deleting genes, correcting mutations, inserting new sequences. It's like find and replace for genomes. Precise, relatively easy, cheap, compared to older gene editing methods. And it works in almost any organism: bacteria, plants, animals, humans. Since its development in 2012, CRISPR has been used in thousands of experiments, advancing biology at breakneck pace. Applications are vast. In agriculture, creating crops resistant to disease, tolerant to drought, more nutritious. In medicine, editing immune cells to fight cancer, correcting genetic mutations that cause disease, potentially curing conditions like sickle cell anemia, muscular dystrophy, or cystic fibrosis. In research, creating animal models of disease, studying gene function, understanding development and evolution. In 2020, the first CRISPR-edited humans were treated for sickle cell disease and beta thalassemia. Doctors removed patients' blood stem cells, used CRISPR to edit them, then returned them to the patients. Early results were promising. Patients showed dramatic improvements, potentially cured. But CRISPR raises ethical concerns. Editing human embryos could change the germline. Alterations pass to future generations, affecting people who haven't consented. Designing babies, selecting traits, enhancing abilities, raises questions about equity, consent, what it means to be human. Who decides what genes are desirable? What about off-target effects, unintended edits, long-term consequences we can't foresee? In 2018, a Chinese scientist announced he'd created CRISPR-edited babies, altering the CCR5 gene to make them resistant to HIV. The announcement sparked global condemnation. The work was unethical, the medical justification weak, the risks unknown, consent questionable. He was sentenced to prison. The incident highlighted the need for regulation, ethical guidelines, international agreement on acceptable uses of gene editing. CRISPR is powerful, perhaps too powerful. It gives us godlike ability to reshape life, to edit evolution's 4 billion year text, to make changes that propagate forward through generations. And with that power comes responsibility, to use it wisely, carefully, ethically, with humility about what we don't know, with respect for complexity we're only beginning to understand. Sleep well, dream deeply, and know that tomorrow brings new discoveries, new questions, new mysteries, and you'll be there, part of it all, still wondering, still learning, still part of the great human story of discovery that began long ago and continues forward, always forward, into the unknown, into the darkness, seeking light, seeking understanding, seeking truth. Good night.